Hello everyone, I am Siddharthan. Welcome to the Generative AI hands-on course. If you are fascinated by the world of generative AI and large language models, but not sure where to start, you are at the right place. In this course, you will learn how to access state-of-the-art large language models and how to use these LLMs to build applications like chatbots, translator apps, and mainly retrieval augmented generation or RAG applications. I covered wide range of tools such as Hugging Face, Langchain, Streamlit, etc. that would help you in this learning journey. This course is beginner friendly, so you would find it easy but informative. This will be a continued course where I'll add more topics in the upcoming videos. And with that being said, let's start with understanding what are all the topics that are covered in this course. So first we will start with a conceptual video of transformers. So transformers are the engine behind this LLMs like GPT, Gemini and so on. So first let's understand the concept of transformers and how these transformers work. And then we will understand how we can access the OpenAI GPT models like GPT 4o, 3.5 and so on. So this particularly is done with GPT 4o, but the concept and the implementation is same for the other GPT models like 3.5, 4 and so on. And you will also learn how you can access these models with Langchain as well. The next topics will be how you can build application using these OpenAI GPT models, such as a chatbot that is interactive and a translator application where the user can select a language and do a translation. We will also learn how we can build the similar application using Google's Gemini, which is Google's proprietary LLM that has been launched as a competitor for GPT. And then we have this open source model, which is like really important. So we have open source models from Facebook, which is Llama, and Google has also launched its open source model Gemma. And you will learn how you can access this open source LLM with Hugging Face in Python. And we will also discuss how we can deploy our large language model using a tool called as Gradio. And then we will also understand the concept of retrieval augmented generation. So this is like a wide range of application that has been used in the LLMs, and you will learn the concept of RAG. And once we learn that, we will also build RAG applications with it. And the other topic that we'll be discussing is Ollama. So Ollama helps us to host models in our local system. So we will learn how you can host models like Gemma and Llama 3 in your local machine using Ollama. And then how you can build this RAG applications like document question answering with a Streamlit user interface where your LLM will be hosted in your local system with Ollama. So these are all the topics that will be covered in this particular course. And in the upcoming videos, in this upcoming part of this course, I'll also add more topics such as graph RAG, and using agents and so on. So this will be the agenda for this course, and I hope you get a lot of knowledge in this. So I've already made videos on this and I've curated this in one video such that it's easier for the users to find it and learn it with some tracking. Okay, so let's get started. Hello everyone, I'm Siddharthan. In this video, let's understand how does a transformer model works and how does it powers today's large language models such as GPT, Gemini Pro, Grok and Llama. So this will be the agenda for today's video, and let's get started. So this is a simple definition of what a transformer model is. A transformer is a neural network that learns the context of sequential data and generates new data out of it. So this is like a simple explanation of what is a transformer model. So it takes in a sequence of data as input. So it can be like a text or a prompt that you are asking it, and it generates the data out of it. So let's say that you are pasting a paragraph in ChatGPT and you are asking it to summarize. So this is a sequential data, and this takes this as the input. And now the output it's going to generate for you is the summary of this, right? So this is like a simple explanation. So all it does is it tries to understand the context of the sequential data that you are giving as input and generates the output sequence just like our human does in natural language. So let's understand how this transformer model came into picture in the first place. Transformers were first developed to solve the problem of sequence transduction. So sequence transduction is what we have just now discussed. So it's sequence to sequence modeling where you give a sequence of data as input to the model and it's going to generate another sequence of data as output. So sequence transduction or neural machine translation, which means they are meant to solve any task that transforms an input sequence to an output sequence, right? So it's all about giving it and getting out a sequence of data. So this is why they are are called as transformers, and they are used in this sequence transduction. So this is about transformers. And the thing about transformers kind of get widely known by the launch of the paper Attention is All You Need. So this paper Attention is All You Need was published by a bunch of scientists from Google, where they have used these transformer models for basic translation tasks. So before this, right, so before the introduction of transformer models, so we relied heavily on recurrent neural networks for NLP tasks like text classification or translation and so on. So RNN kind of had its own problem, which we will discuss in the next slide. But once transformer came, it kind of performed way better than RNNs could in like a lot of tasks. So that's about it. So now let's understand what are all the key advantages or the pillars of transformers that makes it like highly valuable, and then we can discuss about the limitations of RNN. Maybe in a later video we can dive deeper into this about the architecture of the transformer itself. So about this key advantages, right, so we have this concept of self-attention, and that's what they've used it in the transformer model. Like that's what like they've given in this paper as well. So self-attention is all about the ability of the model to weigh the important words. So let's say you have a sentence that has like 20 or 30 words. The transformer models are able to kind of determine which words are like really important by this method of self-attention. So they give this weightage for these important words to determine which word is important. So let's say that there is a sentence that says a cat is sitting on the wall. So here the words that are important are probably like cat, wall, and sitting, right? So this self-attention is able to capture all the important words in the sentence. So that's about this self-attention. And then we have this positional encoding. So the transformers doesn't have an inherent way to say that this is the position of the word in a sentence. So in order to kind of solve that, we have this part called as positional encoding, where all the tokens or the words in the sentence are kind of encoded in respect to their position as well, so that the model can now know where a particular word sits in a sentence. So this is kind of different when you consider a RNN model. So RNN models are the recurrent neural networks, works in a sequential manner, where it kind of looks at one word at a time and remembers the previous words that it has seen. But we don't do that in the case of transformers. So it kind of uses this positional encoding to like know the position of like all the words. So it doesn't go by sequence or like word by word. So that is like a key difference. And then we have parallel processing. So one of the reasons that RNN wasn't able to perform that well was they perform, or basically they understand this data in a sequential manner, and they kind of try to learn from it in a sequential manner. And because of this, it wasn't able to utilize or leverage the parallel processing power of the GPUs effectively. But when you think about a transformer, right, so it can do a lot of processes. So it has the self-attention, embedding, and so on. So all these processes can be done in a parallel way, so that the transformer models were able to kind of train or learn from a large data set. But if you're going with the RNN, it's not able, you wouldn't be able to you know take advantage of the parallel processing computation power that we have with today's GPUs. And the architecture about this transformer model is we have an encoder and a decoder kind of an architecture. And when you just kind of think about it, right, so the encoder's primary task is to process the input sequence and transform it into a dense representation, which is just a vector representation, and this captures the essential information. So and then we have this decoder, and the decoder's role is to generate this output tokens. So this generates this output tokens as a sequence. So this output sequence is generated one token at a time, and this is like using the encoded information that is coming from the encoder. And then we kind of have this entire sequence that comes out of this decoder. So this is how it works. So the first very important aspect is the self-attention, where it kind of knows, or it has this ability to know the weightage of the words in a sentence. Even if it is a long sentence, it's going to be hard for a RNN, but even when the sentence is long, so the transformers can weigh the important words. And then we have this positional encodings, where again, if you have a large sequence, it has this ability to know the position because of the positional encoding that we do, instead of like looking at it word by word, just like an RNN. And then because of these different abilities, it can do all these tasks in a parallel way, taking use of the GPUs that we have. And then we have an encoder which encodes all this information, the input sequence, and then the decoder which kinds of infer from the encoded information and gives you an output sequence. So this is like a basic explanation of how a transformer works. And now, in order to kind of appreciate this difference, right, so we need to understand how a RNN works and what are the limitations of the RNN model. So this slide is about that. So let's now maybe understand in a simple way of how RNN works. So I've given this particular example. Imagine an RNN, a recurrent neural network, as a person reading a sentence word by word, trying to understand the meaning as they go. So an RNN looks at this sentence word by word and it tries to kind of understand the meaning as it learns the entire sentence. As they read each word, they remember a bit about what they have read so far. That's their memory. So we have a concept of memory in RNN where it kind of tries to remember the previous words it has kind of learned. So this memory helps them understand the next word better and so on until the end of the sentence. So this process goes on. So it looks at a word, understand this, and goes to the next word, but it has this memory of the previous word, and this process goes on until it learns this entire sentence. But the problem with this is the challenge with RNN is that they might forget earlier information if the sentence is too long, or they might become confused if there is too much information. So this is like the biggest drawback of this. As this kind of learns word by word, it can kind of forget this information or the memory that it has if the sentence is like long as like a paragraph. And again, we have this different variations of this RNNs, such as LSTM, which is long short-term memory, and then we have this GRU. So this rectified this issue to an extent, but not to a larger extent. This is where the transformers work in a different way. So instead of looking at it word by word, it kind of looks at this entire sentence. So not directly, but by using this positional encodings and the ability to weigh the words by using the self-attention mechanisms, right? So we were able to do that. So now let's understand what are the actual limitations that RNN posed. So vanishing gradient problem. So this is like one of the biggest issue. So RNNs are prone to the vanishing gradient problem, where it means like the gradients, right? So in the back propagation, so gradients can shrink as it goes through the back propagation stage, and this makes it difficult for the RNN to kind of learn the dependencies between the words if again the text is long. So it's going to be difficult in order to, as if the sentence is long, you can think about it as like it's difficult for it to understand which words depends on which words in order to understand the context, and this also is creating this vanishing gradient issue. And then we have the sequential computation. As I said, we have this data flow that's going on in a sequence manner, so we wouldn't be able to take advantage of the parallel processing power that we have in the GPUs. And if you think about it in terms of transformers, right, so we have the self-attention, where self-attention is basically a bunch of matrix operations and matrix multiplication happens there. So all these operations can be done in a parallel way in GPUs when you use a transformer, but it's difficult in terms of RN, as we are looking like word by word. So this is another issue. And difficulty handling long dependencies. So this is what we have seen. So if the sentence is long, just like a paragraph, and we have different words, it wouldn't be able to kind of, let's say, understand the context of the word that is coming later in a paragraph to the word that's coming like kind of earlier. So if you look at it together as a paragraph, it might be important, but the RNNs won't be able to make sense of it in a good way. And then we have the scalability issue, and RNNs do not scale as efficiently as transformer when it comes to large data sets and larger sequence due to their sequential processing and computational requirements, right? So we know that the chat GPTs and the llamas are trained with like, most probably like the entire internet stuff data. So if you're going with RNNs, it's not computationally efficient, as again we have this limitation on how we are going to do this parallel processing and so on. So these are the limitations that RNN posed, but in the case of transformers, we were able to kind of address all these things and build this self-attention model that has this capability to say that, I can understand the sentence, the words in it, and weigh that this word is important in a sentence, and I'm going to use this in order to make a decision. So this is about the transformer models and how this transformer model works. And the main aspect that you have to remember here are, it kind of takes in the input sequence, is basically the sequence of data is the input, and it's going to generate an output sequence. And the key factors about the transformers are the self-attention mechanism and the positional encoding. So these are like very key aspects. So I hope everyone is clear until this point. Maybe at a later time I'll make a detailed video on the exact architecture. So how this positional encoding sets and what are all the different layers. So we have a multi-layer thing, and we have this multi-yet attention and so on. So we will discuss about all these things in a later video where we'll be discussing about the architecture. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. In this video, let's discuss how we can access OpenAI's newest and most capable model, GPT-4o, which stands for GPT-4 Omni, in Python using OpenAI library. So this will be the agenda for today's video, and let's get started. So I'll open my Google Collaboratory session. So here what we are going to do is install the OpenAI library, get the keys from OpenAI, and access the GPT-4o model for tasks like chat completions and image processing and so on. So we know that this GPT-4o, the generative pre-trained transformer for omnis, this is the full extension. So this model is model, so that means like it can take inputs in different formats. So it can take text input, and it can also take image input. So they are going to launch this for audio as well, but for now let's just work with this text and image. So that's what we are going to see here. So first let's connect our collaboratory session and install the OpenAI library. So let's say pip install, I can put double hyphen and say upgrade. So this will make sure that if you already have OpenAI, this will upgrade it to the most latest package. So if you don't have, it will just install the latest library that you have for this OpenAI. So let's run this. So this will install this OpenAI library. And now let's import the dependency. So here we are just going to use the OpenAI library alone. So I'll say importing the dependencies. So now let's import OpenAI. So the next step is we have to configure this session, this OpenAI package with our API key. So I'll name this as configuring OpenAI key. So now let's see how we can get this OpenAI key. So go to Google and search OpenAI. So I hope that you already have an account in OpenAI, and they give like $5 credits per month for which you can use in order to access these models in the APIs. So go to this openai.com site. So if you scroll below, you have this different options for everyone, for teams and so on. So here you can see like the latest GPT-4o model that has been launched. So I've already made a video about this, you can check that out too. So if you scroll below, so we have this for business section and then for developers. So here we have this API, right? So go into this API section and go to this start building, and you can also check the pricing there. So now we have to log in order to get our API key. So I'll click this login. So I'll pause this video and I'll log in into my account. So I've logged in into my OpenAI account, and here you can see the API keys and the usage. So the usage will tell you like how much you have used and the number of credits that you have in the balance. So you can check that out here. Okay, so that's about it. And then you have this option of API keys. So this is from we can like kind of generate the API keys and we can use it in our code. So here I'll delete the key that I already have. So I'll revoke this key. And then you have this option of create a new secret key. So for this GPT-4o, right? So what I realized is that it's not working when you don't have a payment method. So if you haven't like have this card details, so it's not like working for Chat GPT-4 and the GPT-4o model, but GPT 3.5 is working without the card with the default $5 credit. You can even, if you are not comfortable with putting your payment method, you can just try it with 3.5 model as well. So it should work the same way. So here I'll give this create new API key, and I'll call this as GPT-4o testing key. And we have the permission. So whether we have this restricted permission, and like you can say like which are all the capabilities that this particular API key can use, and if it's like only read only and so on. So here I'll give this all, and I don't have any different projects, so it's like only one project, the default project, and I'll give the permissions as all and create this secret key. So now we will see this. So we can copy this and paste it in our code. So once you are done with this, you can revoke this API key, and if you want, you can generate a new one. So here I'll come back to this place and say OpenAI dot API key is equal to, so within the quotes I can paste my key. So here, this is not like the most recommended way to do this, because you can't kind of put your keys just in your code, because you might have to share it with someone else, right? So what you can do is put this in a config.json file, read the JSON file, and then pass it to this API key. That's one way. Or the other way is put it in a .env file and load it with this .env. So that's like much better. But for easier explainability, I'll just put it here. So let's run this. Now let's build our two use cases. One is chat completion and the other one is image recognition kind of a task. So first thing is about chat completion. So here I'll create a variable called as response. So this response is equal to, say, OpenAI.chat.completions. So from this chat.completions module, we are going to use this create function. And now open your parenthesis. The first parameter that we have to pass is model. So what's the kind of the model that you're going to use? So here I'll say GPT-4o. So this is how you can mention the latest 4o model. So you have like different models that you can access from. So here you have this docs, right? So you can go to this docs and see like the different models that you have. So we have this GPT-4o, GPT-4 turbo, GPT 3.5 turbo, and so on. So you can also like check the other models that you have. So here you have this models section, right, in the documentation. So here you can see GPT-4o, the fastest and the most affordable flagship model, and the different versions that you have, Dolly and other things. So here I'll mention this GPT-4o. So this uppercase and lowercase, all this should be, the same way as I've mentioned here. So the next is this kind of a payload that we have to give. So create this, or we have to pass this parameter called messages, and open and close a list here, and we have to pass a bunch of dictionaries. So first I'll say role is system, and the content in this case is going to be, I'll explain you what is the meaning of all these things. So you are a helpful assistant. So the second one is this role user. So the user would ask, let's say, this is like the default example that's given in the documentation. So I'll say who won the World Series in 2020. Okay, so this is the question. So let's understand what it basically means. So chat completions, how it works is, so you give like few conversation memory, like let's say there is like two messages that has been sent by the user, and the assistant has sent two messages. So you can pass this to kind of ask the assistant, which is GPT-4o in this case, to kind of continue this conversation or answer a particular question. And the first thing that we are passing here is the system message, which says you are a helpful assistant. So we have this two key value pairs. First one is role and the second one is content. So role is, when we mention system, that means it kind of sets the context for the model. So in the role of system, we are saying that you are a helpful assistant. That means now the model kind of takes in the role of being a helpful assistant. Now we have the user's question of who won the World Series in 2020. So this is the first question, and let's say the role is now assistant. So this is again, let's put this tab again. As I said, this is the default example that they have given in the documentation as well. So we can see it in this Google's collab prompt as well. Okay, so let's understand this. So first we are setting up the system saying that you are a helpful assistant, and then we are asking a question of who won the World Series in 2020. If a user asks a question, so the assistant would have answered it this way. So the content would be the Los Angeles Dodgers won the World Series in 2020. And then we have another question of role of user content, where was it played. Now we pass this, and the GPT-4o model has to respond to this question. So this is just an example. So similarly, you can have like a different system message, kind of intending how you want your model to be, and you ask like any question based on that. So that's how we can access it. So this is how chat completion works. So I'll run this. So the response will be stored in this variable called as response. I'll run this. Now let's print this response. So again, as I said, if you don't have a payment method enabled, right? So if you don't have any card details associated to it, it's giving an error for GPT 4o and the 4 turbo models. But if you try 3.5 turbo, it's working. So you can check that out. If you have some card details that you can put into, you can probably use that. And again, you have this $5 credits in your account. So now let's print this message. Print response dot choice 0. So response dot choices of 0 dot message dot content. So this will print the exact message, but if you want to see the entire response, you can just print that. Sorry. Okay, so let's print this and see. Right, so we have this chat completion thing. So we have this choices, and within this choices we have this list, we have this choice, and then we have this message and content. So this is what we are accessing from here. So when you call this response dot choices, so it will access this choices parameter thing, and then it will go to the first value of this list. So it goes to this choice, and within this choice it takes this message dot content, which is this message dot content, which is equal to this is the answer that we are seeing. So if you want to access this message alone, you can use this print response dot choices of 0 messages dot content. So you will see the exact message. So we have the message here. If you want to see this in the single place, you can just, instead of print, you can just put in this response thing. So this will show you the response. So the 2020 World Series was played at Globe Life Field in Texas and so on. So this is how you can kind of build this chat completion thing, where instead of this example, you can also have like a different question and answer kind of a thing to just give some context to your assistant. And later you can ask a question of where is it played, or where was it played, or like who was the MVP and so on. So you can ask questions like this. So this is how we can access this chat thing. So all the things would be similar for other models too, but again, if you have this thing of like, using this for a more complex task, you can use this as well. So the next thing is we are going to use this for image recognition task. So here I'll say this is not, image recognition task, or you can ask like any question from this. So or we can also name this as image processing. So anything you want. We know that this is a multimodal, as multimodal capabilities. That means it can take inputs in different data types. So I'll just create this as multimodal input. So this also kind of follows like a similar way of messages. Let's see how we can do that. Say response is equal to OpenAI dot chat dot completion. So we can use the same thing, completions dot create, and first we need to say model is equal to GPT-4o and messages is equal to the same thing. First is the role, which is the system message. So I'll just use the first one. So you are a helpful assistant. So that is enough. So this is set with the role as system. And next I'm going to say role is user. So this means that this is the user's question, right? And the content is open a list, and I'll come to the next line and say type is text. I'll explain you the formatting of this, so you don't have to worry about this. So this is type is text, and this text is what is in this image. Okay, And now the next thing that we are going to pass is type image URL. So you should also have like different options to do this. So here we are going to pass URL for an image and ask the model what it is, but you should have other option to just pass an image directly in a different format. So that should also be possible. So we have this image URL, and in the next line, let's say image URL. Yes. Let's take an image from Google. So I'll just go to Google and search Switzerland mountains. So I'm just going to randomly pick an image, and let's pass this image, this URL, and get the prediction of like what it is. So I'll just like choose some image. So here you can right click this and use this copy image address. So this will copy the URL of this particular image and paste it here. So we have this image now. Put a comma here, and you just have to close all these things with like proper commas. So use a comma after this ending things. Yeah, this should work. And finally, after this last square bracket, we have to say max tokens is equal to some number 300. Okay, so let's understand this. So if you want, you can also add this temperature thing, but yeah, this is sufficient for now. So max tokens is basically the number of maximum tokens that you can have in your output text. So that's what it means. So let's understand this thing. So first we have this response is equal to OpenAI.chat completions.create. So here we are using the GPT-4o model and saying messages is equal to role system, content is you are a helpful assistant. And in the role of user, so the user is going to ask an image and pass kind of an image to the model. So let's understand this format. So we have this content, and previously within this content we have just passed this text. Now we have two input from the user. One is the text itself of asking what is that image is, and the next one is the image itself. So in this content we have this type, and within this type we are passing this text, and the text is nothing but what is in this image. The next parameter or the dictionary that we are passing is the image itself. So we have this type, and type is image URL. So next in next place you are passing the image URL, and here we are seeing that URL is equal to this thing, and finally saying that max token is equal to 300. So let's run this. Missing required argument, messages and models. Okay, I think there is some issue with the parameters that we have mentioned. So let's validate this once. So first we have this chat.completions.create, model is equal to GPT-4o, messages is equal to role, and so there is a issue with the spelling. So instead of messages I use this one. So say messages, and here we can say max tokens. Let's run this. So now we are getting a response, and this will be stored in this response. So similarly you can just copy and paste this same thing. So you can do a print statement or without that as well. So this should work. So I'll paste it here. So you will see the response, and I can just do this without the print statement as well. Let's see what it says. So it says this image depicts a picture alpine village at dusk or early evening and so on. So it's snow covered buildings and blah blah blah. So this is the response we are getting, which is like pretty accurate. So this is how you can pass an image and ask like questions from it. So here we are just like kind of saying the system or saying the assistant that you're going to be an helpful assistant, and passing a text of asking what is in this image, and then passing a image URL. So similarly you can use this for other tasks as well. So these are the two use cases that I wanted to share with you today. One is just chat completion text based input, and the other one is passing like an image along with this text. So in the later videos, let's understand how we can use this GPT-4o model for other advanced tasks such as drag, and how we can use this in order to get multimodal outputs as well, like how you can generate images out of this and so on. So I hope everyone is clear with this video, and I believe that this is useful to you. So please kind of try this code, access this OpenAI model and try this. So as I said, if you have this payment options, you can use that and use the GPT-4. If not, you can just use the other models that are available. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I am Siddharthan. In this video, let's understand how we can access OpenAI's newest model GPT-4o with Langchain. Understanding how we can access this model with Langchain will be extremely useful for you when you are working on use cases such as RAG or building an application with the AI agent with Langchain. So let's try to understand how we can do this in Python in Google Collaboratory, and this will be the agenda for today's video, and let's get started. So I'll open my Google Colab where I will install the required libraries and connect to OpenAI with my API key and then load the model with Langchain and ask it some question and get a response from it. So the first step is to install the required libraries, and I'll connect my system over here and say pip install Langchain and Langchain OpenAI. So these are the two libraries that we need. One is Langchain and the integrated Langchain and OpenAI, using which we will load the model. So here, instead of just pip install, I'm going to add a tag with this double hyphen and upgrade. So what this upgrade tag will do is, if you already have installed Langchain and Langchain OpenAI in your system, it's going to upgrade it to the latest version. So if it's not present, it's going to install the newest version that's available for these two libraries. So I'll run this. So this will install these two libraries, and in the next step we can import the required libraries and then kind of invoke the model and do that, and also configure the Langchain OpenAI with the API key that we can get from OpenAI. So in the next step I'll say import OS and then from Langchain underscore OpenAI import chat OpenAI. So pay attention to the upper and lower case letters. So let's run this. So this OS library here is used in order to save the API key from the OpenAI into the environment variables of this session. And then from this chat OpenAI, we can load the GPT-4o model. So the next step is getting the API key. So go to Google and search OpenAI and openai.com. So there you will see this tag or this tab called as products, and within that go to this API login. So this will ask you to log in with your account. So once you're logged in, you will see this page. One is chat GPT and the other one is API. And by this point, I hope that you already have an OpenAI account, and GPT-4o model, if you want to access it, you have to have some payment method enabled, like a card or something else. So if not, you can try with other models like GPT 3.4. That shouldn't require you to kind of sign up with this payment method. So that's one thing to remember. So I'll click this API here, and in the left navigation bar we can go to the API keys. So this is the place from where we can create our API keys, and here I'll give this create new secret key. We can name this as, let's say, Langchain integration, and you can leave the other things by default. So if you have some other projects created, you can select this as per your need. And now I'll say create secret key. So this is going to give my API key, and I'll copy this and close this, and I'll come back here and say os.environ, and within this I'll create a key called as OpenAI underscore API key. So this name shouldn't change. This environment variable name shouldn't change, because when we load the model, right? So this is the place from which it's going to look for the API key. So you kind of shouldn't give a different name for this. So this should be uppercase and OpenAI underscore API underscore key. And within that, we are going to pass the API key that we have copied with, which is this. So this is how you can store the API key in your environment variable called as OpenAI API key. But pasting it directly in the code is not recommended. So instead, what you can do is you can save this key in a config.json file with this as the key and this as the value, and load it using this JSON module that you have in Python. Or the other better way is to put this key in an environment file. So you have this .env file into which you can put this key and this API key as well, and then you can load it using this load.env. So that's like a better approach as well. So for demonstration purpose, I'm just putting this API key in the code, but it's not recommended. Okay, so that is the next step. So let's run this. Now I'm going to say LLM is equal to chat OpenAI, and then we are going to pass the model name. So we have this parameter called model, into which we have to name the model that we are going to use. So GPT hyphen. So if you want to use 3.5 turbo, you can use this. For GPT-4o, just say GPT-4o with smaller case letters. And then I'm going to say temperature. Okay. So the temperature should be, sorry, let's say 0. So again, you can explore the other hyperparameters that you have. So this temperature, what it does is, it's how much random you want your responses to be. So if the number is closer to 0, that means each time you ask a specific question, it's going to give you different answers. So sorry, when the number is closer to 0, it won't give you different answers. The answer will be similar. But if the temperature value, it's kind of an hyperparameter, right? So if the value is closer to 1, it's going to give you different responses for the same question. So if it's 0, it's going to give you the same response every time. So it's more or less like it's the same response. So similarly, you can also include other hyperparameter as well. So here we are creating a variable called as LLM, and to this LLM we are loading the model from chat OpenAI, and the model that we are going to load is GPT-4o, and the temperature is 0. So let's run this. Now we can pass a message and get a response from this LLM. So I'll create a variable called as messages, and this is the format in which you can pass this. So create this variable and create a list. And within this list, I'm going to say we are going to have like 2 other tuples here. The first one is the system message. So let's call this as system, and the message can be, you are a helpful assistant that translates English to French. And then I'll put a comma. In the next tuple, I'm going to pass the exact message that the assistant needs to translate. So the first value will be this human, and I'll say translate this sentence from English to French. So let's understand what this formatting is. So let's close this, or we can add the exact sentence as well. I'll say I love programming. Okay, so this is the sentence that we are going to translate. Okay. So first we have the system, right? So in the system element, we have to say what the assistant is going to do, or what's the LLM is going to do. So it's just like setting the context for the LLM. So in this case, we want our assistant to be a translator. So I'm saying that you are a helpful assistant that translates English to French. Or you can also have a different context, saying like you are a helpful assistant that answers a specific question, or you are an helpful assistant that does this chat completion, and so on. So similarly, we can set up some context. And in the next thing, we are having this human. That means it's a human message. So it says translate this sentence from English to French, and the sentence is I love programming. So when we pass this to LLM, it will look at the system message and understand like the purpose that it has to kind of do. And then we are passing this human message saying that you have to translate this, and the exact sentence is I love programming. Now we can invoke this LLM and pass this message. So I'll run this and say response is equal to llm.invoke, and within this parenthesis pass this messages. Okay, now let's run this. So this will call the GPT-4o model, and this will give the response, and as you can see, the response are like pretty quick. You can print this response to see how the formatting is. So we have this AI message, and the AI message has this kind of key called as content, and then we have this thing as this specific sentence, which is the French form of I love programming. So in order to extract this content alone, so you can just say response.content. So this will be a string variable. So I'll say response.content. So let's run this, and this will print the exact message. So this is how you can pass a message with the system configuration of what you want the LLM to do and the exact human sentence, and the LLM can do the rest. So we are loading this LLM from this chat OpenAI, and then we are setting up the temperature and invoking the LLM with this message and so on. So this is how you can do this. And there is another variation of this called as chaining, and that will also be really helpful. So let's understand that as well, which is a bit similar to this. So I'll create a text cell here and call this as chaining. So what we are going to do here is chain the model, or let's call this as chain the LLM with a prompt template. So we are going to use a prompt template and we are going to chain it with the LLM so that it kind of solves this purpose, and you will understand like what it exactly does once we complete this. So here from Langchain underscore core dot prompts. So this Langchain core is like another sub module of Langchain. So from this prompts, I'm going to import prompt chat prompt template. So okay, so C, P, and T should be in uppercase letters. So from Langchain underscore core dot prompts, import chat prompt templates. And here I'll create a variable called as prompt, and this prompt is equal to chat prompt template. And dot from messages, open the parenthesis, and then we have to create a list, and within that we can say first is system, and within this we can say you are a helpful assistant. The translate, so here we are not going to say English to French, so we wanted to translate from one language to another using this chat prompt template. So this T should be in caps. Okay, so you are a helpful assistant that translates input language to output language. And then the next parameter will be human, and then we are going to pass the input. So this input languages, so all these will be substituted later, so all this should be present in this curly braces. Okay, so that's about it. So we have this system message setting up the context that it should translate from the input language to an output language. So that is the first step, and then we have the human message within this input. So now I'm going to create a variable called as chain, and chain is equal to prompt, and use this vertical bar and say LLM. So this is what we kind of represent chaining by. So chain is equal to prompt and vertical bar LLM, and say response is equal to chain dot invoke, and create a dictionary, and here say like what's your input languages, what's your output languages, and what's the input message. So input languages, let's say English, and the next key value pair is output language. Let's say the output language is German. You can like try any languages that GPT-4o supports, and finally we have to pass this input, the exact term. So that will be input is equal to, let's say, I love programming. Okay, so this is how chaining works. So you kind of chain the prompt and the LLM together into this variable called as chain, and you invoke this chain with the input language, output language, and the input. So here we have this prompt, right? So this input language English substitutes this part, and the output language German substitute this part, and then we have this input which will be substituted by this particular key value pair, and that's why we have all these in the curly braces. So when we run this, this chain will invoke the LLM with this particular chat prompt template with all the system and human message, and then we will get a response. So this LLM is something that we have already loaded using this LLM chat OpenAI thing. So let's run this and print and see this response. So here also the response will be pretty quick. So you say this particular statement that's probably in German for the sentence I love programming, and if you want to extract this particular output alone, say response.content. Okay, so this is about chaining method where we chain this prompt with an LLM and just write some invoke statements. Okay, so this is how you can invoke this newest LLM GPT-4o from Langchain, and this process is same for other GPT models as well, GPT-4 or GPT 3.5 and so on. Okay, so I hope everyone understood until this part. So here we basically did two things. So the first one is kind of invoking the LLM, just passing context and human message, getting a response, and then we have this chat prompt templates where we set up a template for this prompts and then later replace so that we can do this for different languages and get a response. So that's it from my side, and please try this code and let me know if you face any issues. So I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. In this video, let's discuss how we can build a Streamlit chatbot using OpenAI's newest model GPT-4o. We will build a Streamlit web app similar to this where we can ask the question which will be answered by GPT-4o, which stands for GPT-4 Omni model. So this is a simple text-based chatbot, and later we can also work on including the multimodality of images and audio, and we can also work on concepts like RAG. So here I've asked a question about what is machine learning, and we are getting this detailed answer from GPT-4o model. So this maintains a clear memory, so we can continue this conversation. So next I have asked the question of shorter answer. So this will look at the previous conversation and answer based on that. So when I ask for shorter answer, it will look at the previous answer it has given and gives a shorter response for this. So here we are seeing a shorter definition for machine learning. I've also asked the question of Python code to train a neural network with PyTorch. So here we get a response with proper formatting of the Python code. So we will build this application with Streamlit, and we will also discuss how we can configure our OpenAI and how we can use the GPT-4o model. So this will be the agenda for today's video, and let's get started. So I'll open my PyCharm, and PyCharm is like a better IDE in order to work on this. So you can either use Visual Studio Code or PyCharm, or you can also use Spider, but PyCharm will be like a bit better. So I've already made video on how you can set up your project with PyCharm, so you can refer to that. So here I'll create a new project, and so this is the location in which it's going to be saved, and here I'm going to rename this. So let's say that I have this folder called as LLM where I'm going to make this. So here I'll select this LLM, and when I give a name for this, it will create like another subdirectory where my project will be created. So I'll call this as GPT-4o chat, and I'll just put a name for this. So I'll just put this as May 17. So this will create a virtual environment within this particular directory. So it's always better to have this virtual environment so that your other projects libraries are not changed. So I'm going to give this custom environment, generate new virtual environment, and the version that I'm working on is 3.10. So if you want, you can also like use a latest version. So I'll give this create, and I'll open this in new window. So this is the previous Streamlit app that I had, so I can kind of keep this running, and later I can stop this one. Okay, so this is the new project directory that it has created, and it has this venv. So now here I'm going to create a folder called as src, which stands for source code. So this is like a standard approach of the folder structures and the code files. I'll also create a file and call this as requirements.txt. So it's always better to put your codes within this src, and in the default project directory you can have the file for requirements.txt, which would have your library details. And within this src we can create another Python file and name this as main.py, which is again the standard naming convention. And within this main.py file we can have the code for our Streamlit app and calling this OpenAI model and so on. So for this particular use case, we are going to need like two libraries. One is OpenAI in order to access the model, and the other one is Streamlit. So I'll use OpenAI. So we can use the latest libraries in order to find this latest libraries. So you can go to Google and search OpenAI PyPI. So this would show you the latest library version. So I'll just copy it from here. So the time that I'm making this video, it's 1.30.1. So these libraries are like kind of constantly getting updated because of the new models and the new features that they are providing. So here I'll say OpenAI is equal to 1.30.1, and the Streamlit's latest version is 1.34.0. So this is the latest version by the time that I'm kind of using this video. So you can use the same requirements.txt file. So now I'll open my terminal so you can see this directory. So this is in GPT-4o chat, which is the one that we have created, and here I can say pip install -r requirements.txt. So this will install all the libraries that I mentioned in this requirements.txt with this specific version and all the other libraries that this two packages need. So I'll run this. So this will run the required libraries, which is basically OpenAI, Streamlit, and other dependent libraries. So this is the first step. So next, what we will be doing is import the necessary libraries, configure our OpenAI package with the OpenAI API key, and then we can write the code for this. So this will be the process. So in the meantime, this code is, the libraries are getting installed. Let's open this main.py file and get started with the code. So first is we need to import the required libraries, as I said. So I'll import OS in order to access some directories and some files. And let's import this JSON and then import Streamlit as ST and import OpenAI. So this is again another standard. So we kind of import the inbuilt libraries first, give a line space, and then import the other libraries. So if you have custom libraries like, let's say, OpenAI utils or LLM utils, you can import those custom Python scripts in the next line. So that's like a standard procedure. But yeah, for us, we don't need it. So I'm importing these things. Now we have to configure our API key. So for that, we need to get this, and our API key can be stored in a file called as config.json. So I'll right click in this source, create another JSON file. So I'll create this file and call this config.json. So you can kind of copy and paste the OpenAI code here, but it's not recommended. So it's always better to put this in a configuration file, or you can put this in a .env file and load it using load.env. So that is like better approach. So you can either do this JSON approach or the .env approach. So here I'm going to create a key value pair. So I'm going to call this OpenAI API key. So put these things in quotes. So go to Google, search OpenAI. So in the previous video, we have discussed how we can access this GPT model and ask a question. So there I've explained you how you can get this, API key. So this is the process. So just search OpenAI and go to this. We have this research for business developers and so on, right? So come to this API section and give this start building. So this will ask you for login. So I hope that you already have a login page. So here you will see a sign up and sign in option. So I've already logged in, so I'm seeing this, and in this navigation bar you will see this API keys option. So I've already created a API key, so I can see this API key. So if you want to create a new one, so you can just revoke this API key and create a new API key here. So I'll create a new API key and I'll call this as GPT-4o chatbot. So default project, you can set up your permissions and so on. So I'll create the secret key and I'll copy this and put it in my config.json file. Okay, so now we have to access this API key and pass it to the OpenAI configuration thing. So I'll close this config.json, and here this part is for configuring OpenAI API key. I'll open the terminal and see if the libraries are installed. As you can see, all the libraries are installed. So I'll just clear the logs in the terminal. So now I'll say working directory is equal to os.path dot directory name os.path dot absolute path file. So this is a very important aspect. I'll explain you in a minute what we are doing here. So here I'll create a variable called as config data, which is equal to json.load open if working directory /config.json. So let's understand this. So this line of code, right? Look at the 9th line code. So here we are opening this config.json file and loading that to a dictionary called as config underscore data. So that's what we do using this json.load open. So first the file is open, and using this json.load, it's converted into a Python dictionary and stored here. Now when you give this without this working directory, what will happen is it won't be able to locate this config.json file, because when you run a Streamlit app, it won't run in this particular working directory, which is this GPT-4o chat directory and src. So this is the directory in which main.py file is there, but it won't run there. So it will run in the place where you have installed Python, or basically it will run in your users. So let's say that in my PC it would run in users and sit. So that's the user name that I have. So it will run there. So we have to give this complete path or the full path of this config.json. So what I can do is right click here and go to this copy path or reference and copy this absolute path. So I can copy that and put it in this place. So I can do that. But if I share this code with someone else, right, then they have to change this path and give the path that they have in their system, right? So that's not a better way to write your code. So what we are doing here is, when I call for this working directory os.path directory name os.path absolute path of file, so this will look at this main.py file where we have written this code and get the path of this working directory, basically the working directory or the directory where your main.py file is situated. So that's stored in your working directory. And now we are going to pass this. So working directory /config.json. So when you run this code in your local machine, so it will automatically pick up the path of this main.py file, and it can access this config.json provided you have this config.json file. So that's the idea behind this. Now we have this config.json and it's a dictionary, right? So we can also try printing it. So print config.data. Config underscore data. Let's print it and see the result. So we have this open API key is the key, and the value for this pair is this one, right? Now we have to configure our open AI package. So let's do that. I'll create like a constant kind of thing and say open AI API key is equal to config data, and we need to pass the key. So the key for this dictionary is open AI API key. So let's copy that and paste it over here. So this API key is loaded into this particular variable. And now I'll say OpenAI, which is the library that we have imported. So OpenAI dot API key. So this is how you can configure this, is equal to OpenAI API key. Okay, so the simple step of doing this is, instead of having this in a config.json file, you can just paste your key here. But as I said, it's not recommended to put your key and secrets in your code, so that, I mean, you won't be able to share it, right, if you put your key. So that's the purpose. We put this in a JSON file or a .env file and work on it. So that's the thing about it. So we have this OpenAI.api key now. So now we have configured this. Now we can start working on building this Streamlit app. So this is configuring Streamlit page settings. Okay, so here I'll say st.set page config. So here we are going to configure our page with page title, and so page, let's call this as GPT-4o chat, and then we can have a page icon. So page icon, you can copy and paste a emoji. So I'll just go to Google and search like chat emoji. So you can kind of copy any emojis from this Emojipedia. So I'll just copy this chat thing. So I'll copy and paste it here. And next is layout. Let's understand what all these things will do. The layout that I'm going to use is centered. Okay, so these are the things. Now let's open our the Streamlit app that I've already showed you. So here you're seeing this, right? GPT-40 chat. This is the page title and this is the page icon. So these two things are set up here. So we have this GPT-40 chat and this icon. And then you have this entire thing in the center of the page, right? So this is what this page layout does, layout of center. You have another option and that's called as wide, where your entire content of the screen is like present in a wider space in this screen. So you can also try that out, but these are all the two options. So that's the purpose of setting up this page config. So the next thing that we are going to do is initialize your chat. So I'll say initialize chat session in Streamlit if not already present. Let's understand this. So Streamlit by default won't maintain any sessions in this case, right? So when you ask a question, it gives you an answer. When you ask another question and run it, it won't retain this memory. So in order to kind of work around this, we are going to maintain session states. So that's the purpose of this. So here I'll say if chat history not in st dot session state, I'm going to say st dot session state dot chat history is equal to a empty list. Let's understand this. So st is nothing but your Streamlit library, right? And within this we have this class or function kind of thing called a session state. So within the session state, we will maintain all the sessions and the states of our web page. In this case, the purpose of this is to maintain the chat history. So what this particular if condition will do is this runs, or this is applicable when your application or your web page runs for the first time. So it will look into this Streamlit session state. If it checks if this key called as chat history is there, so when your web app starts for the first time, your chat history won't be there. This key value pair of chat history won't be there. So there we are going to create a key value pair in the session state called as chat history, and the value we are going to pass to it is a empty list. So as I said, as this is applicable only when this loads for the first time, right? So even when you refresh this, that's like a new session state. So when it initializes, you are just going to create initialization thing called a session state of chat history, and then once you ask this question and it kind of gives you the answer, all this will be stored in this chat history. So that's the purpose of this. So all you have to remember here is this is to initialize your chat, and when initializing this, we are going to create this key value pair of chat history and put a value of empty list there. So next is we can just give a name for our Streamlit page. So I'll say this is for Streamlit page title, and I can say st.title. This is a simple thing, so nothing complex. So I can say GPT-40 chatbot. Okay, here if you want, you can also again copy and paste an emoji like this. So again I can search it, robot emoji, and I can just copy it from here. So you can use any emojis, or you can write without any emojis as well. So like nothing important about it. So I'll just put a robot emoji here. So we have this Streamlit page title. So next we have to the next part is like displaying the chat history and how we can get a prompt from the user. So the next thing is displaying this history and how you can create the prompt input field here. So here I'll say display chat history for message in st.session state dot chat history with st dot chat message rule, and then st dot markdown message content. Okay, so let's understand this. So this for loop, so this is used to display your chat history. So in this case, if we see this, right, the first question that I have is what is machine learning, and I'm getting a response, and then I've asked a question of short answer. So when I ask this question, the previous message and the previous question shouldn't go away, right? So what we are doing is all this will be stored in the session state in the key value pair of chat history. So I'm using a for loop to iterate over this chat history and display all the questions and messages. So when I say for message in session state of chat history, message will contain two aspects. One is a role and the other one is a content. Role will tell the, tell the Streamlit interface, or it basically, role contains whether it's a user message or it's a assistant message. User message is what we are giving here, and the assistant message is what we are getting here. So this is used to say that if the tag or the role of the message is user, so this is going to be printed with this particular icon and in this way. And if the message role is assistant, it's going to put it with this particular emoji, and the answer will be in this way. So basically your message contains two parts. One is a role and the other one is content. Content is the actual content that we have. In this case, the role will be user and the content will be what is machine learning. In this case, the role will be assistant and the content will be this entire thing. So all these things are stored in our chat history. So our chat history basically contains this message, and each message will have a role and content. And using this for loop, we are printing and showing this all the previous conversation in the Streamlit web app. So that's the purpose. So when I ask another question, so all the previous chat history are displayed using a for loop. So that's the purpose of this particular for loop. So now and then we are just displaying this. So when I say chat message of role, it's kind of representing this role, so that it's like properly tagged. And then we have this st.markdown message content. So that is this content thing. So the content is displayed using st.markdown format. So it's like a markdown container that's present in Streamlit. So now we can create this prompt input field for the user. So here I'll say input field for user's message. So here I can say user prompt. Let's create a variable called as user prompt, and this will store the question that's asked by the user. And for this we can say st.chat input, and here we can write something like ask GPT-4o or anything. You can give anything, but let's use this. So this st.chat input basically creates this input field with this send button and so on, and you can have like some placeholder like this. So ask GPT-4o is kind of a line that we have, right? So that's what is kind of given here. So chat input creates this input users input field, and you have this message as ask GPT-4o or something like that here. So you can give anything. So when the user asks a question, so that question or that prompt is stored in the variable called as user prompt. So now I'm going to say if user prompt, that means, let me put this in another line. If user prompt, that means if the user has given a prompt, if they have sent a prompt, now what we have to do is we have to pass the entire chat history and the question that the user asked to the model, get a response from the model and display it here. So those are the remaining aspects of this code. So here I'll say add users message to chat and display it. So when a user asks a question, right? So if I kind of go here and ask a question, write code to train a model with TensorFlow, so that question will be displayed here. Maybe I'll show this, or I'll say what is deep learning. So this question is displayed here, right? So that's what we are going to do now. So I'll say st.chat message user. So this is the question asked by the user. So I'm going to say dot markdown user prompt. So this st.chat message of dot markdown is what is given here. So when I asked what is deep learning, so it's kind of displayed here, right? So this is done by using this st.chat message of user markdown, and then we get a response over here, and we have this here, right? So that's about it. Now we have to add this prompt to the chat history, and we will pass this entire chat history to the model because it has to look at the previous conversation and respond based on that. So I'll say st.session_state dot chat history. So I'm going to plug in this user input to the previous chat history that we have. I'll say dot append because the chat history is basically a list which we have initiated, which is a list, right, which is an empty list. So dot append, and we have to append this as role, as user, and content is going to be the user prompt, the user question asked by the user. So it shouldn't be in code as it is a variable. Okay, so this is how all the each element of the list would be. So previously if you kind of look at this, right, the first answer that we got, so within this list that we have created in the chat history, we will have a dictionary with two key value pairs. So one is a role, user, and the content will be the question asked. And then we have this again in the chat history, we'll have the role as assistant, and the content will be the answer given by the assistant. So you would have this for all the messages, and to that we are adding another line, which is this role of user and the prompt, the question that's asked by the user. Now we have to invoke the GPT-4o API and get a response out of this. So this is send users message to GPT-4o and get a response. So here I'll say response is equal to OpenAI dot chat dot completion. So it's going to act as a chat completion thing because it has like a previous conversation and it has to complete it where the user is asking some questions. So here I'll say create. So we are going to create this chat completion method and say here we can pass the models, like you can pass GPT 3.5 or you can pass GPT 4 or any model of your choice. So I'll say model is equal to GPT-4o. So if you want GPT-4, just say GPT-4 or GPT 3.5 turbo or GPT-4 turbo, any different models. So what I've noticed is that if you don't have a payment method in your OpenAI site, right, so the API key is not working, so it's not able to access GPT-4o or GPT-4. If you are accessing GPT 3.5, then it's working without a payment option. So you can try adding a payment option, a card detail. So if you can't do that, you can maybe try this code with GPT 3.5 turbo. It's going to work the same way as this is working, only the questions or the responses quality may change. But if you want to understand the code without giving any payment option, just go with GPT 3.5. So we have this GPT-4o and we have to structure the payload. So I'll put a comma here and and call this messages. So this OpenAI chat completion thing takes in two parameters. One is the model and the messages that we need to pass. So here we are going to pass the chat history where we have already added the user prompt. But along with this, we need to kind of tell the model what's the role that it's going to play. So this I've explained in my previous video where I've explained you how you can use this GPT-4o API. So here we kind of open a list and say create a dictionary, and the key is role and the role will be system, and then the content for this would be you are a helpful assistant. Okay, so this is like setting the context for the model. So here we are going to say that you are a helpful assistant and this is my chat history and the user has asked a question. Now give a response for this particular question. So this is how this would work. So I'll put a comma and say asterisk st.session_state dot chat history. Okay, so when I put this asterisk, it basically unpacks all the elements of this list and basically gives this as like separate values. So as I said, the chat history basically contains different number of dictionaries where it has this role and content. So the chat history in this case would contain this what is machine learning as the first content, and then the role would be user, and the next value or the next dictionary would be assistant, and the content will be here. So we are unpacking all these things. and passing this to this messages model. So before that we have to set the context for the model saying that you are a helpful assistant. So now this looks at this system role of system, which basically says the model how it should behave, and the chat history. And this chat history also contains a user prompt, as we have appended this to the chat history. So once we send this, it will look at the previous conversation, and it will also look at the user prompt, the new question that they have asked, and it will give a response. And that response is stored in this variable called as response. Okay, and now we have to, I mean, it's kind of like a different data format, so it will have this choice messages and so on. So we have to unpack only that text content. So for that you can use a variable called as assistant response. So we are going to extract only the text content from this response. So is equal to response, the one that we have got from the model, dot choices. This also we have discussed in the previous video, like the structure of this response. So you have this message dot content. So when you use this, it will extract only the content or the text output or answer for this user prompt, and we are going to store that in the variable called as assistant response. So now I'll say st dot session state dot chat history dot append. So what I'm doing here is, to this chat history I'm adding the response that I got from the model. So dot append, it should be a dictionary where it contains two key value pairs. One is the role. So this message came from the model, right? So let's call this as assistant, and the content will be the assistant's response. So this is how we have to tag this. User's question should be tagged with the role of user, right, like this. And the assistant's response should be tagged with the role of assistant, and we have this content, the response is present here. So now we have to display this message. So for displaying this, I can say display GPT-4 voice response, and I'll say with st dot chat message. So this is going to be the assistant message, because it has to give this robot kind of icon. So I'm going to say chat message of assistant and st dot markdown. So it's a markdown container, and within this I'm going to paste the assistant response. So this is how this would work. Okay, so the entire idea here is, so first we create a session state, an empty list. So to that we are going to add this system message of you are a helpful assistant, and we add this user prompt to this particular chat history and send it to the model. So the model will look at this context of you are a helpful assistant, so that's going to behave as a helpful assistant, and then to look at this user prompt and give the response for this using this chat completion thing. And this process goes on. So when it runs for the next time, so this thing won't run, this won't, because this will happen only when chat history is not there. But when you have asked the question for the first time, it has already created this chat history, so it's not going to initiate it again, so it won't create a empty list again. So your chat history now contains the first question as well as the message. To that we are again adding this user prompt, and then like getting a response to this, and this process kind of goes on, and finally we kind of display the question as well as the response using this assistant icon and the markdown container. So this is how this code works. So I'll now go to my previous version that I've showed you. I'll close this. I'll close this thing as well. Now we can start our application. So make sure that you have ran like pip install. So you should do this pip install -r requirements.txt. So look that we are in this GPT forward chat May 17. So we are not in src directory. So we are in the project directory. So run this pip install -r requirements.txt. And once the code aspect is done, once you have your config.json thing, all those things, you can run your Streamlit app by saying Streamlit run. So my main.py file is the one that contains the Streamlit code, but it's present in the directory called as src. So I have to say src/main.py. Or the other thing I can do is go to this, navigate to this directory using cd-src and say streamlit run main.py. But I want to stay in this project directory, so I'm saying streamlit run src/main.py and run this. So this will give you this local URL. So you can click this, or like this will automatically open a page in your browser. So here you can go ahead and ask a question of, let's say, what is machine learning? And let's send this. So here we would get a response from the model. So this takes a few seconds for the model. So once it kind of gives the response, so it's kind of displayed in the markdown format. Yeah, as you can see here. So what's basically happening here is when we refresh this, so the chat history is not there. So this will instantiate this using this particular line of code. And then when we type in a question and it send, so it's going to display that question using this. So we have this chat message of user, and then we are using a markdown to display it, and then we have this st.session state, adding that user prompt to the chat history and asking the model for a response. So this process goes on. So when I put this as short answer, give me a short answer, right? So it's similar to this. So this what is machine learning, and this content is passed to the chat history, and this question is also passed on to the chat history and sent to the model with the format of a role of whether it's a user question or the assistant response, and then the model would give a response which we are going to display it over here. So once we get a response, we are saving it here and displaying it using with st.chat message of assistant dot markdown. St is nothing but streamlit dot markdown assistant response. So let's put this as shorter answer, so we would get a shorter response from this. So this is how you can use a GPT-4o model in order to create a chatbot. So I hope that this is helpful to you. So please practice this code and try to understand this. And in the upcoming videos, let's work on this by creating more applications to this. Like let's say the widely used RAG, the retrieval augmented generation thing, and how you can deploy this LLMs in a production ready way, and so many things. I have some ideas. I'll probably make videos on these topics, and also maybe try and use Llama 2 chat or Llama 3 models. So these are the things I'm planning. So if you want to learn any other specific things, you can let me know as well. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. In this video, let's build a translator application using Streamlit, where we will be using OpenAI's GPT-4o model for translation. So this model supports more than 50 languages, and the user can select an input and output language of their choice and do the translation. So this is how our end translator application will look like. So this is the Streamlit user interface that we will build. So the user will select an input language and the output language of their choice. So let's say that we have input as English and the output language as French, and here we can type in some text saying, like, let's say hello world. So once we have done that, so we can click this translate button, and this will translate the text and give it here. Okay, so we can also take like a longer text and copy this, paste it over here, and click the translate button. So we would see this output here, and the response is also pretty fast. So here we are calling the OpenAI API to access the GPT-4o model. So this is what we are going to build. Okay, so this is the end result of what we are going to do. And now let's get started with the development process. So I have my PyCharm ready. So here I've created a project with Python 3.10, but you can try it with the later versions of the Python as well. So here I have this .venv. This is my virtual environment directory where all the libraries will be installed. So I'm going to create like a more standard code structure. So in this project directory, I'm going to create a folder. So right click in this project directory and create a directory. So I'm going to name this as src, which stands for source code. And I've already made a video on how you can create these environments in PyCharm and so on. So if you're not familiar with that, you can check that out. And I'm going to create another file within this project directory and name this as requirements.txt, where I'm going to add all the libraries that I want. Okay. And within this src, I'm going to create three other things. So first is the main.py file. So this file contains the code for our Streamlit application. And then let's create another Python file and name this as translator utils. Translator underscore utils. So in this Python file, I'm going to build the code that will call the OpenAI API and get the response. So you can add this in the main.py file, but by doing this, you would have like a more modular code. So the user interface code is in one Python file, and the the code that calls the API and other backend stuff is in another Python file. So that's why we are doing this. And finally, we need this config.json file. So I'll create a file and call this as config.json, where we are going to store our OpenAI API key. So these are the three files that we need. So in the first step, let's open the requirements.txt. So see that in the project directory we have src and requirements, and within src we have all these code cells. So in this requirements.txt, first I'll mention the libraries that I want. So first let's mention Streamlit, and then let's add Langchain, and then Langchain OpenAI to access the GPT-4o model. Okay, so these are the three libraries that I need, and I'll mention the latest library version that I have like while making this particular video. So for Streamlit it's 1.35.0, and for Langchain it's 0.2.1, and Langchain OpenAI it's 0.1.7. So these are the versions that I need. So I'll save this, and then I'll open my terminal and run this pip install. So I'll say pip install -r requirements.txt. So this pip install -r requirements.txt. So this command looks into this requirements.txt file and installs all the libraries with the specified version. So that's what this command will do, and let's run this. As you can see, so the libraries are getting installed. So we have this Streamlit, Langchain, and Langchain OpenAI, and all the other dependent libraries for these three libraries will be installed. So the next thing that we can do is get the API key. So how this would work is we would have this user interface built in Streamlit. So the user selects this and type in some text. So all these are done in Streamlit. So after that, once they click this translate, we are going to invoke the OpenAI API. So for that, we need the API key. So in order to get that, you can go to the openai.com. So I'll search openai.com, and here you have this products, right? So within this product, go to this API login. So this will ask you to log in to your account if you have not like logged in. So I've already logged into my account, and the thing about this GPT-4o model is that if you don't have a payment method, then it won't be like applicable to you. So if you can add your card details and sign up here. If not, you can just try it with the other models for now. Let's say GPT 3.5, where they give this standard $5 credit per month. So you can go with that instead of adding any payment method. So if you want to try GPT 4 and 4.40, so for me it kind of requested me to add this payment method. So that's something you can think about. So in this OpenAI thing, so we have this ChatGPT and API. So I'm going to go into this API, and in the left navigation bar we have this API key. So here we can create a new API key. So I'll delete the API key that I already had, and I'll create a new one. So I'll give this create new secret key, and I'll name this Translator application, and this is the default project. So if you have other projects created, you can mention that, and I'll create the secret key. So this will display the secret key that I've generated. So I have copied it, and now let's come back to our code. So as you can see, the libraries are also installed. So now I'll open this config.json, and I'm going to create a key value pair. So the key would be OpenAI API key, and the value for this would be the API key that we have generated. So save this. As you can see, this is just like a dictionary, a JSON object. So we have this OpenAI API key and the key that we have generated. Okay. So now I'll close this and close the requirements.txt as well. Let's clear this, and now let's get started with building the Streamlit code. First, let's import the libraries that we need. So I'll import Streamlit as st. Now let's set the page configuration. So I'll say st.pageconfig, and here we are going to mention some parameters like page title. So page title, let's name this as translator.ai. So you can give any name. So I'll just go with translator.ai. And the next parameter that we need to set is page icon. So page icon, we can like copy some emojis from Emojipedia. So I have this Japanese symbol. So I'll just copy this Japanese symbol and put it over here. Again, you can choose any symbol of your choice. And then we have to set the layout. So layout is equal to center. So there are like two options that you can give for this layout. So one is centered and the other one is white. So when you give the center, all the content that you see in the Streamlit application will be mainly focused in this like center part. As you can see, if it's white, like it occupies like more space in the sides. So that's about this layout thing. So these are the page configuration. So this page title of Translator AI, page icon of this emoji are like what you are seeing here. So the emoji and the translator.ai in this previous version that I'm showing you. So the next step is like setting the page title. So this part would be Streamlit page title. So st.title, and we can name this like with the same symbol. We can name this as translator application or translator app GPT-4o. So again, you can give any name of your choice. So the next thing that we are going to set is set this input language and this drop down in the left side and the output language and drop down on the right side. So for this we can use streamlit.columns. So I'm going to create two columns as I need only the left and right part. So if you need three columns, if you want to put something in the middle, you can create three columns as well. So I'll say column 1 and column 2 is equal to st.columns, and within the parenthesis mention the number of columns that you're creating, the number of variables that you add. So now I can say with column 1. So when I put this with column 1, all the thing that I'm building here will be represented in this left side, and with column 2 will have everything on the right side. So first we need to create a list that holds the list of languages that we are seeing here. So for now, let's just take like a few examples or like few languages, but later when you're working on, you can increase the number of languages that you have, or you can also get it through some APIs or some Python libraries. So that's also possible. So here I'll create a list and call this as input languages list, and let's say this input languages list as languages like English. So this is something the user is going to select, and let's say we have this French, German, Latin, so the GPT model also supports like Indian languages as well. So you can choose something like that as well if your like target audience is from India or something. So we have, let's say, Hindi, Tamil, Telugu, or like other regional languages as well. So I'll choose like a few of these. And finally, maybe let's have Marathi. Okay, so you can, as I said, you can add like more languages as well. So the next thing is we have to create a drop down and pass this list to the drop down. So the user is going to see the list that we are seeing over here. So that will be the next step. So here I'll say input language. So this is the variable that will hold the language that the user has selected. So this input language is equal to st.select box. And here let's say label. So label is equal to input language. So this is what we are going to mention in this top as input language. So input language, and in options parameter we have to pass the list that we have created, input languages list. Next thing is with column 2 I'm going to create another list. So I'll call this as output languages list. So for this output languages list, I'll say I'll create a list, and for X in input languages list, okay, so for X in input languages list, if X is not equal to input language. So let's understand what this does. So in this code, right, so we have this input language as English and the output language as French. When the user selects French, the output language shouldn't be French, so it should change, right? So if they have, let's say, selected German, so German shouldn't be present in the output language, as you can see. So the original order is English, French, German. So if German is selected here, so German should disappear from here. If, let's say, French is selected from here, then German will appear and French will be removed from this. So we have to implement this. So for that, what I'm doing is I'm going to create a list from this input languages list, and take everything that is like except this input language. I'm going to choose everything. So when the user is selecting French, we will take this original list of this input list and delete that French alone. If the user is selecting this Latin, we will take this original list and remove Latin alone. So that's what we are doing here. So when I say for X in input languages list, if X is not equal to input language, so this is basically a if condition and for loop. So using this, we are creating a list. This just like takes the input languages list, takes all the elements except for the element that is the input language. So as I said, if French is selected, French will be removed. If let's say Hindi is selected, Hindi will be removed in the output language. So it's for that purpose. And now we can just do the same thing of output language, so like similar way that we have done over here. So here I'll say output language is equal to same st.select box. So in this label, instead of this input, we can say output language, and options can be output languages list. So what we have created over here. So let's name this output languages list. So the next thing that we need to create is a text box for the user to type in some text. So here, so I'll come out of this with column 1 and column 2. So that means I'm coming out of this left and right column. So it's going to now present in like in the entire layout of my application. So I've came out of this column 1 and column 2 and say input text. So this is where the user is going to give you the input text. So the input text is equal to st.text area. And so within this, we can say type the text to be translated. Okay, so this is the label that we are seeing over here. So this is like pretty much the layout kind of thing that we are creating. So we have this column 1 and column 2 layout where we have this input language and output language, and we have created a text box where the user can type in some text. So now we have to create this translate button. So once the user has click this translate button, we have to invoke the API. So that step of invoking the API, let's do in a different file which we have created as translator utils, right? So I'll come back to the code. I'll open my project directory, go to the src folder and open this translator utils. So this is where we will be having the code. So first I'll import OS and I'll import JSON, and from Langchain OpenAI import chat OpenAI. So this is to load the LLM, which is GPT-4o in this case. And from Langchain underscore core dot prompts, I'm going to import chat template. So chat prompt template. Okay. So now let's understand the purpose of this. So first we have this OS in order to direct the thing to the particular directory, and JSON in order to read the config.json file that we have over here that has the API key, and then chat OpenAI in order to load the LLM GPT-4o, and then chat prompt template to set a template saying that it's going to work as a translator. So those are the required dependencies. So now we have to configure our language, this Langchain library with the OpenAI key. So this is to configure OpenAI API key. So for this, I'll say working directory is equal to os.path.dir name, os.path.absolute path, and here I'm going to say file. So this is a very key thing, and I'll explain you what's the purpose of this in a minute. So here I'll say config data. So here I'm going to load my configuration file. So it's json.load open, and within this we have to pass the path. So path, I'll say f quotes working directory and config.json. Okay, so let's understand this code. So the translator utils and the config.json file are in the same directory. So it should work if we just say config.json. But when you run this on a Streamlit application, right? So what it's going to do is, so the application will basically run from the place where you have installed Python. So this will in more cases be like, let's say you have this users in your system, and in my PC it would be like users sid, and within that Python will be installed. So that's the location on which this particular Streamlit application will run. So that will be the working directory. So now we have to point it to the config.json, which is in a different directory when it runs in a Streamlit application. So I'm going to say, or instead of copying this like entire path, so I can do this. I can copy this absolute path and paste it over here where I'm mentioning this path. So it's like the entire path of this config.json file. So if I share this code with someone else, right, so then they have to change this particular line of code with their directory where they've saved this config.json. So in order to avoid that, we are using this particular piece of code which is going to get the path of the file. So when I say this file, it's going to get the path of this translator underscore utils.py file. So this is what happens here. So we pass this special parameter called as file, which will mention this translator utils file. So wherever this file is located, right? So it will take that directory and pass that to this variable called as working directory. So now we can attach this config.json file to this working directory, which will be the exact path that we are seeing over here. Okay, so this is how this happens. So instead of mentioning this directly, so we are saying that get this directory from your current file and then add it to the config.json file. So when you do this json.load open, so this will read the config.json file that we have and convert it to a dictionary and store it in the variable called as config underscore data. So now from this dictionary that we have created of OpenAI API key and this value, so we are going to extract this API key and store it in the environment variable. So that's the next step, and that's why we have imported the OS library. So here I'm going to say OpenAI underscore API key is equal to config data. So the key is the same name. Okay, so that we have over here in this config file. So I'll copy this key and let's paste it over here. So as you can see, OpenAI API key. So now this key is stored in this variable called as OpenAI API key. Now we are going to store that in our environment variables. So I'll say os.environ, and in the square brackets I'm going to create a environment variable and call this as OpenAI API key. So this name shouldn't change. So this OpenAI API key with all the uppercase letters, this shouldn't change. You can name this anything you want, or you can even name this variable anything you want, as well as like the key that you have over here. But when you're storing this in your environment variable, this should be the exact name. This is because when you load the LLM model from the Langchain, it will look for this particular key in your environment variable. So this shouldn't change. And now I'm going to pass the API key that we have retrieved here, which is stored in this particular variable. So I'll paste it over here. So now this does the configuration. So first we are getting the working directory of this file, attaching it to this path of config.json, reading the JSON to a dictionary, storing it here, and then passing the key to this variable called as OpenAI API key and storing that in the environment variable of OpenAI API key. So now let's load the model. So I'll say LLM. So let's call this model LLM, and LLM is equal to chat OpenAI, which we have imported over here. And here I'll say the model that we are going to use is GPT-4o. So GPT-4o. So if you want to use GPT 3.5 turbo, you can use that as well. So GPT-4o, and temperature is equal to 0. So when the temperature value is closer to 0, it's going to give you less random output. If it's like closer to 1, if it's a large number, right? So this value ranges from 0 to 1. So if it's closer to 1, then it's going to give like different response, or like kind of different response each time you ask a particular question. So you can also explore like the other parameters that you have for this. So that is the next step. So now we are going to create a function that can get the input language, output language that the user has kind of given, as you can see here. So the user will give an input language, output language, and the text, right? So we are going to pass that to a function here. So here I'll create a function and name this as translate. So define translate, and the first parameter will be input language, second parameter will be output language, and next will be the input text, the exact text that they are typing in. So input text. So when we call this function, we are kind of creating this prompt template. So this prompt is equal to chat prompt template, which we have imported. and dot from messages. So this we have already seen in the previous video of how we can access the GPT-4o model from Langchain. So there I've explained to you about this chat prompt templates. So from messages, open this parenthesis and then create a list, and within that list we have to create a maybe a tuple. So here let's say system. So system is like kind of setting the context for the LLM. So here I'm going to say you are a helpful assistant that translates input language. So put this input language within curly braces because we have to replace it later to output language. But make sure that you don't have this if. So this kind of formatting shouldn't happen here. So you are a helpful assistant that translate input language to output language. Okay, let's just put a dot over here. So this system message basically sets up the context as I said. So here you can have like different context, like you are a helpful assistant that completes the chat or answer your question or something like that. So here the context is just building a translator. So I'm asking it to be an assistant that translates one language to another. So next I'll do this. Next will be the human message. Human. And here put another curly braces and put your input. So here we are going to pass our input text. So this input is nothing but the input text that we are going to pass in later. So this is our prompt templates. Now I'll create a chain. So this is what we have seen in the previous video, chaining the prompt with the LLM. So I'll say prompt and use a vertical bar and say LLM. Okay. So now I'll say response is equal to chain.invoke, and then we have to pass in a dictionary. So in this dictionary I'm going to say input language will be input language. Next is output language. So that will be my output language as well. And finally the input text. So this input that we have mentioned over here. So the input is going to be input text. Let's understand this. So here we have set a template, right? So you are a helpful assistant that translates input language to output language. So we use this chat prompt templates and store this prompt. Now we are chaining this LLM and creating this variable called as chain. So this is the chain that we are creating, and in the response I'm invoking this. So while invoking this, it will invoke the LLM and it will replace these factors, the input language, output language, and input, whatever is present in the curly braces. So that will replace those values with the dictionary that we have given here. So the input language will be replaced by this variable, which is the input language that the user is selecting, and the output language will be replaced by this parameter. Again, the output language the user is selecting, and the text given by the user is replaced here. So this, let's say if it's English to French, so this will be replaced with English, this will be replaced with French, and let's say the text is hello world, so this input will be replaced with hello world. So this is the dictionary that we are passing. So that is all. So this chain dot invoke with this dictionary will give you the response of converting one language to another for that text, and you can say response.text, response.content. So in this response.content only the final output will be kind of stored in this AI message. So here we are setting up the context for the LLM, saying that this is the system, how the system has to perform or how it should behave, and then the human message, the text itself, and then we are storing it in this response, and now we can return this response.content. Okay, so that is all. So I'll copy and paste it over here. So now we have to call this function translate from this translator utils in our Streamlit app. So here I'm going to say after a Streamlit, let's import from translator utils. As you can see here, import translate. So this is the function that we are importing, and after the user has given the input text, right, so we have to create a button as we have discussed earlier. So here I'll say if st.button and let's name this button as translate. Let's create a variable as translated text. Okay, so the translated text will be translate the function that we have imported over here, and within that pass the input language, output language, and the text that the user has given. So the three parameters it's going to need. So I'll just copy this because all these are like the same names that we have in the Streamlit app as well. So I'll copy and paste it over here. So we have to pass input text, output text, as well as the input language, output language, and the input text. Oh, okay, I have to name this as output language, not input language, this one. So this is stored here. So how this would work is, and finally we can use this st.success, which will display a green, text box where the output will be displayed. So let's put this translated text over here. Okay, so we have this, let's understand the code. So first we are setting up the page configuration, Streamlit app titles, and the left should be column 1 where we are displaying the input languages. Output languages should display all the languages except the one the user has selected. So that's the second column, and then the input text box where the user is going to type in something. And finally we have this translate button that will call this function, which is in turn invoking this API with this chat prompt templates and all those values and so on. And finally it's returning the result that is stored in this translated text, which will be displayed using this st.success. So now let's run this. So I'll open the other project that I was showing you the demo. So I'll close this and close this web page as well. Now let's run this app that we have created right now. So I'll open the terminal. So in order to run this, you have to say streamlit run src/main.py. So pay attention to the directory. So now this is in the translator app project directory. So my main.py file is my streamlit app. So I have to say streamlit run src, which is the folder dot /main.py. Or instead what you can do is you can go to that particular directory, cd space src, and then you can just say streamlit run, you can do something like this, streamlit run main.py. So this is also something that you can do. So that's like of your choice. So pay attention to the directory. In order to come back, you can do cd double dot. Okay, I'll clear this and say streamlit run src/main.py. So this will open my Streamlit app. So here you can see this translator.ai and the emojis, the center layout. And here let's say we choose English and the output language to be French and say hello world. And translate. Let's make sure if it's working. So it's okay. So the temperature spelling is wrong. So I'll come back here and TU. Okay. So let's stop this application and rerun this. So you can try with other languages as well. So now we are seeing the output. So similarly, I'll just go and copy some other text from this thing. So preparing food or something. So you can like copy some text, paste it over here, and ask the model to give a response. So I mean, don't know French, but if someone knows, they can probably validate. So you can also choose like some other languages as well. So probably like I'll choose Tamil because I know it. So I can do this translate and check if the output is proper and so on. So this is how you can build this simple translator application with this thing of GPT-4o API and the Streamlit user interface. Let's just do a quick recap. So the first thing that you need is like all the requirements.txt, the libraries that we need, which is Streamlit, Langchain, and Langchain OpenAI, and the OpenAI API key, which is like really important. And then we are building the Streamlit user interface with all the layouts, page titles, and the layout of left and right of input and output languages. As I said, you can like include more languages to this as well, so that like it's kind of broader. So the user selects the input language and the output language and the text area, and they click the button to get the output from the response. And this translator utils, we have created a function called as translate that will take in the input parameters as input language, output language, and input text and do this translation. Okay, so the next step that you can do is probably deploy this in a Streamlit cloud and give it out for public use. Like some other people can test it out. And the other option that you can do is like, if you don't want your API key to be used, you can just have like another field here where the user can paste in their API key, so our code is going to use their API key to get the response. So you can try that as well, but for now we are just like giving that here as well. So this is how it works. So I hope everyone is clear until this point, and please try this out, and it will be like really interesting, and you can build a lot of things on top of this as well. So let's see in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. Welcome to this complete Google Gemini AI course, where in this course we'll be using Google's latest LLM Gemini to build this interesting application where we have chatbot, image captioning system, text embeddings, and also a question answering model. So this is what we are going to build in this course. So we will dive deeper into each of these sections, and we can see how we can use the different versions of the Gemini Pro model in order to build this application. So first we have a chatbot, as you can see here, where I've asked this question of why did Thanos do what he did. So if you have seen Avengers movie, you would probably know who Thanos is, and we have the question for this. So it kind of explains like what is the reason for Thanos in order to do that snap and all those things. And I also asked a tricky question of about was he right about it. So this is just not like a question answering system, so it also takes in the previous conversation it had, and it kind of gives the response based on that. So here I didn't mention Thanos and all that, so this is just like a conversation. So it picks up like all the conversation that we have over here, and it responds that no, Thanos was not right about it. So this is like the first page that we will build. And then we have this image captioning system, where once you kind of upload an image, we will be using Google's Gemini Pro vision model in order to get a caption for this image. So this is like a kind of a street with all the lights and so on, and it's kind of like written in Chinese over here. So I'll show you the original image later. So it says that it is a busy street in Hong Kong at night and so on. So this is like the second page of this application that we will be building. And then we have this text embeddings, where if you write something or you put a paragraph over here, so it would give you the vector embeddings of that particular text. So here we are just displaying it, but there are like more applications to this, like document search and so on, that probably we will discuss in a later video. And then we have this ask me anything section, where we can just ask a question and click this button to get a response for that. So this is the application that we are going to build with Python and Streamlit. And once you are kind of done with this video, you will be well versed in how you can use Gemini Pro API and all those things. So I'll start from scratch of how you can set up your environment in PyCharm and how you can get these API keys and build this application. Okay, so let's get started. So I would suggest you to use PyCharm or maybe a VS Code, but again, you can use other IDEs like Spider, but PyCharm is like better with the terminals and other options. Okay, so let's say that you have installed PyCharm. What you can do is open it and go to this new project section. So I mean, if you have already worked on a project, so you would probably have the folder here, but if you are working or if you are opening it for the first time, you will see this option of new project. So you can click that, and you need to kind of specify the folder on which you need to maintain this kind of like what we can say. So you can maintain this project and all the libraries specific for this particular project, so that we can store in a particular folder. So here I'm choosing a folder called as complete Gemini AI course, and then you can name a project. Again, this would create like a subfolder for this. So I'll call this as Gemini AI complete course. So the reason we are kind of creating this is like, let's say you are working on another project and that needs like a different version of a Streamlit library, right? So let's say that this course requires a different version, right? So in order to segregate these, we can just create a virtual environment for individual projects, which is like a much standard way to do this. So I've given the location and also the subfolder for this, and you can give this custom environment. So you can use your Conda Python, but I would suggest you to use this custom environment. So for base Python, right, if you haven't installed it previously, it will kind of give you an option to download it. So you can download it, and for all the other projects that you are using, you can just choose this. So give this custom environment, generate new, and you also have this virtual env. So you can also choose other things, but I'm going with this virtual env, and base Python version is this, or you can kind of go with an updated version as well. And we have the location of this libraries as .venv. So I'm creating this project folder called as Gemini AI course, AI complete course. Okay, so you can see .venv. So this is where all my libraries will be installed. Now you can close this, and within this particular folder, right, you can go ahead and create like all the files that you need, and let's do that. So here you can just do a right click and create a new Python file. So let's call this main.py file. So this is again a standard naming convention of using this main.py as the name, and this is where we will build like all the Streamlit code and so on. And the other important thing that we would need is a requirements.txt file where we are going to specify all the Python libraries that we need. So I'll say requirements.txt, and here I'll give the latest version of all these libraries. So first is Google Generative AI. So we have this. So let's say that the version that we need is 0.4.0. So this is the latest version by the time that I'm doing this, but you can update it if you want. And then I want Pillow in order to do some image processing for our image captioning page. So here I'll call this as 10.2.0. We will also be discussing how we can deploy this on Streamlit Cloud so that you can share it as a public cap. So that is like another thing about this course. And you also have this Streamlit library that we need, which is equal to 1.31.1. And finally we need Streamlit option menu. So we need this in order to create those navigation pages for these different kind of applications. I'll give this 0.3.2. So these are the things that we need. So first you can create this requirements.txt and I'll also give the GitHub repository for this code, so you can kind of refer that, so you can copy the files, get the files, and do the similar thing. So once we have this requirements, we need to install it. So for that you can give this terminal section that you have here and kind of install it. So here if you see, we are already in the project directory, which is Gemini AI complete course. You can just do a ls in order to list the files. So we have main.py file and requirements.txt file. So here I'm going to say pip install -r requirements.txt. So this will install all the libraries with those specific versions that we have mentioned over here. So I'll run this. So this will kind of install all the dependent libraries for these packages as well. So that is like the first step. So next step is getting the API key for our Google Gemini Pro model. Okay, so for that go to Google. So I'll close this particular app, the previous one that we have created. So go to Google and search Google AI Studio. So if you search it, you will see this page called as Google AI Studio Quick Start Gemini API. So this is where we are going to get our API keys. And now kind of Google give this LLMs, Gemini LLM for like 60 requests per minute. Like there is a cap for this free version, so we can kind of use it for like a development. And there are also other LLMs like Llama 2, which is like open source given by Meta, and of course we have GPT 4 and other GPT versions by OpenAI, right? So in this video, let's go with Gemini as we know. So go to this Google AI Studio Quick Start, and in the next navigation bar, left navigation bar, you will see this option called as get an API key. So this is where we have to go, but make sure that you are already signed in. So once you signed in, go to this get an API key, and here you will see this button called as get an API key. So click that, and here we can generate our API key, which is like a combination of alphanumeric letters and so on. So here you need to kind of accept this. If you don't want to receive anything, you can just leave these two checkboxes and just give continue. So you can give create API key, create API key in new project, like if you don't have any. So this is completely free, so you don't have to worry about it. Okay, so this is my API key, so I'll copy this. You will also see this below once you like kind of come back to this. So I'll close this, and now I'll create a file called as config.json. So we can kind of write this kind of hard code it in the code, but it is not a standard way. The more standard way is to put it in a .env file and load it with like this .env package, and the other way would be to put this in a configuration file. So I'll create a file called as config.json. Again, you can also try putting it in a .env file also, but I'm just going with this approach. So this I'm going to say it's basically a JSON file, right? Just like dictionaries in Python. So here you have to create a key value pair of, I'll call this as Google API key, put a colon and paste your key within quotes. Okay, So this is my API key. So save this, and in this kind of file, we are going to load this API key and load the model that we have. So the different model that we have here are like, you can just go to this model section. So here go to this Gemini. So here we have like different models like Gemini Pro, Gemini Pro Vision, and embeddings and AQA. So this is like a question answering model and so on. So we have all these things. So we are going to try few of these models. So let's see how we can do that. So now I'll come back to my PyCharm. So main.py file is where we are going to create our Streamlit app. But I mean, we will also create like another file in order to load this Gemini models, get a response, so that our code is more modular. So I don't want to put like all this getting response, all these things in my main.py file. Only the code of my Streamlit app will be here, and all the other things will be in a separate file. Maybe I'll create another Python file and call this as Gemini utility. Okay, so in this main.py, the first things that we are going to do are just like build the outline for our Streamlit app. Okay, maybe I can close my API page. Okay, so here I'll say import. Let me close this. Streamlit as st. And there is another main thing of this working directory. So when you run a Streamlit app, right, with the Streamlit run command, the default working directory won't be this project directory. So it will be your user. Like, I mean, if you are in Windows, right, so you would have this users folder and you would have your name in a folder. So that will be the default working directory. So in our code, we need to specify this exact directory in order to access the files. Otherwise, it's going to throw you an error saying that the files are not present. So if you don't understand this, it's okay. I'll discuss this or I'll explain this to you in more detail once we face that issue. I'll also import OS library and I'll leave a space over here. So here we have this working directory, and this working directory is equal to os.path .dir name, which is the directory name. And here I'm going to say os.path dot absolute path, and within that I'll say file underscore. This is basically used in order to get the working directory here. So I can just kind of go here and copy the path, but I don't want that because I don't want to hard code this path, because if you run this file, right, in that case you need to replace this. So, but in case if you have this, right, this will automatically pick the path of this particular file. So that's what we are doing this. We are getting the absolute path of this main.py file here. So if you want, I can also print and show you this working directory. So no harm in that. I'll just run this. So you will see the output here. You can see, so this is like the path of this. So if you run this file, right, you will get the path of the directory that you are working on, so that we don't have to hard code anything. So that's about it. And then we can set the page configuration. So I'll say, can put this as setting up the page configuration. Okay, so here I'll say st dot set page config. So this is like what's the icon of the page should be, and like what's the logo should be, and so on. So we have this st dot set page config, and the first parameter I'm going to pass is page title. So let's call this as Gemini AI, and you can also put a page icon. For this page icon, like what I'll do is I can just go to emojis and like search some emojis that I want. I can just search Emojipedia. So here you can like, I mean, kind of get emojis that you want. So I'm just going with the brain emoji. So search it. Right. So once you click this, you will see this copy. I mean, you don't have to do that. It's just like it's better if we have this icons and so on. So that's why I'm doing it. But these are like not that critical. And then you have this layout. In this layout, you can give either centered or so we have this centered option and wide option. So I'm going with this centered so that your app kind of looks compact. You can also like try wide as well. So these are the other things. Now let's build the sidebar for this. So for that I need to import okay, so I need to put this as from Streamlit option menu, import just option menu. Okay, so here I can say with st.sidebar. So we are creating like the sidebar with the Streamlit package, and within that I'm going to create the pages. So for this you can create something called a selected. So once the user has selected the page, we pass that information here and use this option menu that we have imported, and here say Gemini AI. This is like the name. So once this is complete, right, so you will see how this navigation pages will look like. This is the name of this like page, and you also have these page names that you have seen, right? So for that I'll say chatbot. Next we have a image captioning thing, right? Image captioning. So this is the second page, and we have a embed text page, and finally we just like have a question answering thing. So once you ask a single question, it will just give you like an answer for that. So I'll call that ask me anything. And finally we have this menu icon to put an icon for all these pages. So first is like the icon for this page thing itself. So here I'll use this robot, and then we have the icons for the individual pages. So for this basically we are using the bootstrap icons. So if you want to use a different icon, right, so you don't have to use this emoji PDF for this. Just go to bootstrap icons, and once you go here, if you scroll below, you have this search bar. So here you can like search something you want. So let's say that you search question, it will give you these question marks and so on. So you just need to copy the name. So for example, right here we have this patch question fill, you need to put that over here. So here I'm going to first use this first maybe I can go and search and show it to you. So I'll search chat. So I'm going to use this chat dots fill, right? So I'll copy this name, paste it over here in code. So this is my first pages icon, so this should be corresponding. And then next I'll get image captioning. So for that you can just search image, and you can just choose an appropriate icon for this. So here I'm going to go with an image fill thing. And okay, the other two icons are embed text and ask me anything. So here I'll just go ahead and search for text. I'm just going to use this T thing, but I think I've seen another one. Okay, so I know the name for that. So that's text area. Again, you can use anything that you want. So I'll use this text area -T. And finally, we have this for this, ask me anything. I just want like a question mark. So for that, you can use a patch question fill. Okay, this is our sidebar. And by default, you can also mention like what's the page that should be kind of like selected. For that, use default index. So this default index, if you say 0, the first page will be selected. Okay, so now we can just check how our Streamlit app is looking like. So for that, if you run this, it kind of like won't show you the Streamlit app. So for that, you need to use this Streamlit run main.py. So make sure that you are in the project directory. So main.py file contains the code for our Streamlit app, and again just use the Streamlit run main.py, run this. This will automatically open your browser, or you can just click the localhost URL that you get. So again, this is still in localhost, so that means you can't send this to anyone yet, but later we will deploy this. Okay, so here we have this Gemini AI. If you see this brain symbol, and we have this Gemini AI, right? So these two things are the ones that we are setting up in this page config thing, Gemini AI, this brain symbol and so on. And then you have this Gemini AI name and the robot icon, right? Menu icon. So that's what you are seeing here. So robot icon, Gemini AI, and you have this chatbot, image captioning, embed text, and ask me anything. So all these are present here. Yeah, and you also have the icons for that. So this is how you can do this. So now we won't see anything because we haven't configured to display anything. So now once the user has like clicked a specific page, we will write the code in order to show like the corresponding things of our application. So you can just press Ctrl C in order to stop this Streamlit app. So I pressed Ctrl C. So now if you refresh this, it won't be available. So I'll come back to my code, and I'll say we just like need few functions for this, but before this I think we can go to the Gemini utility and kind of load these models. So for this we need to import the libraries such as Google Generative AI and other things. So for this Gemini utility, and again import this OS. We'll also import JSON, and from will import, this is for image captioning. Okay, let's not do that. So first let's just focus on the chatbot. So first again I'm going to kind of mention this working directory thing. Okay. This is again mainly used if you want to access the files that are being uploaded in Streamlit. So you need this working directory in that particular case. So the next thing is we need to load this API key and pass it to this Google Generative AI library. So I'll import that as well. So for that you can say import Google.generative AI as Gen AI, and then we need to load this config.json. For that you can use JSON library. So I'll say config data. So this is the variable that I'm creating, and I'll say I think we can first mention the path of this file. So I'll say config file path. So this is equal to we can use like this working directory, which is the folder, and then put the name of this file. So for that you can just say put a f so that the string is substituted within this parenthesis, and put a slash and use this config.json. So I'll say config.json and put working directory. So if you want to look what this config path is looking like, so you can just say that print config file path. So it will say like all my complete kind of path and the name of the file. So this is what we are accessing. Now I'll just delete this, and this is basically a dictionary. I mean, we are going to load this JSON file into a dictionary, right? For that you can just say json.load open and say the path of the file. So just config file path. Now we can create a variable for this key. Let's call this like API key. Call this as loading the API key that we got. So here I'll copy this name itself. I mean, you can use a different name, but I'll just go with the same name. Google API key is equal to config data. This is again a dictionary, right? So once you do this and print this Google API key, this will show the API key that we have copied, which is this. Okay, so this is what we have to configure our Google Generative AI package with. So the next thing is create a comment and say that configuring Google.generative AI with the API key. So then only you can access this. I'll say Gen AI, which is nothing but my Google.generative AI. So Gen AI.configure. We need to put our API key. So say API key is equal to Google API key, which we have loaded. Now we can go ahead and write some functions in order to load the model. So first function that we are going to use is it will just load the model and return it. So for that I'll create a function called dash load Gemini Pro model. So in order to do that, again, you can basically do all these things in this main.py, but I don't want to kind of keep my code too complicated. So I'm just like kind of making this code more modular, so that like the things that we are getting from the Gemini model stays in this Gemini utility, and main.py just contains like the user interface for our application. So that's the main idea. So here I'll create a variable called as Gemini Pro model, which is equal to Gen AI dot, we need to use this generative model, and within the parenthesis give Gemini Pro. So this is how you can load the Gemini Pro model. Again, the same model that Bart, that kind of like powers Bart. Again, now they have changed the name, so we can just call this as Gemini. So you can return this Gemini Pro model. Okay, so this is the first step. So basically we need to load this model to this chatbot page that we have, and kind of send the question that the user asks and get the response from it, right? So that should happen when the user clicks the first page, which is chatbot. So that's the first step. So for that we need to import this particular function from this file. So in order to do that, you can import this as from Gemini utility. So all this main.py and Gemini utility are in the same directory, so that's not an issue. So import this from Gemini utility, import second. So I can say import load Gemini Pro model. So this is what we are going to use. And next I can say if chatbot, if selected is equal to, chatbot, this should kind of run the below code in order to give the page that has like this space for the user to type in the text and get a response. So that's the idea. But before that, we need to create another function for this. We'll call this as define translate role for Streamlit. So again, I'll just explain you what's the purpose of this in a minute. Translate role for Streamlit, and here I'll say user role. If user role so if user role is equal to model, then we need to return assistant, else return user role. Okay, this is like not a complex thing. So basically, like we have a terminology for this LLM models in Gemini Pro, in this Google library and Streamlit, but these terminologies are different. In order to map those terminologies, we are just using this function. If the user role is model, right? So let's say that this model is referred to as model in the Google's package. We are going to convert this name to assistant. So that Streamlit kind of adjust or it understand like what it means by this model. If it doesn't say model, then we are just fine with it, right? So this is like not a complex thing at all. So the purpose of this is, right, it's just like a function translate role between Gemini Pro and Streamlit terminology. That is also, it's not complex at all. Okay, so this is something that we need. Now we have this page where we'll use this function and the load Gemini Pro model function that we add. So here I'll call this model is equal to load Gemini Pro model. So we are basically calling this function. So what this function does is it will call this Gen AI and load this Gemini Pro model, and understand that this will only work if you have configured it with this API key. So this will load this model and return this model, and that we are kind of storing this in the variable called as model. And now we are going to maintain a session for this. So Streamlit is basically like the default version that you work is like a stateless version. So if you kind of ask something, right, in the next question it kind of forgets everything, so the session kind of changes. So now what we are going to do is maintain the states so that the conversation that we have with the AI is kind of continuing. So like let's say that we have seen an example, right, where we asked what's the reason for Thanos doing what he did. So it gave an answer. Next, I asked, like, was he right about it? Now the model needs to kind of get this previous conversation. It kind of needs to read the previous conversation in order to answer this. But if you don't maintain the states, right, so the model won't get the previous conversation. So that's kind of like reset in Streamlit. So that, the reason, as I said, is like we are not maintaining the states. So we need to create these states or session for this in order to kind of pass this entire conversation and get an appropriate response. So for this, I'll say that initialize chat session in Streamlit. Again, this is not just for this LLM application. So this is like useful for any application that you build with Streamlit. It's always good to kind of maintain this states and session wherever it's required. Not already present. So if there is like some session maintained, it will use this. If not, it will like create a new session for that. So here I'll say if chat session, this is what we are creating. If chat session not in st.session state, yeah, this is like the Streamlit's internal function to do that. st.session state dot chat session is equal to model dot start chat. Here I'll pass history. No, this should be in parentheses. Is equal to an empty list. Let's understand like what this particular thing means. So here within this Streamlit session state, we are creating this value pairs called as chat session. So this chat session maintains all the previous conversation, or basically the previous messages that we have sent to this Gemini, and also the response for that. So if chat session is not in Streamlit session state, that means like if this is not present in the session state, it will create this. That means like if you have already created it, if you already had a conversation with it will already have this chat session, so that's okay. So if it's not present, that means you are running the Streamlit app for the first time, so this will create a chat session. And within that chat session, st.session state, we are using this again the same thing, the chat session. To that we are adding this model dot start chat. Model is nothing but the Gemini Pro model that we have loaded. And within this model, so this Gemini API again also has this ability to look at the previous messages and get and give an appropriate response. That you can do with this start chat. Again, this is coming from the Gemini Pro model. So you need to pass the history. As we are just creating this chat session for the first time, we don't have any history. That means we don't have any previous messages, so that's why we are just passing a empty list to that. But if as it runs for the next iterations, right, this list will basically contains the previous messages and the response from the model. So that's like the basic idea for this. Next, I'll create the title for this Streamlit page. Streamlit page title. So here I'll call this as st.title chatbot, but I just want to include like a robot symbol for this. So again, I'll go to this Emojipedia and search robot. Now I can click this and copy this and paste it. Again, you don't have to do it. So if you want, you can do, or use some other version, some other emojis as well. So it's not a problem. Next is we need to display like all the previous messages and so on. So this is to display the chat history. So for message in, I mean, it may be a bit hard to understand this right now, but once we see this chatbot page, right, so once we see that particular output and the way it displays it would make like more sense to you. So don't worry about it if this is like not very clear to you right now. So you will eventually get this. So for message in st.session state dot chat session dot history, so here basically we are opening this history that we have saved in this chat session and displaying all the messages over here. For the first time, it will just be empty, as we don't have any you know, we just don't have any conversation previously, so that's why it doesn't display anything. So we have this history colon. So for message in st.session state chat session dot history with st.chat message, this is again Streamlit way of displaying the message in a proper way, so that like you know, we have this proper messaging box and the response and so on. So chat message, we are going to use that translate role for Streamlit that we have created, and here I'll say message dot role and st dot markdown. So we are displaying all the results in markdown. We'll say message dot parts 0. I mean, these are standard things, you don't have to worry much about it. So text, so let's also discuss this a bit later as well, like what the purpose of this code exactly. Now the next part is, I mean, the users text box in order to ask something. Okay, so here I'll say input field for user's message. Here user prompt is equal to st dot chat input. Here we can just use a placeholder like ask Gemini Pro. And if user has given something, right? So if user prompt, so when the user doesn't type anything, this will be none. So this if block won't be executed at all. So here I'll say st dot chat message user dot markdown user prompt. So we are basically passing this user prompt. Let's say that they are asking what is machine learning, so we pass that to this chat message, which basically holds this model dot start chat. So that's the purpose of this. So once we get a response, right, so that will be from let's call this as Gemini response is equal to st dot session state dot chat session. Basically all these things are maintained in the chat session. If you're not maintaining these sessions, all this code will be like much simpler. So yeah, you can try with that version as well. Chat session dot send message user prompt. So this will pass this this send message is again the one with the Gemini Pro. So this will pass this user prompt as a message to the model. We get the response and store this in the variable called as Gemini response. Now all we have to do is display it on the Streamlit web page. So this is for display Gemini Pro response. I'll call that as with st dot chat message. Call this as assistant and st dot markdown Gemini response dot text. Let's see what all these things mean. Okay, that is all for this. I mean, first page that we have. 1 second. Okay. I'm just trying to also make sure that the code is in like good standard. So we would kind of see this lines when it's not in this page standards. And another thing about standards is, right, so here if you see this I have imported this OS library. So you can import all the pre-built libraries in the first few lines, give a space and kind of include like other libraries that you have installed, like let's say for example Streamlit and Streamlit option menu, and later again give a space, import the libraries and the functions that we have custom built. So this Gemini utility is what we have built, right? So that's what you can do first. In the first line you can kind of import all the inbuilt libraries that comes with Python, then import all the libraries that you have installed, and again the custom files that you have built. So that's like another tip that can be useful for you. So now again I'll go to this terminal. So we have built our first page and I'll say streamlit run main.py. Let's understand the code by just putting some messages. So here we have this image captioning doesn't have anything at all. Now we have this chatbot. So here you have this box, right, called as ask Gemini Pro, and you have this send symbol and so on. So that's what we have built in this particular section. So we have this user prompt is equal to st.chat input. So this chat input basically creates this box and this particular symbol, right? That's what this chat input does. And we have mentioned this ask Gemini Pro that's displayed over here. And now the user has to type something, right? So I'll ask the same question: why did Thanos do what he did? So you're seeing this little symbol, right, like with a human face kind of a thing. So for the chatbot's LLM's response, it kind of has this robots symbol. So this is also kind of configured in Streamlit. So you can again go through this answer. So Thanos a fictional character in MCU and so on. So we have this, right? So this is the response. Now I'll ask another question. Again, the same question of was he right about it? Was he right to do that snap and kill, let's say, I mean, like do what he did to, let's say, the half of the universe? Was he right about it? This will just like take a few seconds, so this model won't take like much time to load this. Like Yeah, this is like a more diplomatic and I would say like a better answer of whether Thanos was right about his action is a complex ethical question that has no easy answer and so on. So I would say this is a better answer saying like rather like yes or no, because a LLM or a robot can't take a stand for these sensitive issues, right? So it tries to put all the arguments in place and it lets the user to make the decision for themselves, which is like I would say a better way for the robot to act. So that's about like what's the answer that we got. But coming back to the coding aspects of this, so here we kind of asked a question and then we have this, we asked a follow-up question. So here I didn't mention Thanos and other things, right? So basically this answer is related or linked to all the text that we had previously. So the model should kind of, it shouldn't see this like as a separate question. So this question is linked to the previous question, just like the question that you would ask in ChatGPT, right? So we don't want to ask unlinked question or like it's not a conversation. Like let's say that you are asking why did Thanos do this particular question, it gives you an answer and then you ask was he right about it, and now it doesn't know who you are talking about. It doesn't know you are talking about Thanos. So that's why we are maintaining all this chat history and passing this history to the model so that it knows what the context is, so that we are maintaining a conversation and not a one-time message. So now let's see how this thing is built. Okay, so first we have this kind of the chatbot is being selected, so then only like this page opens and then you have this uh, st.title with chatbot and robot symbol. So we have that over here. Next thing is for yeah, this one, if chat session not in session state. So if I refresh this, right, so you won't see anything here. That means the session is empty. When you refresh this page, you won't see anything. At that time, the session state, this chat session is getting created in this st.session state and it put all the history over here. So here it is a empty list because we don't have any conversation previously. Now for message in st.session state, right? So once you have a conversation or once you have sent a message, we are using a for loop to display all these messages. So if I ask another question, right? So this is like everything is happening newly, but what happens is it displays this messages using a for loop, and that's what we have over here. For message in st.session state chat session.st, the first message that we have is the one that we have over here, like the one that I asked, like the first question and the first response from the model, and then we have the second question, right? So all these are displayed using a for loop, but with the message roles and the markdown, right? So all these things, and then we have this user prompt. As I said, like the next part is like having this message input box where the user can ask something and it can give a response for that. So this is how you can build a chatbot. So again, this may seem a bit complex, but once you try this code, right, it would make like more sense to you. So definitely try this out. I hope everyone is clear with the chatbot. So now in the next step we can move to the next page, which is this image captioning system. The purpose of this particular image captioning page is, right, so we should have an upload box where the user can upload an image, and we call the Gemini Pro vision model in order to understand the image and just give a caption for this or basically narrate what that image is about. So that's what we are going to build. So before building the Streamlit page for that, let's come back to this Gemini utility and load the Gemini Pro vision model just like the way we loaded the Gemini Pro model. So for that, I can just create a comment here so that the code is more readable. So this is function to load Gemini Pro model for chatbot. Okay. Next is function for image captioning. Okay. So here I'm going to say define Gemini Pro vision response. So it needs two things. One is the prompt and the next one is text. So here we are just focused on a caption for this image, right? So we would just like hard code this particular prompt which just says like write a small caption or a short caption for that. So I'll just say this as prompt comma image. So if you want, you can try something else, like you can explain, you can ask it like some other question instead of narrating it, right? But I just want a caption, so I will like hard code this prompt. But again, you can also let the user to write a prompt for that message asking like where this particular image is, or what do you understand by it, or you can ask something, but I'm just interested in a caption, so I'm not going to do that. So I'll create a function. Now I'll load this model as Gemini Pro Vision model, just like the way we have loaded our Gemini Pro model. So I'll call this as Gemini Pro Vision model is equal to GenAI dot generative model, the same thing, but in the parentheses you just need to mention Gemini Pro Vision, Gemini hyphen Pro hyphen Vision. So we need to put this in quotes, and then we have this response. So we need to pass the image as well as the prompt to the model to get a response. So we should say response is equal to Gemini Pro Vision model dot generate content. This is the function to get the result, and within that we need to pass a list. Within this list we need to first have the prompt, and then we need to pass an image. You can basically pass an image that we have read from pillow. I'll show you. And then we have this result is equal to response.txt. So you would have like other things from this API response, but I just want to take like the text out of it, so you can just use this response.text. And finally I'll return this result. You can also kind of see what this response is, and you can basically do more things to it. I'm just like sticking to basic things. So we can test this function here itself. So I'll show you how you can do that. For this I have a test image. I'll open this. So I think this is like Chinese, because when I put this to the model it says that this is a street in Hong Kong or something, right? So actually this image is also generated by image generating model. I'm not sure if I generated with GPT-4, or you also have this Microsoft Designer that you can use. I don't remember it, but yeah, this is also generated by AI. So this is the image that we have. So I'm going to copy this and paste it in my default working directory for now, just to test this particular function. So I'm pasting it here. So I have this test image PNG. Now I'll load this. So we have this, we don't have pillow here. What we'll do is we will load the image in this file, but in order to demonstrate this I'll show it to you this way. From pill import image, and here I'll say image is equal to image.open. This basically opens a image and load it with pillow library. So test image.png, and here I'll say I'll basically call this as I'll create a variable called as output, which is equal to Gemini Pro Vision response. Within that pass the prompt. So let's say the prompt is write a short caption for this image. Now you need to pass the prompt as well as the image. So I'll say this as prompt comma image. Let's run this and print the output as well. Let's see what the model is saying about the image. Let's run this. Yeah, so the image model like just take like few more seconds compared to the Gemini Pro model, and it says like it's a busy street in Hong Kong. You can also say like write a short or brief caption, or you can say like explain what the image is. You can like ask something to it as well, so instead of a caption. So I'm just interested in building this captioning model, so I'm just sticking to this prompt. But again, as I said, you can hard code captions the prompts like this, or you can let the user to choose whatever they want to do with that particular image. So this is how this would work. I'll just delete this. We will kind of do this image loading part in the main.py file as we should. I'll delete this importing thing as well. Okay, let's come back here. So all this function is done. All it requires is like the prompt and the image, and then it passes it to the Gemini Pro Vision model, get the response from generate content, and we just return the result. So I'll come back to the main.py file. Let me just close this. So here first, when the user has selected this chatbot, it does this. Next thing is when they have selected image captioning, we need to do this, right? So for that, what you can do is create another if condition. So here I'll call this as image captioning page. If selected is equal to image captioning, you can just copy this one. If the user has selected the second page, the below code should get executed. First, let's create a title. So let's say st.title. Within that we can call this as snap narrate. Just narrate what's present in a picture, or you can just name anything. For that I'm going to use like a silly emoji, so I'll just search it as image. I'm going to use a camera emoji. Yeah, I'll use this. Okay, so we have the snap narrate. Put this within the if block, and we need to create a box where the user can upload the image. So for that I'll create a variable called as uploaded image is equal to st.fileUpload. Okay, file uploader. Here we can say some text like upload an image, and you can also mention like what are all the types that you accept. So let's say for example we accept only jpg, jpeg and png images. You can just mention that. Okay, Mr. Quote. Okay, the next thing is we are going to create a button. If st.button, so st.button will create a button, and I'm going to name this button calling this like generate caption. So once this button is clicked, the below code should get executed, which is the image should be opened and displayed. So image is equal to image.open uploaded image. Oh, we have to import image, which is from pillow. I'll import this as from pill, import image. And I'll create two columns just to display the image and the caption like in separate spaces. So I'll say column 1 comma column 2 is equal to st.columns. You can again create any number of columns that you want. So here I have two columns, 1 and 2, so that's why I'm mentioning 2 here. If you have 3 columns, mention 3. And in the first column, right, I need to display the image. So for that you can say with column 1. You can also resize the image depending upon your needs, so that if the user has kind of uploaded a larger image with a larger dimension, you can just resize it and fit it in your screen. So I'm going to call this as resized image is equal to image dot. So once you have loaded it in pillow, you can just use this resize, which is from pillow library resize. I'm going to go with 800 width and 500 height. Can use this, or again any dimension, proper dimension you want, you can play around with that. And I'll see st.image. So this st.image, if you pass like a image loaded with pillow, I have to use this resized image. st.image basically displays a pillow image and other images that you have loaded. And next is I'm going to pass this particular image and the prompt to my model. Let's say that default prompt. So here, as I said, I'm going to hard code my prompt here. So default prompt is equal to write a short caption for this image. Please try few other things as well with this, and getting the response from Gemini Pro Vision model. So I'll create a variable called as caption, which is equal to Gemini. Oh, we haven't imported this function, right? Which is Gemini provision response. So for that, what you can do is in this import, again, more standard way, if you want to import more thing is like import, put a, parenthesis here and do this. Import. First, we need load Gemini Pro model. And the next thing is like we need Gemini Pro Vision model, right? So this is how you can just create like a tuple kind of a thing, and you can import it so that your code looks more compact and so on. So there are like standards of how much space that you can cross. So you see this line, right? So you shouldn't cross this line. You won't get any errors, but these are just like some coding standards that you can follow, what we call as pipette standard. So you can follow those things. So for this caption, I'll say get Gemini Pro Vision response. Here I have to pass two things, right? So one is the prompt, the next one is the image that has been loaded with, I mean below. You don't have to pass the resized image, that's okay, just pass this image. So we need two things, right? One is prompt and image, so that's what we are passing, and the result will be in caption. Now we need to display this. For this, I'll call this with column to st.info caption. So we are just putting it in a text box that will look in blue color if you use this text.info. So another interesting thing that if you see here, right, first we have this with column 1, and then I'm calling this with column 2 and caption, and then we are displaying it. The reason is you can get the caption as soon as the image is uploaded and later display the image and the caption. But the thing is, let's say the caption generation takes like 5 seconds or 10 seconds, so before that we can display the image. So that's why first I'm displaying the image over here and then getting the caption and then like displaying the caption here. So that's the idea. So I think this captioning model is ready. Let's again run the streamlit run main.py. It's okay if you have this running as well, you can just refresh this in order to get the response. So first we have this chatbot, then you have this image captioning. So you have this upload an image, which we have over here, upload on image thing, snap narrate, all these are here. So I'll browse this file that's present in this desktop, which is test image.png. Let me quickly check one thing. Yeah, I've deleted it. Right, so we have this test image.png and click this generate caption. So we are seeing like a smaller image of this, the resized one. Again, you can resize this to any shape that you want. This is like the first column. In the first section of this page we are seeing this, and the next section we are seeing this, a busy street in Hong Kong at night, the street is lined with tall buildings and so on. This basically is like narrating the image. So you can also adjust the prompt as you want, or what you can do is put a text box here where the user themselves can give a prompt for this. So this is how you can build the image captioning page. So these are the two things that we have worked on. So I hope that you are clear with the chatbot building and the image captioning model. So the next thing that we are going to work on is text embedding. So the other two things are like pretty simple things, so it's like not complex at all. So let's see how we can get the embeddings for this text and then like just build a question answering thing. Yeah, so I'll come back to my code. You can stop this Streamlit tab. I'll come back to the Gemini utility file. Next is we need to load this embeddings model, right? So this embedding model is basically you have to pass text and it gives you the embeddings as the result. Maybe you can mention this. So Gemini Pro takes in text and gives the output as text. Gemini Pro Vision is kind of a multimodal model. So it takes text as well as images, but it will give you the output as text. So similarly, embeddings will take the input as text and return embeddings. So here I'll say that function to get embeddings for text. I mean, these embeddings are mainly used in order to do a similarity search and all that. So again, it's really helpful when you are kind of doing a document search where we will first embed the content of the documents, and you also kind of have this query, you kind of convert that to embeddings as well. It's just like finding like related vectors or like vectors that are lying close to each other. Like, that's interesting stuff. Maybe let's discuss about it like in a later video, as I said. So here I'll call this as define embedding model response. This we have to load it a bit differently. So I have this input text. You can see like all these model details in this Gemini AI Studio. So you would have this model section, you can check that over there. So input text where the user has kind of passed a text, right? So we will embed, or we'll basically return the embeddings for those text. So I'm calling this or creating this variable called as embedding model. So embedding model is equal to models slash embeddings 001. This is the name of the model, and let's say embedding. You can again, as I said, you can find these details in Google AI Studio Quick Start. So here we need to get the embedding output from this embedding model. So here say Gen AI, the same library that we have been using, dot embed content. So previously we have used Gen AI generative models, but now we are going to embed the content. The text content is basically the text that the user is kind of sending. And here I'll say model is equal to embedding model. Content is equal to input text. The user is the thing that the user is sending. And the next thing is task type. You can mention this as retrieval document. And finally, you would have this list. So this will be in a dictionary and we need to extract the content from it. Maybe I'll show you that dictionary as well. Return embedding. We can again as well test this. So we need to call this, right? So I'll create a variable called as output is equal to embedding model response. I'll just create a simple text like something like the same thing. Who is Thanos? And let's print this and we can run this one. Okay. So this will take in the text and return the embedding. So it's in the form of a dictionary. So we have a key called as embedding and a list that has like all the embedding values, right? So again, this is crucial in doing those similarity search and other things, but let's discuss about that later. All I'm interested in is just to get this list. So for that, you can just say embedding, which is basically a dictionary, is equal to, or I can say that embedding list is equal to embedding, and within this square brackets you can mention the key, which is this one, right? Yeah, now this should just return embedding list, just that list, not the dictionary itself, and then later we can display it, right? So you can see the list now. So this is the function that we are going to use in our main.py file. So I'll just remove this. Now let's come back to main.py file and build this vector embedding page. Again we have to do this if selected. Okay, let's call this text embedding page if selected is equal to embed text. In that case, we need to kind of give a title to this page, which is st.title, and within that you can say embed text. Again, I'm going to take like a quick emoji from here. I'll call this as letters or something. Okay, me go to this symbols maybe. I think I saw this ABCD thing that we can use here. This one. I'll copy this and paste it in the code. This would be the title, and let's give a text bar for the user where they can type in some statement or even the paragraphs to get the embeddings for this. So basically the ultimate goal of this is, right, so you can upload a document and just ask a query about it. So let's say that you upload a document, a PDF file about a particular study, and you want to kind of ask a question that's present in that particular PDF. So you kind of ask that question and upload that PDF. So both these question and the document will be converted into embeddings, and we kind of look for a similarity search, do a similarity search with this embeddings to get a proper answer from this document. So that's the ultimate goal, but we're just going to display the embeddings for now. So here I'll say text to enter the prompt. I can just say like input text box. Create something like input text is equal to st.text area. So this will just create like a larger text box where the user can type in something. I'll the label. So label you can just have it like as an empty thing. So we don't have to put anything here. And placeholder you can just display something like enter the text to get embeddings. Okay. So now we can create a button just like the way that we did before. st.button. We'll call this as get embeddings. Once this has been clicked, right, so we can call the model. So response is equal to uh, embedding model response. Oh, I think we haven't loaded it again. Yeah. So put a comma here and load it from this Gemini utility, embedding model response. And within that, we just need to pass the input text, right? So input text. And then we need to display it with st dot markdown response. Okay, so basically what happens is the user types in some text, and then we, once the button is clicked, we call this embedding model thing where we pass this text to this model of embedding not one, and then we just get the embedding list out of that and then display it with markdown. So this is how the third page works. So I'll save this. Let's run the Streamlit app again. We can see it here. Okay, so chatbot is done, image captioning is also done, and then we have this embed text where I just ask something. Let me put this as machine learning. It's a subset of artificial intelligence, and just say get embeddings. Right, so this is the embedding list that we use. Again, as I said, this is like a part of the problem. Later, let's see how we can get like or build like interesting use case around this. So this is how you can embed the text. So here the input is text and the output that you basically get is a embedding list. So this is how you can do this. I'll just put a capital G over here. So if you make any changes to the Streamlit app, right, you don't have to stop it and run it again. Sometimes it may not work, but in most cases you just have to do a refresh. So now you see this G in lowercase, right? So I'll refresh this, and now if you go here, it will be kind of adjusted. You can just refresh this page, but I'll just stop this app for now and just build like the last page, which is just like ask a question and get a response. So nothing complex. It's just like the chatbot, but we are not going to maintain the conversation. I'm just going to give you a simple version of that. So let's see. I mean, it's just like a simple thing. So I'll come back to my Gemini utility. Here I'll create another function. Let's call this as function to get a response from Gemini Pro LLM. Okay. So let's call this as define Gemini Pro response, and we need to give the users prompt, like the prompt that they are kind of typing in. Here we need to load the model again. I think we can use like the same thing that we have over here. So here we are returning the model itself because we need it for maintaining this chat history and so on. Here I'm loading this with the same name Gemini Pro model, and then the response is equal to Gemini Pro model dot generate content. Same thing that we have used, generate content. Within that, pass the prompt that the user has sent. That is all. And then result is equal to response dot txt text, and then return result. Okay, that is all. It's like that simple. Let's test this as well. I'll this as output is equal to Gemini Pro response. Within that, I'll give a prompt of what is machine learning. Okay, and let's print this output. Hmm. So this would explain like about machine learning in a detailed way, right? So you are seeing this, right? Machine learning is a subfield of artificial intelligence, and all those things. So we have the stars and so on in order to make these particular line more bold and so on, right? In order to incorporate all this, we are using Streamlit st.markdown. So it would capture like all these bold styles and so on. So that's the purpose we are using st.markdown. So let's see how we can do that in this main.py file. So these are the functions that we are going to build, and all these are done. And finally, let's build our final page, the fourth page, which is this yeah, ask a question thing, right? Ask me a question. Let me just put this as question answering page or something like that. If selected is equal to, so you have to put double equal to, come back to the top, copy this, ask me anything. Again, as I said, this is like a shorter version of the chatbot that we have built earlier. So ask me anything is selected, st.title. I'm going to say that ask me a question. So this is the title of the page. Put this in small. I'm going to copy a question mark emoji. Yeah, so put this as question. And copy this red question mark and paste it here. Again, this is the name of the title of the page. This is like what's the user has kind of selected from the left navigation bar. And ask me a question. So once they have asked a question, so text box to enter prompt by the user. So let's call this as same. User prompt is equal to st.text area. They can just like ask anything. Again, you can use label is equal to just an empty null string, and placeholder is equal to same thing, ask me anything. Or you can even put ask Gemini Pro, same thing that we have there, just 3 dots. So now let's have a button. If st dot button, so once this button is clicked, we will call this model. Let's call this as get response, or you can just get an answer. Here we would call the model, so response is equal to we need to import it again, Gemini utility. We need to import this Gemini Pro response function. I'll do that over here, Gemini Pro response. And within that, we just need to pass the user prompt, and then later display it with markdown, st.markdown, and put your response over here. So that is all. So this is our final Streamlit app. Let's make sure that this is working. I need to run it again. Okay, st.markdown response. And I'll come back to my terminal, clear all these things. You would just get some warnings because of that label, but that's fine, no issues. This would open my page. So I've completed my chatbot, image captioning, embed text. Finally, my ask me anything. I'll just ask like what is machine learning. You can also display it with st.info and other things, but for this markdown is better to capture like all those styles and so on. Let's wait for this to give an answer. Right, so you have these definitions of machine learning in bold and all the response for that, right? So this is how you can use this Gemini model in order to build this chatbot, image captioning, embed text, and ask me anything. And again, we are at the last part of this video of deploying this as a public app. So this is still in a local host server, right? So you can't share this to anyone. So let's see how we can deploy this in Streamlit cloud so that you can share this app to anyone for absolutely free of cost. So the other things that you can do is you can just build a chatbot that kind of sends you some codes as well, right? So I think I can try it with this thing as well. Write a Python code to build a convolutional neural network. I think sometimes it may fail, but let's see if this is working. I'm not exactly sure. Write a Python code to build a convolutional neural network. Let's see. So later, let's see how we can deploy this on Streamlit Cloud in this video itself. So I hope that this gives a proper response. Not bad. So we have a Python code, say it's import TensorFlow, STF, and all those things. So I'm not sure how much of this is right, but I can see like it's okay. So you can try doing that, or you can also get a Python code and you can execute in the backend and display the result to the user. You can kind of do that as well. Just create like, let's say a coding buddy or something. You can create another page and do this. So this is how you can do this. Now let's come back to our Streamlit deployment part. So for this, you need to go to this share.streamlit.io. Before that, you need to put all these code in a GitHub repository, and Streamlit Cloud expects your repository to be public. But I think they allow you to have to kind of deploy one or two applications in your private repository, but you can look that up. So here I've added like all these files in a GitHub repository which is public. You need to sign up with that same GitHub account to your Streamlit thing as well. Just go to Google and search share.streamlit.io. So I'm already signed in, so this would automatically log me in. If not, you can just like create an account again. As I said, like the same GitHub account. GitHub is must, so it takes all the code from there. So it's like a must. So you can do that. So once you've connected it, right? So your GitHub account will be connected. So here you will see this new app within the share.streamlit.io. So click this new app. So again, as I said, your repository is already linked. Oh, seems like it's not linked it. Okay, it's asking for authentication. Yeah, so it's active now. So now if you click this, it will automatically pick up all the public repository, basically all the repositories you have over here. Here I have this Gemini AI course prep, right? So that's what you will see here. If I click here, it says my username and Gemini AI course prep. Select this, mention the branch. Here I just have main branch. I don't have any development other branches, so you can mention that. So it's a main branch, and name of the Streamlit app. So it's Streamlit app.py, but in our case it's main.py, right? So just like rename this to main.py, and you can also give like a custom name for this. I'll call this as Gemini AI application. You can create any name if you want. So this domain is available. So the final URL will be Gemini AI application.streamlit app. So let's give this deploy. This would just take like a few minutes, like a couple minutes, shouldn't take more time. Let's also test and see if this is working in cloud as well, so that like you can just share this URL to your friends or someone, and they can use it as well. Like I would suggest you, like if you are going to an interview or something, or if you want to present this in LinkedIn or something, you can just deploy this. It's absolutely free of cost, so they will turn off your app if you're not frequently accessing it. But yeah, you can share this to others so that they can experience like what you have built. So you can also click this manage app to see like the process that's going on. So here basically your requirements.txt is getting installed. So you need like all these files here. So you need this config.json, which as your Google API key, Gemini utility, main.py file, requirements.txt, and finally your test image is not required. This is like the sample image that I had, so that's not required. So all the dependencies are getting installed. Let's wait for it to get completed. Okay, so we have our application. So here you have your chatbot, image captioning, embed text, and ask me anything. So I'll just test if everything works. Again, I'll ask the same question of why did Thanos do what he did. Let's see. This is just to make sure that everything is fine and working normal. So if there are any issues, you can kind of see this in the manage app thing itself. Okay, you will see this warnings again. As I said, that's okay. The label thing, if you want, you can put something in the labels. So Thanos the Mad Titan, blah blah blah, and so on. So we are getting a response. I'll also upload my image and check this. So browse your files. I have this in my desktop. So yeah, this test image.png. Try with some other different images as well. Generate caption. So we have displayed it, so it's running. And then we would have our caption over here, a photo of a busy street in Hong Kong, and then we have this embed text. We'll ask machine learning, just put something like machine learning course, get response. We have our embeddings, and finally ask me anything. I'll just ask what is machine learning, get a response. So seems like everything is working, and this is how you can build your application. So make sure that you are trying this at least once, so you will like get a good amount of learning. And again, this is just like the iceberg, tip of the iceberg. You can like try more complex and advanced application and interesting use cases as well. Let me know if you have worked on something that you would like to share, so you can kind of tag me in LinkedIn. So I'm active in LinkedIn, you can do that. Okay, so I hope that everyone is clear with all things that we have done, and this is like helpful to you. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone. I'm Siddharthan. Meta has launched its next generation of LLM called Llama 3, and a lot of people are discussing about the potential it has to compete with the industry standard models like GPT-4, Gemini Pro, and other LLMs. So the best thing about the family of Llama models is that Facebook open sourced these models, so we can use these models for commercial use and other research purposes too. So in this video, let's understand how we can access this Llama 3 model and how we can build a text generation system with it in Google Collaboratory. So this is what we will be covering in today's video, and let's get started. So as I said, we will be using Hugging Face. So the first thing that you need here is you need to create an Hugging Face account if you don't have one. So again, Hugging Face kind of hosts a lot of models, and even you can access like Llama and Llama 2 model, and they have added this Llama 3 model, and this Llama 3 has like two variations. One is 8 billion and the other one is 80 billion. So the previous family of model was Llama 2, and that came like 7 billion, 13 billion, and 70 billion. So this has like 8 billion and 80 billion. And within this 8 billion and 80 billion, there are also two other variations. One is just this base model, and the other one is instruct model. So I'll explain you about all these things. So for getting started, right? So just sign up for Hugging Face if you don't have an account. So once you do that, right? So you can go to this Hugging Face page in Google. So sign up, and in this search bar, even before signing up, you can just go to this Llama 3. So you will see this in the initial place. If not, you can just go ahead and search Llama 3, and you will see this. So you're seeing this 8B, right? So you will also see this 80B instruct and 8B instruct and so on. Maybe let's just go with the base model first, and here you will see this. So you need to agree to share your contact information to access this model. So there are like some terms and conditions you need to agree, and it's like completely free. It's not like we need to pay anything or something like that. Just scroll below, you will see this option to log in or sign up. So once you log in or sign up, right, so there will be this accept terms and conditions thing. So once you do that, it would say that your request is being reviewed, and maybe after an hour or couple hours you will get this access. So if you refresh this page, you will see that you will have access to this model. So you will also get a mail in which you have like signed up in your Hugging Face account. So this is how it would look like once you have the access. So you will see that gated model, you have been granted access to this model. So once you have this, you can go ahead and start working on it. So this is how this works. And as this is a gated model, we need to provide the access token from our Hugging Face account. So we have this collab environment, right? So here we are going to load the model from Hugging Face. So here we need to get this access token, put it in this collab environment so that we can authenticate that this is the account through which I'm trying to access this model, and I have like reviewed all this terms and conditions and so on. So that's about it. Okay, so now let's understand how we can work with this. So the first thing is we need to install a bunch of libraries, and we need to save this HF token or this Hugging Face access token. So let's maybe discuss like how we can do that first. And you need to connect to a GPU environment. So go to this runtime, go to this change runtime type, and select T4 GPU. Okay, so if you have Google Colab Plus or Colab Pro, right, so you will kind of get access to more powerful GPUs, but I mean this is not required. You can choose T4 GPU, and the size of this 8 billion model is about 15-16 gigabytes. Even that you won't be able to do this in Colab, because Colab just offers you 15 GB of GPU RAM. So what we are going to do is do a process called as quantization. So I'll explain you about all those things. So for that, we of course need this GPU setup. So that's why you need to kind of have this T4 GPU setup, and you can give this connect this thing. Then go to your files section. So you're seeing this files, right? So once you're connected it, we are going to create two files. One is requirements.txt to mention all the libraries that we need, and the other one is config.json. So I'll just right click here, and I'll see this option called as new file. So here I can say requirements.txt. So in this untitled, I'm going to say requirements.txt, and here I'll enter it, and this will save this file. Now double click this, and this file will be opened here. So here we can install the required libraries. So we'll be needing three libraries. The first library is called as accelerate. So I'll say accelerate pypi in order to get the package index. So again, this is used to do the quantization. So quantization is nothing but we would reduce the precision of the model so that we can, let's say the 15 GB model won't be 15 GB anymore. So it will be around 6 GB. So again, it's a trade-off between the accuracy and the performance that we would get. But again, we can't load a 15 GB model if we don't have that much computation power. So that's about it. Okay, so let's install this accelerate. And next we need this bits and bytes configuration. So again, come to Google, search bits and bytes. So all the latest version should be good. So in this bits and bytes, download this. Again, if you have a laptop or a PC with, let's say, a larger GPU, you can do this in your local Jupyter notebook too. But again, if most of us may not have this, so that's why I'm doing this on Collab. Or if you are working in an organization and you can use their AWS SageMaker notebooks, then you should be good, because that gives you offer to larger machines. So that's good too. And then we are going to check transformers. Transformers is nothing but the Hugging Face library. So that's called as the transformers one. So you can see this. So here I'll copy this transformer 4.40 and paste it here. Okay, so we need to install these three libraries. If you want any other libraries, or if you're working on something else, you can install that too. So I'll save this, and now here I'm going to save exclamatory marks to run this as a command and say pip install r requirements.txt. Okay, so this will install all the libraries present in this requirements file. So the next step is creating a config.json file and putting your access token there. So there are like a few ways to do this. One is you can use a .env file so that you can save the access token in the environment variable, or the other step is you can create a JSON file and load it and pass that HF token. So here I'll create another file and I'll call this as config.json. Okay, so config.json. So you should kind of have the data in the format of a dictionary. So double click this. So now this is empty, and here I'm going to create a key value pair and I'll call this HF underscore token. So this would be my key for my JSON file. So I'll come to this Hugging Face account, go to, so this on this right side you're seeing this, right? So this is your profile thing. So click this and go to your settings, and in this settings we would have this access tokens. So in this access token you can copy your access token and paste it there, right? So here I've already created like a access token. Maybe I can delete it and I'll show it to you, or you can do this. So I'll create a new one, and maybe after I posted this video I can delete this. So make sure you're using your access token. So the token that I'm going to show in this video won't work because I'll delete this. So again, these are like pretty confidential information, so you shouldn't share your tokens publicly, and that's what they have mentioned as well. But just for this tutorial purpose, I'll just show you. So go to this access token in your settings tab, and in this give new token, and let's name this as Llama 3 getting started. So this name is not like important. You can give any name and you can like kind of write it, or like you can basically give different permissions. So for this particular thing, read permission is enough, and say generate a token. So you can show this, or you can copy this from here. So it will say copied. Now come back to your HF token, and then in this again put double quotes and put your access token here. Okay, so I'll save this and close this config.json. So now what we are going to do is save this config.json to a variable. So maybe that we can load later. Now we can import all the libraries. So installing of this libraries may take some time, so we need to wait for that. So here it has installed all the libraries. Now let's go ahead and do this code of importing it, configuring the transformers library, the Hugging Face library, and then loading the model quantization. So we can start with like all those things. So first I'll maybe say this part is installing the dependencies. Okay, so next step is installing the dependencies, and now we are going to import it. So here I'll say import JSON. So I'm importing JSON to read this JSON file, and later pass that HF token to this transformers library, and then I'll import this torch. So torch also we need in order for this setting up the data type for this quantization. And then from transformers import. So here I'm going to import like multiple things. So I'll put a parenthesis here just like a tuple and say that again this is like a better way to import if you have, let's say, 5 or 6 methods or classes that you need to import. So you can just put a parenthesis and within that you can import it. So I'll say first thing that we need is a auto tokenizer. From this we would kind of import the tokenizer of the Llama 3 model, and then we would have this auto model for casual ML. So all this other model as well. So casual casual LM, and basically the language model, and bits and bytes configuration. So B should be in caps. We have bits and bytes. So pay close attention to the uppercase and the lower case letters. So bits and bytes config, and here we will pass the quantization configuration, and finally pipeline. So we would create a text generation pipeline. So let's run this. So these are the things that we need. So we have auto tokenizer, from which we will load the tokenizer of the Llama 3 model, and auto model for casual LM. So okay, I think I made a mistake here. Casual auto model for casual. Okay, so not input name. Let me check this quickly. Let me check this. Sorry, so this should be causal, should not be casual. So rename this to causal. Okay, so let's run this again. And sorry, there is a typo. So this will import all the required methods or the classes that we need. So the next thing is we are going to configure the transformer library. So I'll create another text cell, and here I'll say HF. So the HF basically means Hugging Face. So Hugging Face account configuration. Okay, so here let's load this config data. So I'm creating a variable called as config data, and within this I'm going to say json.load open config.json. So here what this does is this json.load will open this config.json file and save this in a dictionary, convert this load will convert this json to a dictionary, store this in this variable, and then you can store this token using this variable hf token is equal to config data, and in this you can say hf underscore token. Okay, so let's run this. So this will read this file and save the token. So I can copy and paste it here, and then can show it to you. So you can, I mean, you can directly copy and pass this to the variable, but that is like not recommended at all, because you shouldn't post any API keys or access tokens directly in your code, so that, because if you're sharing your code, then others could see it, right? So for that purpose you shouldn't do it, but this is just for your learning purpose. I'm just showing this to you, but this is not recommended. Okay, so we have loaded the configuration token to this variable called hf token, and next we are going to give the name of the model. So I'll say model name, or you can also use the variable model id, so that is also widely used, and we need to copy the name. So come back to your Hugging Face and search for meta llama 3 8 billion. This is the name, so you can copy this and paste it here. So meta llama 3 8 billion. So run this. So the next step is we are going to create the configuration for our quantization. So here I'll create a text and can call this quantization configuration. And as I said, the purpose of this quantization is the LLMs that we are working on. It can be a GPT-4 or it can be a Llama 2 or Llama 3 or any other LLMs. Like, these models are pretty big. So what we do is we do a process called as quantization, and this will shrink the model. So how this does is this will change the precision of the weights. So we know that all the models, the deep learning or any models would have parameters of this weights, right? So this would be in a higher precision, like 32 bits. So here we can we have this ability to use, instead of 32 bits, you can use like 16-bit or even like 4-bit weights and parameters. So that's what we call as quantization, and we kind of do this. And of course there's going to be a trade-off, because we are reducing the size, but the loss in that performance or the accuracy won't be that big. So this is just to kind of do this analysis or working with LLM, even if we don't have like that large of a GPU. So here if you see this, right, so the GPU RAM is 15 GB. When you load your LLM and just pass one prediction, your GPU is going to fill and your collab session is going to terminate. So we don't want that to happen. So we will quantize this and load this to the GPU. And when you load it, right, so that is going to take only like 5.5 or 6 gigabytes of GPU RAM. So that's the reason we are kind of doing this. So for this, we are going to create a variable called as bnb f_config. And within this, I'm going to say bits and bytes, the one that we have imported, put a parenthesis and say load in 4-bit, like all the ones that are mentioned here. So load in 4-bit. So here I'm going to say true. And the next is bnb 4-bit use double quant. Use double quant is equal to true. So this double quant is equal to true is like, this is nothing but, so we are telling this bits and bytes that I want to quantize this model, but I don't want to lose a lot of information, so that my model is performing well. So this double quantization helps us to preserve the performance of the model, or like it doesn't allow the model to lose a lot of information or its ability to perform by reducing this precision. So that's what like this parameter is used for. And then I have this parameter called bnb 4-bit quant type. So this is like one of the types of doing this quantization. So quant type is equal to, that is this type called as nf4. So this is what we are going to use. And then we have this bnb 4-bit compute d type. So we need to pass the d type. So for passing this d type, we'll be using this torch. So we should that's right, actually we have imported this. So here I can say torch.bf float 16. So we can use this 14-bit floating point. So I'll run this. So now we have to pass this bnb config, this bits and bytes configuration for quantization while we load the model. So that's the purpose for this. So once this is done, the next step is loading the tokenizer and the model. So here let's say loading the tokenizer and the LLM or the model, you can call it whatever you want. So here I'll create a variable called as tokenizer. So I hope you know what is a tokenizer. So this tokenizers are used in NLP cases. It's just to convert the raw input string to a format that the model needs. So all these models, right, so it can be any LLMs that you're working on. So each of these models would have like a separate LLM for that. And for this LLM, this Llama 3, we have to use the tokenizer that is used for this Llama 3. So you can go to this tokenizer and we have this auto tokenizer, right? So you can give that here. So I can copy this and paste it here, and within this auto tokenizer you can say auto tokenizer dot from pre-train. So this is a pre-trained model, right? The Llama 3 one. So say pre-trained, and you have to give the model name. Again, if you want to use a Llama 2 model, you just have to find that name. So for Llama 2 you can just say Llama 2, and Llama 2 has like a chat variation too. So chat acha, so this performs well in chat scenarios. So you can try this model also. You just have to change this model name to that one. So the other things can stay the same. So I'll copy this model name, and the next parameter that you have to pass is your HF token. Okay, so here I'll say token is equal to HF token, which is what we have loaded, and I'm going to say tokenizer dot pad token is equal to tokenizer dot EOS token. So let's run this. Okay, so you can see the tokenizer size 9.8 MB. This has been loaded, and it says like special tokens have been added in the vocabulary and so on. So this is how you can load this tokenizer, or like any pre-trained tokenizer, you can just give that name, and I mean all the models doesn't require this HF token. So Llama 3 models require your access tokens. There are some models for which you actually don't need these tokens. For that you don't have to include this tokens. And then we have this tokenizers dot pad token, right? So this is like an interesting thing. So pad token is nothing but the padding tokens, and EOS token means end of sequence tokens. So it's like when you pass a set of sentences, or like let's say a batch of input, right? So all these sentences of the data points that are being processed by the tokenizers should have the same length. And what would happen if you don't pass this end of sequence, right? So the let's say there is like a particular sequence is short, the input text is short. In that cases, we would like add extra spaces to it, and then we would pass this to the tokenizer. But when we add this EOS, end of sequence token, it would add a marker to say to the tokenizer that this is the end of the sentence, just process until this point. So that this is like a better approach to do this. So we are setting this pad token to this end of sequence token. And the next step is similarly from this, we have imported this model from this tokenizer from this auto tokenizer, right? So similarly we are going to load this LLM from this auto model for causal LM. So for that I can say model is equal to auto model for causal LM, and within this parenthesis, okay, I have to say from pre-train. So here we have to pass some parameters. The first parameter is the model name, so the Meta Llama 3 model, and then device map. So this is a very important thing. So here this tells you whether to load the model in your CPU or GPU. So here I'll say device map is equal to auto. This means if there is a GPU, it will automatically kind of allocate that space in the GPU, and it will load the model in this GPU. If not, you can also say CUDA, or you can say that I want to load this in the CPU, right? So that will basically load your model in your RAM. And again, so this is kind of crucial because when you are working with a larger machine, so let's say that you're working with a SageMaker notebook instance that has like 8 GPUs, so you would probably work with like a G548X large machine. So that's like a pretty large machine that has like 192 gigabytes of GPU RAM. So there again, as I said, it has like 8 GPU. So let's say this 80 billion model would be somewhere around 200, be 150 to 200 GB. So I think that's the size of the model that it would be, and this model, right, would be loaded in all these GPUs. It would kind of be distributed in all these GPUs. So when you say this device map is equal to auto, it will kind of automatically allocate the model to the GPU or the RAM that is available, or you can also configure this or like custom load this model, so that's possible too. So here I'll say device map is equal to auto, so that this will like load the model in my GPU RAM only. So I'll tell this, and the next thing is I'm going to pass this quantization config. So if you don't do this quantization config, it will load in this default precision, and again, if the model is 15 GB, your GPU RAM will be filled with 15 GB. So again, we don't want that to happen because of our lesser GPU size. So pass this BNB config which we have created here, and then you have to pass your token too. So my token is hf underscore token. Now let's run this. So this will download the model. So here you will see like the size of the model. So we totally have like 4 shards for this model, and the first shard is like 4.98 GB. So all these 4 shards will be downloaded first. So here if you see this, right, so what is happening is like it's downloading this shards to this disk. So you have 78.2 gigabytes of disk. And again, we are just working with the 8 billion model. If it's 80 billion, the model, of course, it's going to be more than 150 gigabytes. So even your disk will kind of fill. So it's not like ideal to work with it in Google Colab. So of course, you need a larger machine. So it's as it's downloading, you will see this increase in this disk space. So once the model has downloaded, what would happen next is this will load this model into the GPU. So that process will happen next, and you will see how this GPU RAM is filling once all this safe tensors, this shards kind of completed loading. So the first shard is 4.98 GB and the next shard is like 5 GB. So similarly we have like 2 more shards, and as you can see it's like downloading in a very good pace. And if you're working in a Jupyter notebook, in a local Jupyter notebook, you won't be having like this fast of a speed. So I can I mean this is like pretty high speed, right? So it's happening in Collab so that we are kind of able to load this. But again, if you're working in your local, so that might take a lot of time. So the other option is Meta should have given this repository access, so you can also download the model from there and then you can load it too. So even that is possible, so you can try that out too. So let's wait for this download to complete and we can check how this model is loading. In the meantime, we can do the other things required. So here I'm going to create a pipeline. Right? So for that only I've imported this pipeline thing. So I'm going to create a text generated pipeline. So here I'll say text generator is equal to pipeline, which I've imported from transformers library. And within this, let's say the first parameter is what's the kind of pipeline that you want. So there are like different pipelines that are available in transformers. So again, a question answering pipeline or a text classification pipeline, but we are interested in text generator, so we are kind of using that. Okay, so you can go to Google and search transformers pipeline, and there you can find like the different pipelines available, and or you can use like different pipelines, I mean of your choice. So these are like text classification, it would like give an output, so you can expand this and see like, so we have audio classification, automatic speech recognition. So all these pipelines are there, but we have focused on text generator. And in the meantime, you can see the shards have downloaded and now it's loading the checkpoint shards. So if you open this, your GPU will start filling. So this is loading the downloaded model to the GPU RAM. So you can see this. So as you can see, the total downloaded size is like 4.9 plus 5 plus this is also almost space. This is like 15 and almost more than 16 gigabytes. But once the model is downloaded, it's around this space. I think this will slightly increase, right? So it has taken like 5.6 gigabytes. So this is what we have done with quantization. So right, and then now we can create this pipeline. So text generator and say model is equal to model, this is the parameter, and pass the model. And you can also pass the tokenizer. Tokenizer is equal to tokenizer. So this we have already kind of loaded these things, and we have to pass this to the respective parameters of pipeline. And then max new token. So this is like kind of like the length of the output that you are expecting. So default, I think it would just return 20 tokens, but again, if you want a larger response, you can use like a larger number. You can also use like 256 or like 5212. So that's completely fine as well. So let's run this. So this is our pipeline. Now we will use this pipeline. Okay, unknown or text generator. Sorry, this should be text generation. Let's run this again. Okay, so this has created my text generation pipeline. Now I'm going to create a function called as get response, right? And say prompt. So this is the prompt that the user will be sending. And let's say sequence is equal to sequences is equal to text generator, which is the name of the pipeline that we have just now created, and within that you have to pass the prompt and then say gen text. Generated text is equal to sequences of 0 generated text. So I'm doing this because this is how the response from the model will look like. Return gen text. So when you pass this prompt to the text generator pipeline, right, which has the LLM, the Llama 3 model, it would return a dictionary, and that dictionary we have to look at, which is basically I would say the sequence. Sorry, not a dictionary but a list. So within this list we are taking the first element and finding like the generated text. So this would be the response. Maybe I can show you how this output looks like and later explain you this function. So here let's say the prompt that the user is sending is what is machine learning. Let's say this is the question and the model should answer this, and I'll say text generator and pass this prompt. Oh sorry, I have to run this. Let's store this in a variable called as response, and I'll copy this too. So let's see the output. So this may take a few seconds. And the other thing is like this is the base model, so this is not optimized for chat yet. So if you ask a question, right, so it's likely that it may not give you a very accurate response. We are seeing that what is machine learning. Machine learning is a branch of artificial intelligence that deals with development of algorithms and so on. So here we are seeing, right, and sometimes it's possible that you may not get this answer in a really good way, because as I said, this is not fine-tuned for chat. We also have this other variation called as instruct, as I told you. So that is like instruct is basically fine-tuned to understand instructions better. So that's again better if you're working with RAG task. Like let's say you have a document or you have a context and you want your model to answer from that context. So in those cases instruct would probably work better than a chat model. So again the point that I'm trying to make here is like don't expect like very accurate answers, because this is not a chat based model but a text generation model. But again for Llama 2 we have a chat based model, as we have seen, so you can use that if your application kind of is like completely like a chat based one. But yeah, this output seems to be fine. But okay, so this is how this would look like. So keep all these things in mind. So how this output is looking like is I have get a list, right, and this is what I'm doing. So in this sequence, in this response that I've gotten, I need to look at the first element. The first element is nothing but this, and this is a dictionary. So from this dictionary I want to get the generated text key alone. So when I pass this, so take the first element, get the value of this key which is generated text, this would output this what is machine learning thing. Okay, so that's the reason that we have created this function. So I'll move this prompt down and I'll delete this one. Now we can basically use this get response and pass this prompt and so on. So let's run this prompt and call this function. So here maybe I'll create a variable called as llama response, or I can call this as llama 3 response is equal to get response, and within that pass your prompt. Okay, and now you can print your llama 3 response. This will just give you the output that the model has generated. So you can just run this, or you can also print llama 3. Right, so you can kind of get this. So if you don't want this question that the user has printed, right, so what you can do is paste this and say you can just slice it. So length of my prompt and so this would remove that question, the prompt that we have sent, and this would display this. So this is how you can use the llama 3 model, load it from Hugging Face, and you can get a response. So how you can deploy this is, right, so That is a package called as Gradio, so that lets you deploy this as a API. So you just have to pass this function to this Gradio. You can maybe look into some reference, or later I'll make a video on that too. So you can get a API endpoint for that, maybe build a Streamlit app, and once the user has asked some prompt, right, you can pass that to the Streamlit app and get this response and display it there. But this is how you can basically access your Llama 3 model and work on it. So I hope everyone is clear until this point, and I'll just give you a quick recap of what we have done, and so that like it's really clear for you. So the first thing to do is make sure that you're signing up to Hugging Face and accept to the terms and conditions, and once you will receive a mail, or you can see this here, that you're you have been granted access to the gated model. So once you have this access, go to your account as I've shown you, get the access token, put it in a config.json file, and also give all this requirements.txt with all the proper version numbers and so on. And finally you can install the libraries and then import the required libraries, configure the HF account with the tokens, mention the model name. We have to do this quantization, which is like a critical part in this case, which is reducing the precision of the model so that we can work with a smaller model size without losing any performance or the efficiency of the model. Then you have to load the tokenizer from auto tokenizer, and load the LLM with the model name, device map to say that loaded to GPU, and so on. And finally you can create pipeline, text generation pipeline, and get a response out of this. Pass a prompt and you can get a response from this. So I hope this is useful, so please try this out. So this is like not complex at all, so you can try this with your application. Let's say you are working on some chat applications or like text generation applications, you can definitely try this model out. And the important reason being, this is like a open source model, as good as GPT-4 or Gemini Pro. If you're going with the GPT-4, right, so there is always going to be API cost that's going to be coming along with it. So but if you have a larger machine, you can host your Llama 3 model here and you can work on it. So that's it from my side, and I hope that this is useful to you. So subscribe to my channel for more videos on this AI, ML, Gen AI related stuff, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. In this video, let's understand how we can work with Google's Gemma using Hugging Face in Python. Google has launched Gemma as its open source lightweight LLM that the developers can use without having to pay for any APIs, or without the need for having a machine with a larger GPU. So Gemma comes in a smaller version of 2 billion parameters, and the other version is a 7 billion model. So this two models also has this the base version and also an instruct fine-tuned model. So in this video, let's understand how we can load this model from Hugging Face and how to use this for tasks like question answering, chat, or even this Python code generation. So this will be the agenda for today's video, and let's get started. So I'll open my Google Collaboratory, but this will work fine if you even have like a 4 GB NVIDIA GPU. So even you can quantize this model so that the size reduces further and you can use it as well. So first we need to install transformers and accelerate. So here I'm going to connect it to a GPU environment so that the response of the model is like faster, but you can also load it to CPU as well. So I'll run this. So I've already installed this library, so it's going to say the requirement already satisfied. And sometimes the transformers and accelerate, especially accelerate, would require you to restart your runtime. So I'll go here and restart the runtime once the libraries have kind of installed. So that's the first step. So now we can import the required libraries, and we have to get this Hugging Face token, and I'll show you how you can store that Hugging Face token in the environment variables and how you can connect to it and load the Gemma model. So I'll hide this input for now. So first I'll import OS. So as I said, this is used to store our Hugging Face token in the environment variable. So that's the first step. And next, import from transformers, import auto tokenizer and auto model for casual LM. And then we need to import PyTorch. So I'll say import torch. So these are the three libraries that we need for now. So the next step is, so this Gemma is like a gated repository. So if you open this in Hugging Face, right, so I'll say search for Hugging Face. maybe I'll first show you this in incognito. So when you search for Hugging Face and go to Google's Gemma model, we have to accept their terms and conditions. So I'll search for Google, and here we have this Google Gemma 7B, and then we have this Gemma 2B, right? So I'll maybe search Gemma 2 billion, and this iteration is the version that we are going to use. So I'll click this one. So Gemma 2 billion IT basically is the instruct version of the model. So as you can see, so this access Gemma on Hugging Face. So we have to kind of accept to these conditions in order to access this model. So once you're in Hugging Face, so once you're logged into this account, so you will see this button where you will request for access, and this request will be like approved like instantly. So you don't have to wait a long time like you have to do for like Llama models. So once we are in this page, right? So once you're logged in and once you kind of get this, permission in order to access the Gemma model, you can come to this part again, the 2 billion iteration, and we have to get the HF token, Hugging Face token. So on the right side, you will see this profile and go to your settings, and within that settings, you have this access tokens. So in this access token, we are going to create a token that we are going to store in the environment variable of this collab session. So I'll create a new token and call this token for Gemma. So you can change this, or you can just leave this as such. Maybe I'll just give this a read permission for now and generate a token. So I can copy this. So now I'm going to store this in my environment variable and say os.environ. And within the square bracket, you can say HF token, all should be in uppercase letters. So this is the place where the transformer library, the Hugging Face library, will look for the Hugging Face token. So paste this token over here and run this. So now we have to load our tokenizer from auto tokenizer and the Gemma model from this auto model for casual LM. So all this LM as their kind of have their own tokenizers. So let's load that first. So I'll say tokenizer is equal to auto tokenizer dot from underscore pre-trained, and within this we have to say this thing, Google slash 2 billion iteration. So you can copy it from here and paste it over here. So Google slash Gemma hyphen 2b IT. So this is like a unique string under this Hugging Face library to access like specific models. So we are importing this auto tokenizer from transformers, and from this pre-trained we are loading this Google Gemma 2 billion iterations tokenizer. So this won't take much time. So I'll run this. Auto tokenizer is not defined. Okay, I think there is a spelling mistake. So let's paste it here and run this. Okay, so this will load the tokenizer and save it to the variable called as tokenizer. So the next step is importing the model itself. So when you run the next line of code, it's going to download the model from Hugging Face. So I'm going to say model is equal to auto model for casual LM. And within the parentheses, I'm going to pass some parameter. First is the name of the model. So the name of model is like what we have copied here, Google Gemma 2 billion and instruct version. So you can also work with the raw version itself. And then torch data type is going to be, let's say, a 16-bit data type. So this is again specifying like how the precision of the weights should be. And in the device map, you can say auto. You can also say CUDA, but if you have a GPU, right, when you say auto, it's going to work with the GPU that you have over here. So that's the parameter for this. If you don't mention the device map, it will by default load it into the CPU. So when you do that, your inference and your text generation will take a lot of time. So that's something you can keep in mind. So we are creating this variable called as model and loading this Google's Gemma 2 billion instruct model from auto model for casual LM, mentioning the data type. So it's a torch, floating point of 16-bit, and the device map is auto. So to make sure that the model is loaded in the GPU. So it says it's designed to be instantiated using auto model pre-trained or auto model. Okay. So let's see what's the issue over here. Okay, so I have to say dot from pre-trained, similar to what we have done over here. So I'll copy this and paste it. So these are the pre-trained models, right? The Llama, Gemma, and other models. So as you can see, this is downloading the model. So this would be about, yeah, as you can see, 5 GB. So when it's installed, you can see that your GPU RAM will be filled by about like 5 GB or something like that. So if it's kind of getting loaded into your RAM, so you will see that your system RAM will increase. So this part is downloading the Gemma model and loading it to your GPU. So let's in the meantime it's getting downloaded. Let's move to the other aspects. So let's say that now we can ask a question to this model. So I'll say input text. So input text is equal to, I'm going to say, this is like given in the Hugging Face documentation itself for this model. So I'll ask the same question as, write me a poem about machine learning. Okay, so you're seeing that your model is getting loaded. So this is the part where it shows like once it's downloaded, it will load the model shards to your RAM, or basically your GPU or the CPU. You can ignore this activation function warning, so it's like not a big deal. So here I'll say write a poem about machine learning. So this is the input text. So now we have to convert this input text into tokens, pass it to the model, and get a output from this. So I'll run this, and here I can say input IDs is equal to tokenizer, which is the tokenizer that we have loaded, and within this I can pass input text comma return tensors, like what you are basically seeing here, is equal to PT. So PT is nothing but I am going to take this input text, convert it into tokens, and return it as PyTorch tensors, and then I'll say dot to CUDA to load it in the GPU itself instead of the CPU. So let's run this. So this will convert the input text into tokens that the model is going to take. So this is the prompt that we are sending, and I'll create a variable called as outputs, or you can even call this as like a response. Maybe let's call this as a response. So response is equal to model dot generate, and within this I'm going to pass all the tokens that we have over here. So I'll say input ID and then max new tokens. So max new tokens is like what's the size of your output is going to be. So what's the maximum token size of your model's response. So I'll just take like maybe a larger token size of 512, and later I can print this output. So for printing this, maybe let's run this. So this will give you the response. You can print and see this response over here. Here you can see your GPU RAM is filled like 4.9 GB, which is the size of the model that we have downloaded. So we have got this response, and you're seeing this as like this tensor, right? PyTorch tensor. Now we have to convert this response into a proper natural language text. So a human readable text. For that I can say output is equal to tokenizer dot decode, and within that I have to pass response 0. So you can maybe leave the other things as such, and then print output. So the question or the prompt that we have asked is write a poem about machine learning. So here you can see this. So this is the beginning of the string, and this is the end of the string. Basically like the special tokens to say that this is where the thing begins and this is where it ends. So we have asked it to write a poem about machine learning, and we kind of get this as the response from the Gemma model. So this is how you can send a prompt and get a response from it. So the next thing that we are going to see is how you can use a chat template and pass it to the model, and you can get an output from it. So here we are going to set a template for the model to write a program, and then we are going to send that prompt template to the model and get a response, and then like process that to get this Python code alone. So that will be the next step. So here I'll maybe create a text cell and call this as chat template. So this is used for generating Python code in this case, but it can be used for anything. So you can like kind of create this custom templates, later replace that as well. So that's possible too. So here I'll create a variable as chat, and this should be a list, and within that I'm going to create a dictionary kind of a thing and say role is user. So the user is going to ask the model, content is going to be write a Python program, let's say to print hello world. So this is like the simple thing that I'm asking the model to do. Let's see how it is performing. So this is the chat that we have. And then I'm going to say prompt is equal to tokenizer dot apply chat template, pass the chat, tokenize is equal to false, and add generation prompt is equal to true. So let's understand this. So basically the chat or the template that we are sitting here is write a Python program to print hello world. So here you can maybe write a template such that every time you call this is something the user gives. So it can be Python or it can be a different programming languages as well. But for now, let's say that it's a Python program that we are interested in. So we are creating this chat template and using this tokenizer dot apply chat template and passing this chat variable that we have created, which is basically a list, and saying that tokenize is equal to false. So this is nothing but, do you want tokenize the prompt that you are sending the model? So here we are setting it to false, and add generation prompt is equal to true. So that means it is like kind of a signal to the model saying that you need to generate this particular thing. So it's for that purpose. So here we are setting that to true, and we are just saying that if that prompt should be tokenized, so like we don't need that. So this is what we are setting it here. So I'll run this, and the next step we are going to get the output from the model. So I'll say this input IDs, or basically the inputs is equal to tokenizer dot encode prompt comma add special tokens to do this padding and other things is equal to false, and return tensors. So the output is returned as PyTorch tensors, and let's say this response is equal to model dot generate. Model is where we have loaded our 2 billion instruct model, and pass your input ID is nothing but your input dot to CUDA. So you can do that here as well. So that's possible too. Maybe let's do that. So 2 in parenthesis say CUDA. So here you can just pass this inputs. Even you can call this input IDs as well with the same name. So that's good as well. So I'll copy this and paste it over here. And same thing, max new tokens, right? So what we have passed here, so we know that it's going to be a shorter program. So I'm just going to go with lesser tokens. Max new tokens is 512. So here, instead of just sending the prompt, we are applying a template. So using this tokenizer dot apply chat prompt, passing the chat template, and then we are tokenizing this prompt, setting this like parameters of whether we have to add the special tokens, and mentioning that the output should be a PyTorch tensors, this PT, and we are storing this to CUDA, or basically the model is in GPU, right? So we are making sure that the data that we are going to send is in that same format as well. So, and then response is equal to model.generate, pass your input IDs, which is basically your tokenized version of the prompt that you're creating. So pass your input IDs or your input tokens, and mention the max new tokens. Maybe I'll call this 50 because this program is not going to take a lot of tokens, right? It's like a smaller program. And finally, I'll say output is equal to tokenizer dot decode response of 0 and print output. Let's see if it works properly. So here you can say we have this beginning of string, start of turn, user. So user is nothing but it's mentioning that this is the question asked by the user, and then you have the start of turn for model. So this is the turn of the user. So here we mentioned like what the user has asked, and it's model's turn. So we are saying that start of turn for model, and we are giving this Python code. As this is a Python code, this as the substring of this, this 3 symbols, and then we have Python. So we can use this in order to extract this Python code. So here we have this explanation. So here it's kind of cut down because of the lesser tokens that we have. So this is how you can generate Python codes. But now let's kind of ask like a model to write complex code, like let's say training a logistic regression model, and see how we can extract this code. So here I'll do the same thing, just I'll change this prompt, and the next thing is this prompt thing. And then we have the response, and finally we are extracting this to output, and let's print it. Let's see if the model is able to give like a decent code for this. Let's run this. Okay, so I have to increase the size of 512 and change this prompt to, something like write a Python program to train a logistic regression model, and run this. So we have changed the prompt and increased the output tokens to 512. So you can see like the occupied RAM. Again, as I said, if you do this quantization, even the model will be stored like 2.53 GB. So that's other thing that you can try. So here we have the output. So the user turns as write a Python program to train a logistic regression model. So end of turn, and then we have the start of turn for the model. So it has like given the code, and it is also kind of explaining the code. So what we are interested in is this Python code, right? So we can use this as the start and the ending marker. So these three symbols, and the starting would be these three symbols in Python, right? So we can use this in order to extract the code, and maybe you can work on something like once you extract this code, you can execute that and show the results to the user. So let's say the data is going to be data.csv. So the user is uploading a file. So you have a Streamlit user interface, and the user is uploading a file, and you can rename that to data.csv and ask the model to say that data.csv is the file name, and for that write a code to train a logistic regression model. So the model will return this code. So you can extract this code from this entire text, run that, and train a model, and maybe display the accuracy, its performance, and so on. So that's other thing that you can try, but I'll just show you how you can extract this piece of code alone. So for that, you can use a simple regular expression in order to extract this code using a pattern. So here I'll say response. So we have this output, right? So output is saved in this output variable. So here I'll say pattern is equal to re.compile. So here we are going to set the pattern, and maybe I can also create a start pattern. So start pattern is equal to r, and within this quotes I can mention this as my start pattern. So this is how the start pattern is always going to be when I ask it to generate a Python code. So this will be my start pattern, and my end pattern would be, you can also use some special tokens to mention like where the code ends and starts as well. So here I'll copy this and paste it. So this would be my end pattern. So say re.compile rf start pattern dot. So this is like a standard regular expression pattern matching code. So here I'll say in pattern re dot all, and next I'll say match is equal to pattern dot search your output. So basically this pattern is what we have mentioned here. So this will search if this pattern is present in the text that we are going to pass. So the text that we are passing is output, so it will check for that pattern in the output. So next I'll say if match. That means if a match is found, then let's put this in a substring. Substring is equal to match dot group, or maybe instead of substring you can say Python code, because that's the Python code that we are generating. And we are going to strip off any spaces, and then print your substring. So if we don't find a match, if it's not working, if this matching thing is not working, we are going to say no match found. Okay, so this is nothing but a simple way of kind of mentioning the start pattern, end pattern, capture everything that's present between them, and printing it over here. So I'll copy this and paste it, and let's run this. So this should give me the Python code alone. So here you can see it's giving like only the Python code that has been mentioned here. So this is what we are doing. So once we get the response, we are using a simple regular expression code in order to match a pattern with the start and end pattern, and then we are extracting the code. Again, the purpose of this is you can have a sandbox kind of environment where you can run this Python code and show the output to the user. So that's it for today's video. But before signing off, I'll just give you a quick recap of what we have done. So this video is all about using Google's Gemma, which is a lightweight model, so that we don't have to kind of own a large machine to, get this experience working with the LLMs. So we are going to use Transformers Hugging Face library, and we are like importing all the necessary libraries. And the important step is to get the Hugging Face token and store it in the environment variable of HF token. And then we are loading the tokenizer and loading the model using this auto tokenizer and auto model for casual LM. And then we are having this input text, tokenizing this input text with the tokenizer that we have downloaded for Gemma. And then we are converting this final output into the human readable text, the natural language text, and printing it over here. First we have asked a question of write me a poem about machine learning, and we get a response. And then we are using a chat template to mention that this is the thing that the user is asking to write a Python program to print hello world or something like that. So we are kind of doing all those, so passing this prompt template to the tokenizer, and then like eventually to the model to get the output. And we have also seen how we can extract this Python code alone with some starting and ending pattern matching. So I hope everyone is clear with this video. This is like a simple concept, and using this you can like build more complex things like a rag or a graph rag or something like that. So you can definitely try that out with this smaller LLM. So I hope this is useful to you, and I'll see you in the next upload. Thanks for watching. Hello everyone, I am Siddharthan. In this video, let's discuss how we can deploy large language models as API using Gradio. So Gradio is a very useful tool that helps you deploy LLMs for prototyping. So let's say that you are working with open source models like Gemma, Llama 3, Llama 2, and so on. So some of these models are pretty large, and let's say that you want to host this in Google Collaboratory or even some other environments. So there you can host these and expose these LLMs as API. And let's say you are working on a Streamlit app on your local machine, so you can integrate the Gradio API in your Streamlit app, so that you can work with these LLMs hosted in some environment that has the capacity of, let's say, 12 GB GPU or a 15 GB GPU, and you can connect it with your local system that doesn't have like that much of capacity. So this is the application of Gradio, which is mainly to deploy these LLMs as APIs and to integrate them. So in this video, let's clearly understand how we can load this Gemma 2 billion model in Google Collaboratory and expose this as Gradio API. But this process is same if you are working with LLMs like Llama 2, Llama 3, or any models from Hugging Face for that matter. So let's get started. So here I have my Google Collaboratory open, and I have connected to a GPU runtime. So here you can go to this runtime and change this runtime to GPU, so that your model is loaded in the GPU, such that when you're asking it some questions, so you get a response quickly. So here we have connected it, and I've installed three libraries here. So I did a pip install for Transformers, which is the Hugging Face library, using which we are going to import the tokenizer and the model for Gemma 2 billion instruct model. And then we have this accelerate. So this accelerate is kind of an optimization library that helps us to load the models in a optimized manner in the GPUs. So some machines has like multiple GPUs, so there can be like 8 GPUs. So when you use this accelerate, it makes this process smooth of loading, or loading this model in a distributed way across all these GPUs. So accelerate is also required. And then of course we have this Gradio library in order to deploy the LLM as API endpoints. So these are all the three libraries. So here I have already installed these things, so you can do the same as the first step. So for now I'll just hide these inputs and create a text cell and call these as importing the dependencies. So this is the first step. So first I'm going to import OS library. So this is used in order to access some files, and this is also used to save the API keys in the environment variables. So that's the purpose of this for us, and then I'll say from transformers import auto tokenizer, and so that is the one model that we one module that we need, auto tokenizer and auto model for casual LM. Okay, so this is for the language model. So a lot of pre-trained models are available here, and then we need torch. So PyTorch library, let's import Gradio later. So first let's understand how we can load this Gemma 2 billion and generate some text out of this. And this Gemma is kind of a gated model. So that means you have to accept the terms and conditions, and later you will be having access to this particular model. So you need to accept these conditions, and then we will get the access tokens from the Hugging Face. So this step is not complex at all. So all you have to do is first locate the model that you want to use. So let's say that you are going to use Llama 2 or Llama 3. So you just have to search for that model here. So locate that particular model. So in this case, when we are using Gemma, right? So here you will see a checkbox asking you if you are going to accept the condition. So once you do that, after some time you will receive mail stating that you have been given permission, and you will see something like this. So you have been granted access to this model. So this is all done. Now using this account, we have to get the Hugging Face access token. So for that, go to this top right corner. So this is your profile icon. So once you click there, you will find this settings option. So in that settings option, in the left navigation, go to access token. So here you will see this Hugging Face token. So you can like create a new token or kind of like refresh the previous token that you have. So here I'll copy my tokens. If you don't have any tokens, you can always create new token here. So now I'll come back to the code that we have over here. So the next step that we are going to do is save this in our environment variables. So I'll say os.environ, and in square brackets I'm going to say HF token. So all should be in uppercase letter. So when we kind of load this model from auto tokenizer, the tokenizer, and the model from auto model for casual LM, it will look for the Hugging Face tokens in this particular environment variable. So that's why we are passing it over here. So this name shouldn't change, so it should always be in this uppercase letter. And here I'll paste my Hugging Face token. So this is not a recommended way. The best approach would be to save this in a config.json file or in a .env file and load it, so that our tokens and the API keys are not like deliberately present in the code. So that's one thing you probably have to remember, but just for demonstration purpose, I'll just like put it over here and I'll run this. So now I'm going to say tokenizer is equal to auto tokenizer, the module that we have imported, and within this brackets, or before that I should say from pre-trained. Okay, some pre-trained, we have to pass the model name. So for this, what I'll do is create a variable and say model name is equal to, so that you can copy from Hugging Face. So here you are seeing this right, so Google/Gemma 2 billion IT, which is the instruct model. So copy it from here and paste it. So this is the name that we are going to use, and paste this model name over here. So here we are going to load the tokenizer for the pre-trained model Google Gemma 2 billion instruct. So let's run this. So this will load the tokenizer in this step. So the next step will be loading the model. So this is the tokenizer for this Gemma 2 billion instruct. Now we have to load the model itself, the LLM itself. So for that we have to say model is equal to auto model for casual LM, and within that we are going to pass some parameters. Again we have to say dot from pre-trained. Okay, so and then I can say here I'll pass the parameter. So the first parameter would be the model name, and the next parameter is torch d type, the torch data type. So let's say that the torch data type is equal to torch dot b float 16. So we are going to make it as like 16-bit values, and then I'll say device map is equal to auto. So you don't have to pass the Hugging Face token because we have already saved it in the environment variables. So let's first understand what we have done here. So here we are using this auto model for casual LM function. So from pre-train, we want to pull this particular model. Maybe I'll run this as this may take some time. So here we are like loading this model, and then we are specifying the data type. So the torch data type. So the data type for the tensors, or basically the weight for the model, is going to be 16-bit floating points. So the reason we are using this is like we have this concept of quantization. So the model's precision, the parameters precision can be reduced so that the size of the model can be reduced. So let's say that for example, right? So here we are using a precision of 16-bit. So the size of the model is 4.95 GB. So if you are using a 4-bit precision, that's going to reduce the model size. So in that case, the Gemma 2 billion model will be like 2 GB in size. So if you have smaller GPU, you can use this concept of quantization, so that your model is reduced. Again, you will see a reduced or a decrease in the performance of the model, accuracy of the model, but it's kind of a trade-off that we have to do between the performance of the model and the hardware that we possess. So we have to do this quantization. So here we are doing a 16-bit quantization. So the floating point is going to be 16-bit. So this is kind of a decent number that doesn't kind of reduce the performance by a large factor, but it kind of reduces the size of the model by a fair amount. So here we have done that, and then device map is equal to auto. So this will automatically load the model in the GPU. That means like you don't have to say that I have 4 GPUs, so distribute in a distributed way, load the model in all these 4 GPUs. So you don't have to say that. So it will automatically do that. But in our case, it's just a single GPU, so it's not an issue. But if you're using like, let's say, a large instance or easy to instance with like 8 GPUs, 4 GPUs, in that case, you can go with this device map of auto. So here, when you open this, here you can see that the GPU RAM is filled with 4.8 gigabytes, right? So that's nothing but the model that we have loaded. So this is the next step, which is loading the tokenizer to this tokenizer variable, and then we are loading the model to the model variable. So now we are all set. So we have the LLM. So the next step is we are going to pass it some text and get a response. So here I'll maybe call this as invoke the LLM. And let's create a variable called as input text, and let's say write a poem about machine learning. So this is what we are asking the model to do. And now we have to pass the model. So we won't pass it directly because the model won't be able to answer it. So we have to convert these into tokens and then pass it to the LLM. So here I'm going to say input IDs. So input IDs is equal to tokenizer input text. So here we just have to say dot to CUDA. Let's understand this. So this is in the form of text, right? So this text will be converted into tokens, which is nothing but it will be chunked into smaller pieces, and we will kind of assign some tokens or like IDs to these texts, so that we are passing this numerical values to the model. So that's what happens in the tokenizer, and for this purpose we are loading the tokenizer from this auto tokenizer. Again, each LLM would have like specific tokenizers, and here we are passing the input text which needs to be tokenized, and then return tensors means, so all these outputs, so the output that's coming from the tokenizer, so this input text will be converted into tokens, and the output format will be PyTorch tensors. So that's what PT means. And then we are moving this to GPU using this CUDA. So that's what this particular line of code does. So it takes in the input text, converts it into tokens, and the output format is going to be PyTorch tensor, and we are moving it from CPU to GPU using this dot to CUDA. Okay, so that will be the next step. So here you can maybe try and print this input IDs. So you have this input IDs, tensors, and so on. So this is the data that we have, and then we have this attention mask. So now we can pass this to the model, get a response, and then kind of decode it. So now let's say that our text has been encoded using this tokenizer. So once we get a response from the model, we will later kind of decode it. So here we can say response is equal to model.generate. Here we can say like double asterisk symbol input IDs and max tokens, max new tokens. is equal to, let's say we want 512 tokens. Let's understand this. So we are calling this model.generate, and then we are passing this asterisk thing input IDs. So this particular thing, this double asterisk that we have used, right? So this is used to unpack a dictionary. So here we have a dictionary that has this input IDs and attention mask. So we have like two key value pairs. So this unpacks and passes these key value pairs directly. So instead of like passing this as a single dictionary, this will pass input IDs, this tensors, and then like attention mask tensor value. So this is what it does, and this is the format in which the model expects the data to be as well. And max new tokens basically represents what's the number of tokens that you need in your output from the LLM. So that's the parameter max new tokens purpose. So now we have this response. I've ran this particular cell. So we call this model.generate, pass the input IDs, which is nothing but the tokens that we got from this particular text, and the model has responded to it. Now I can just say response. Let's see how this response is looking like. So here we are not seeing the text, but we are just like seeing some random numbers. This is nothing but the response given by the model is also in the form of tokens. Now we have to decode it. So you can think about this entire process as, first you are getting an input text. This input text has been kind of encoded to tokens. We are sending it to the LLM, which is Gemma in this case. So the model tries to understand this and generate the output for this, which is in the form of tokens as well. Now we have to decode this tokens back. So for that we can say output. So let's store this final thing in this variable called as output and say tokenizer dot decode response. You can skip the special tokens if you want. Maybe we can try that. Skip special tokens is equal to true, and finally we can print the output. See, so we have this write a poem about machine learning, machines, they weave a web, and so on. So basically we got a output. So this is how it works. So we add this tokens as the output, and then we are kind of decoding it. So if you don't include this special skip special tokens, right? So what would happen is, maybe I'll show this to you. Let's remove this. So here you have this BOS, which is beginning of a statement, and EOS, end of statements. So all these special tokens will be removed when you use skip special token. So this is like a good thing to have. So here we are getting the output. So this is the question that we have asked, and then this is the response that we are getting over here. So yeah, so this is how you can load a model from Hugging Face along with the tokenizer and get a response from this. So this is about it. The next main step that we are going to do, which is the purpose of this video, is how we are going to now serve this particular LLM as a API using Gradio. So that will be the next step. So in order to use this Gradio, we need a Python function. So in this case, what we are going to do is, here we have loaded the model, right? And after that we are passing an input text, doing all those conversion using this tokenizers and decoding this, all those things are present, right? Now we have to put all those things in a function and then later pass this function to the Gradio code. So that will expose that particular function as API. So let's see how we can do that. Let's maybe call this as deploy LLM with Gradio as API. So here I'm going to say import Gradio as gr. I'll also import JSON library. I'll tell you the purpose of this a bit later. Now let's create a function. So we have already installed Gradio library, so that's fine. So here I'll create a function and call this as get response, and the input parameter will be input data, which is going to be a JSON, which is like a preferred data type to send to the model. So here let's say that we have this input data is equal to JSON.loads input data, and then input text is going to be input data. Let's use a key called as query. So I'll explain you about this in a minute. And then we have this tokenizers, input text, and so on. And finally we can say response is equal to so all these are good, and finally return output. So let's understand this function. So this function is going to take a JSON object as an input, right? Because it's better to pass JSON objects in the API. So we are going to do that. So this input data will be a JSON object, and then we are converting this JSON object into a dictionary using this JSON dot load method. Okay. So, and then we are extracting this particular query. So let's say that we are passing this as the key will be query, and then we would ask a question like write a poem about machine learning and so on. So we are getting that exact input text and then converting this input text into tokens, getting the PyTorch strings as output, moving it to CUDA, all those steps that we have discussed previously, and then we are passing this to the LLM, getting a response, setting the output size that we want, and finally we are decoding the response after like skipping the special tokens, and then the output that we are sending is a dictionary that has a key as output, and the value is nothing but the text that is generated by the model. So this is the function. So now we have all the code that we want. So now I can say demo is equal to gr.interface. Gr is nothing but Gradio, the thing that we have imported, and we are going to pass this function is equal to get response, and then inputs is going to be JSON, and the output from this Gradio will also be JSON. Okay, and then I'll say demo.q dot launch, and within this launch I'm going to say share is equal to true, debug is equal to true, and show errors is equal to true. Let's maybe understand this first. So here we are using this gr.interface, Gradio.interface, and here we are passing this function which is get response, and then we have this inputs is equal to JSON and outputs is equal to JSON. So this is telling the Gradio interface that I'm going to send you JSON as input, and you're going to send me again JSON as output. So this output will be processed in the part where we are going to invoke this Gradio API thing, and then we have this demo.q. So actually you can skip this queue, but the thing is when the API is taking more than a minute, right, so it's going to stop invoking that endpoint. So when you're calling a process and you're sure that it's going to take more than 60 seconds or 90 seconds, I'm not very sure about the limit, but you can check that out. So in those cases you can use this queue so that it kind of waits a bit longer for basically this particular code to give you a response, so the model to give you a response. And then we are using this share to kind of generate a URL for our API, the endpoint for it, and debug is equal to true, show is errors is equal to true. So when we kind of pass these parameters, when there are some issues, we will also kind of display these errors so that it's easier for us to debug. So this is all the things that we want, and now I'll run this. Okay, so got an unexpected keyword, show errors. Okay, so this should be show error without an yes. Let's run this. Hmm. So running on public URL. So this is the URL that you can use. So basically it's like anyone can use this from remote as well. So you can open your PyCharm, run a code in your local, and invoke this API as well. So that's doable. So here you can maybe like pass a JSON, get an output, but we are not interested in it, interested in this particular user interface. Rather, we are going to use via API. And here you can see how you can invoke this via JavaScript or even like Bash and so on with curl, basically in the form of this endpoints. But we are interested in Python. Let's say that you are building a Streamlit application and you want to integrate this API with that Streamlit application. Like, you can do that. So now all we have to do is, let's say we go here. This is the base codes. We just have to make like slight changes to this. So first we need to install the Gradio client library. So here I'll say pip install Gradio client. So the client version, by the time that I'm making this video, is 1.0.0. So I'll use that, and then I'll import JSON and Gradio client. So I'll say from Gradio underscore client import client. So this C should be in uppercase. Okay, so let's wait for this to complete the installation. So JSON is used in order to convert this dictionary that we are going to create into a JSON object, because that's what our function is also expecting. So here I'll just hide the output and let's run this. So now we have to pass the URL. So okay, I'm getting some issues. Oh, there is a typo. So URL is equal to come to your collab and copy this. Again, it's not like you have to work in collab, so you can also work on your local or any environments. So I'll copy this URL and say input, let's say text is equal to the same question, or even you can like use a different one, or we can directly create a dictionary. I'll say input data is equal to create a dictionary. The key should be query, because that's what we have addressed over here. So the key should be query, and then I'll say what is a LLM, right? And let's convert this to JSON. Input data underscore JSON is equal to JSON dot dumps. So this is the function to convert this dictionary into a JSON object. So let's run this, and then we can pass this URL to the client. So I'll say client is equal to this client with uppercase C, which we have imported, and then pass the URL parameter, the Gradio URL, and run this. So your API will be loaded here. As you can see, you can ignore the warnings for now, so that's not an issue. And finally, we can say result is equal to client dot predict input data JSON. API name is predict input data JSON, which is a JSON object, and then we have this API name as predict. So that is all. Let's run this. So we have successfully called our Gradio API, and now you can just say print a result. So it will be in the form of a dictionary, right? So output this thing. Maybe you can check the type, whether it's a dictionary or a JSON. It's in the form of dictionary, which is like processed here. And then if you want to get only the output, you can just say print result, and within this you can call this output. Let's run this. So the question is, what is LLM? And it says large language model, or LLM, is a type of AI that has been trained on a massive data set of text and code. Okay, so this is how you can call this API client. So what you can do is put all these things again in a function, and let's say that you are building a Streamlit app, and you can call that function in that Streamlit app. If you are, let's say, building a chat application or a RAG, right? So retrieval augmented generation. So all this can be done where you're hosting this LLM. So this is, like, as I said, very useful when you are doing a prototype on something and you don't have like this large machines on your PC, right? So, or large GPUs on your PC. So instead you can just use Collab to load the models like Llama 2, Llama 3 and so on with some quantization, and you can deploy this. So even you can follow this same process in SageMaker notebooks that are present in AWS, where they offer like this large GPU. So you can do that there as well. So these are the steps. So the only drawback is this share link expires in 72 hours. So they have given this, right? So when you keep this running, so this URL will explain in 72 hours. So here they have also given this option for permanent hosting, GPU upgrades, and so on. And the other alternative for this is, right, so let's say that you have some storage spaces like a S3 bucket or a storage account in Azure. What you can do is, once you generate this URL, you will be able to extract this URL alone. So you can store this URL in a text file, put that in a S3 bucket, and while you're calling this, right, you can load that particular file load the URL in that file, and you can run this so that you don't have to replace this particular URL every time that you're running. So this process will be automated. So once we generate a URL with Gradio, so it will be automatically stored in a particular file in S3 or storage account, and here you will automatically call that file and extract that URL from there. So this is like an alternative for this. So this is how you can deploy this LLM as APIs using Gradio. I know that this is a very simple and easy process to do. So please try this out. I'll just give you a quick recap of what we have done. So the first step is installing all the libraries, transformers for loading the tokenizers and the model, accelerate for easier loading of models in a distributed way to the GPU, and then Gradio to deploy it as API. We are importing all the libraries, and the important part of storing the Hugging Face tokens in environment variables, and then specifying the model name and loading the tokenizer as well as the model. And here we have seen how we can give a text, convert it into tokens, and generate the output from the model and decode the token. And how you can basically put all these things in a function and create a Gradio interface and deploy that as API, and you will get a URL, and then you can just simply call this URL using this Gradio client. Again, if you want to use bash, basically curl or even JavaScript, you can follow the code that's present over here. Okay, so that is all from my side for this video. I hope that this is useful to you, and I'll see you in the next upload. Thanks for watching.
Hello everyone, I'm Siddharthan. In this video, let's discuss about retrieval augmented generation, more commonly known as RAG or RAG. So let's first understand what is a large language model and what are the limitations and how RAG can help in solving those limitations and help us build a better application with a large language model or a LLM. So this will be the agenda for today's video, and let's get started. So we know that there are like a lot of LLMs today. So we have ChatGPT by OpenAI, which came first, and then we have Gemini by Google, and then we have Llama family of models by Meta Facebook, right? So we have Meta AI, and first they have launched Llama, and they have launched Llama 2 with 7, 13, and 70 billion models, and recently they have launched Llama 3 with 8 and 80 billion, and they also said that Mark Zuckerberg said that they are also training a 405 billion Llama 3 model, which is like pretty huge. So basically, a large language model or a LLM is a AI model, and this AI model is designed to understand and generate human-like text. So we have these models like ChatGPT, which is based on GPT-3 and GPT-4, and even Gemini Pro and these models. So they are trained on vast amount of text data, and this kind of helps them to understand the patterns and relationships and a lot of nuances in the human language. So once these are trained, we kind of can use this in order to for purposes like text generation, question answering, and so on. So we would have a LLM, and the user would give a query, more commonly known as prompt, and based on the data that it has been trained on, so it would give a response. So you can just go to a LLM and ask, like, let's say, what is machine learning or what is deep learning. So it is already trained on a vast amount of data, and based on its training or its learning, it would give you like a response saying like what machine learning is, right? And then there is like a bit of limitations to this LLM. So let's say that I mean we have this prompt and we kind of ask this question to this LLM, and it gives a response, right? And I've told you that this response is based on the training data on which the LLM is trained on. So what if the user has asked a query or a question for which the LLM doesn't know the answer? Think about this situation. So let's say that you want to kind of ask about a thing, or let's say your company's policy or something, but the LLM doesn't know this, right? So when there is like no source for the LLM to answer, so in that cases it can definitely not answer your question, right? So when there is no source data, or the data was not present by the time the LLM was trained, right? So in those cases you won't get the answer for those queries. And then there is this out of date information. So let's say that you are asking a question about a particular library in Python, and during that time, let's say the library was in a different version, and later, like let's say the version has changed, now the LLM won't have this updated information, right? So these are few limitations. So not just for versions, but for any general questions too, if the information has been updated but the LLM doesn't have access to that updated information, then in those cases it's going to give a response that is not accurate, right? And it also tends to hallucinate when it doesn't know the answer, so it kind of tries to make up some answers. So these are some limitations, and the framework called as retrieval augmented generation. So this augmented memory that we are going to give the LLM is going to help us solve these issues. So that's where RAG, or this retrieval augmented generation, comes into play. So let's say that we have a prompt, and we are going to ask this prompt to the LLM, and we are going to give a response. But let's say that we know that LLM may not have an answer for that because it is like a more specific question. So let's say that, or it can be also a situation where you have a custom document. So again, it can be like the legal document for your company, or anything for which the LLM doesn't have access to. So let's say that you are going to ask question from this particular document. So let's say that it's an 100-page document and you don't have the time to go through it. So you're kind of using the LLM to answer it. So in those cases, we know that there is this limitation in the original LLMs. So what we do is we take this context, or let's say a document in this case, we use a retriever to pass this kind of information, this context, to the LLM, and we add like some custom instruction to this. So this custom instructions can be saying the LLM that answer this question, but answer from this document, don't make up the answers. So we can give these instructions. So based on these instruction, now the LLM will kind of give a response. So this is basically the application of retrieval augmented generation. So I hope everyone is clear until this point. So the main idea here is it's kind of helps the LLM, or enables the LLM to answer a question not based on the corpus of data it has been trained on. So we have this training data, right? So instead of answering the question based on this corpus of data, it's going to answer from the context that we are going to provide. And for that, we have this framework for this retriever, and we add some custom instructions and so on. So this is the base concept of retrieval augmented generation. So if you are clear until this point, now we can go ahead and discuss about the architecture of a retrieval augmented generation framework. So this is like the image that kind of explains this in a clear way. So let's say that this is the application or a chatbot that we are building, and the user is kind of asking a query to it. So that this is like the first step that happens. So the user is asking a query, but that is based on a document. So this need not be a document. So this can be an article in the internet that has the latest information. So it can be that too. So in this case, let's consider this document for simple understanding. So the user is asking a query from this document. So let's say that that is a legal documentation, and the user want to get a particular information out of this. So now what we would do is, this document is split into multiple chunks. The one way to do is you can copy the entire content, put it in a chat GPT, ask the question. But if the document is long, the text is long, then you're not going to kind of you won't be able to ask that question, right? Because the input text is like too long. So this kind of solves that problem, and this is better in kind of retrieving that specific information from the document. So what we would do is we take the document and we kind of create like multiple smaller chunks of this document. So once you have that chunk, an important aspect of this retrieval augmented generation framework is that a embedding model. So we use a embedding model in order to convert these text chunks or the document chunks into vector embeddings. So once we do that, so we save this vector embeddings into a vector DB. And what happens is we have the user query, right? So this query is also fed to the embedding model, and this is also kind of converted into vector embeddings. So you have the documents, you are chunking those document pieces and embedding it, and also you are querying, you are also converting this query into a vector embedding. So once we do that, what we are going to do is we are going to find a close match. So these are vectors, right? So we can just do a similarity search or a nearest neighbor search and find the information. Let's say that the user is asking a query, and let's say we have 10 chunks, and let's say the user's query, we can run a similarity search and find that 8 chunks. So out of let's say the document is in 10 chunks, and the eighth chunk as the response for this query. So now we are going to feed that to the LLM. So this is how this would work. So that's why we are also embedding the query. So you have two vectors. So we have the query vector, and we have like different vectors of these chunks. So we put these two things in the embedding models, save that in the vector DB. And once we get this information, right, so what would happen is you store this vector embeddings of these chunks in the vector DB, and you also store the text of those chunks. So let's say that you have this chunks. So the chunks are in the form of text in the first place, so you save it in one place, and these are converted into vector embeddings, and those are saved into vector db. And you also have the pointers for a vector embedding to the text, right? So let's say that we have a chunk one, and we have the chunk one text here, and then we have this pointer that points to it. Maybe I can just take a pen and explain it to you. So we have this chunk, and the text of this chunk is saved in a db or somewhere, and then we have a pointer, so let's call this as p1. So this pointer kind of points to the vector embedding of this chunk, so let's call this as embedding c. So let's call this E1. So similarly, you have this E1, this is stored in this vector DB. So similarly, all those 10 chunks are stored as E1, E2, E3, and so on. So all these vector embeddings are saved. Now we have the pointers. So for a text, you have a pointer that points to this embedding. So now what we would have is, so we have this query embeddings, right? So let's call this as Q. So Q is nothing but, or we can also call this like QE, which is the embedding of the query. Now we try to find the similar, let's say not similar, but like what's the nearest vector for this query. So you have 10 embeddings, and let's say that you are kind of doing a similarity search and find that the chunk 8 and 9 are similar to this question. So that means like that is the answer for this particular query. Now let's say we have this E8 and E9. Using the pointer we get the text. So you start with a query, and you start with a larger document, and once you do this chunk, you finally do a search, similarity search with these vectors, and you finally end up with the actual text based on the pointers that you have. Now you have this text, right? So we can just call this as t. Let's say t represents the text, so we have t8 and t9, which let's say which is the answer for the particular query. So these are not in vector embeddings right now, because we are using the pointer, we have extracted the text. Now we get the query's text, so let's call this as q t. So it's the actual query. So let's say that the user is asking some query, we pass that query as well as this text to the LLM. Okay, so now let's say the user is asking like what's the legal procedure to do this particular process. So we take that query and we find the response, for not the response but the actual answer in this documents, and now you pass these two things to the LLM, but you add a context or like those custom instructions saying that answer this query based on this text, don't add anything else or don't make up any answer if you don't know it. And now the generator, the chat gpt, just do a comprehension kind of thing. So it has like, let's say, a paragraph or a text context, and it also has this query, and we tell it that, tell the LLM, or it can be a chat gpt or a Gemini or anything. So we tell that answer this question based on this context, don't make up any answers. Now it would be able to answer your question. So this is how the framework of retrieval augmented generation works, where we split the documents into different chunks, embed that into a vector db, and we also embed the query into using a embedding model, do a similarity search or like a nearest neighbor search. And once we have those proper chunks for which we know that that's going to be the answer, we pass that specific text. So we won't pass the entire document, but those specific text alone to this generator, and the generator would be able to answer this question. So let's say now you have you're going through documentation of a library that has been updated recently, but the model doesn't have the information for it. So now it can answer your question with like this updated information. So this is like a widely used use case in like the industry. So when we do a Gen AI application, right? So a lot of use cases that companies are doing are like completely based on LLMs, doing this summarization. Let's say there is a course for which they need to have this transcription, and let's say we can consider this use case, right? So let's say that there is an Udemy course, and we are building a chatbot that can answer users questions. So what they can do is like get the transcription for this course. Once the user has asked a query, we can find the response or the answer in this transcription, and kind of answer the user. So this is how this basically works. And again, in a later video, let's also understand how we can do this in Python. So in Python we can do this with libraries like Langchain, Llama index, and so on. So yeah, this would be like really helpful if you're also learning Gen AI and stuff. So that's it from my side, and I really hope that you are able to understand the concept of RAG in terms of this LLM and so on. So that's it from my side, and I'll see you in the next upload. Thanks for watching.
Hello everyone, I'm Siddharthan. In this video, let's discuss how we can build a document question answering system with GPT-4o using Langchain library in Python. So here we will be using the framework of RAG or Retrieval Augmented Generation, where instead of the LLM answering from the corpus of data it has been trained on, it's going to answer from the custom data that we are going to provide it. So in this case, we will pass a document, a process document to the LLM, which is GPT-4o in this case, and it will look at the data or the text present in that document, and it will answer our questions. So this is how RAG works. So let's get started. So I have my Google Collaboratory, and you can just work with CPU environment itself, as we are going to call the GPT-4o API. And if you want, you can use the GPU version as well in order to load your embedding model. And these are the libraries that we need. So we have this transformers and sentence transformer, which provides us the vector embedding model from Hugging Face. And then we have the Langchain and Langchain community libraries in order to access the retrieval chains and other stuffs that we have. And then Langchain OpenAI, which is another extension of Langchain to interact with OpenAI models like GPT-3 or GPT-4. And then FAISS. So this is Facebook AI similarity search. So this particular tool is developed by Facebook AI research team, which is used for similarity search of vector embeddings. And then we have this unstructured and unstructured PDF versions in order to read our data and extract the text from it. So these are the libraries that we need, and I have already installed this library. So if you're trying this out, please install these libraries first. As you can see, it's already installed. So once you install all these libraries, you have to restart the session and you will get a warning message in collapse. So you can restart the session and you can just run this again, and you will see this message of requirement already satisfied. So I'll hide this inputs for now. So let's import the required libraries, and I'll also explain you what's the purpose of all these different libraries and where exactly we are going to use it. So first I'll import OS. So this is used in order to save the OpenAI API key in the environment variable so that we can call the GPT-4o model. And then from Langchain dot OpenAI, Langchain underscore OpenAI, I'm going to import chat OpenAI. So pay attention to the uppercase and the lowercase letters. So this is used in order to load the GPT-4o model. Okay, so this is the first step. Next is from Langchain dot document loaders. So you can use PyPDF. So in this case, I'm going to use unstructured file loader. So this will be used in order to read our PDF file and extract the contents from it. And then from Langchain underscore community dot vector store, import FAISS. So in case you are using a CPU environment, you have to install FAISS CPU. If you are using a GPU environment or session, you can use or install FAIS GPU. So that's one thing to remember. So the next step is importing from Langchain dot embeddings, import Hugging Face embeddings. I'll explain you the purpose of all these functions and the modules that we are importing once we complete this. And then from Langchain dot text splitter, import character text splitter. And finally, we need from Langchain dot chains, import retrieval QA. So in case you don't understand the process of RAG, I've already made a detailed video on how this RAG works and the concept of this retrieval augmented generation. I'll give the link of that video in this video description. You can check that out to understand the concepts of RAG. So now let's understand the purpose of like all the functions that we have imported. So as I said, we are importing this OS module. So we need this in order to store our OpenAI API key so that we can call the model. So the next thing is chat OpenAI, which is the function where we will pass the model that we want from OpenAI. So in this case, we'll be using a GPT-4o model. And then we have this document loaders, and in that I'm importing this unstructured file loader. And from Langchain community.vector stores, I'm importing this FAISS. So this is used in order to do a similarity search of vector. So how this RAG works is, right, so let's say we have a document. So we split this document into smaller chunks and store it in a vector DB. So in this case, instead of vector DB, we will just create a knowledge base, which is like kind of this vector knowledge base in runtime. So instead of creating a DB, we are going to use it. And now you have this document stored as vector embeddings. And now the user asks a question that, based on this document. So now we would embed this question as well. So now you have one vector, one question vector, and a larger vector of the entire text. So using this FAISS or the similarity search algorithm, we are going to find the relevant answer for the user's question in the vector embeddings and return the output for that. So this output will be sent to the LLM, and the LLM would kind of properly curate this answer from the question and the answer, and it would give you a response. So this is how this works. That's the purpose of FAISS, which is basically a vector embeddings similarity search. And from Langchain.embeddings, we are importing this Hugging Face embeddings, using which we can import the vector embedding models. So this would take a particular sentence or a text, and they would convert it into vector embeddings. And for that, we need the sentence transformer libraries. So you can use the default Hugging Face embeddings, or you can also, if you think that you can use a better embedding model, so you can choose the one that's present in Hugging Face as well. And then we have this text splitter. So this is used in order to split your larger document into smaller chunks of data. So this is important when you are working with a very large document, or the LLM that you are using has a limitation on how many tokens that you can pass. So that's the purpose of using this. And then from Langchain.chains, I'm using this retrieval QA. So Langchain supports a lot of chains. So you have this retrieval QA, which is mainly for retrieving the relevant information from your vector embeddings or your like document, and then passing it to the LLM and getting an answer. So that's about this retrieval QA. And you also have this conversational chain QA, which also is used to build a chatbot kind of a thing, where the LLM can understand the history of the conversation and answer based on that. And then you have this graph db based retrieval chains and so on. So for the simple use case of document question answering, we can just go with this retrieval QA. So I'll run these import statements. So the next step is getting the API key and storing it in the environment variables. So I'll say os.environ, and the API key variable should be OpenAI underscore API key. So this shouldn't change. So you shouldn't change the key name for this. So it should be OpenAI API key in uppercase letters. So this is basically used to save this to environment variables. And when we load our GPT-4o model using this chat OpenAI, it will look for the API key in this environment variable name. So we are doing that. So here we can pass our API key. So I'll go to OpenAI and go to this products, and within this products we have API login, and from there you can create a API key. And I've noticed that for using GPT-4 and 4o, it's asking for the payment method for some card details. So you can give that, but if you don't want to give that, you can just go with the GPT-3 or 3.5 model. So that should also work. So you don't have to change much of the code. So it's like pretty much similar to it. So I'll open the API, and in the left navigation bar, you will see this API key. And this is the key that I've already created. So I can just delete this or revoke this key and create a new one and use this. And I'll name this as doc QA rack. So project, you can leave this as default project, or choose a different project if you have created like multiples. So here I'll copy the API key and put it here. So this is actually not a recommended way to put your API key in your code just explicitly. Instead, you can just put this key in a config.json file or a .env file and load it. So that's like a more recommended approach, so that your API keys and secrets are not visible in your code. So I'll run this. Just for simplicity of demonstration, I'm just putting it, but please don't follow this particular approach. The other videos I've shown you how you can do this with a config.json file. So you would put this in a JSON file, read that into a dictionary, and from there you can pass it to the environment variable. So now I'll create a variable called as LLM, where I'll be storing this LLM model. So I'll say chat OpenAI, and within this we have this parameter called as model. I'll say model is equal to GPT-4o. So if you want 3.5 turbo also you can choose that. So but I'll use the newest model GPT-4o, put that in quotes. And the next parameter that I'm going to use is temperature. So temperature determines how random your answer would be. So if you give the value, so this value ranges between 0 and 1. If the value is closer to 0, then if you ask a similar question or the same question, it would give you the same response. If the value is closer to 1, it's going to give you a response, different response for the same questions. So that's about it. So I load this, and again you have different parameters. You can check like the other parameters and play around with that. I'll run this. So this will load the GPT-4o model into the variable called as LLM. So yeah, if you don't save this API key in the environment variable, so this line of code won't work. And then next step is reading the file. So for this I'm going to use a PDF file, a paper on attention is all you need. So this is the paper that first talked about transformer, which is released by Google. So let's upload this document and ask questions from this one. So I'll open this files and upload the PDF file that I have. So this attention is all you need. So you can find this paper online. You can check that out. Just go to Google and search this paper name. Attention is all you need, and you can download the PDF from there, or even you can use like any other PDFs of your choice. So here I'll say load the downloaded document. I'll create a variable called as loader, and this loader is equal to unstructured file loader. File loader, and within this we have to paste the path of the PDF that we have uploaded here. So copy this path and paste it here and say loader, documents is equal to loader.load and run this. So this part basically takes in the PDF that we have given here, and it will load it and basically extract like all the text that we have. So the next step is splitting it into chunks. So I'll maybe put a comment here as saying create text chunks, and text splitter is equal to characters text splitter that we have imported previously. So here we are creating an instance of this character text splitter and storing it in this text splitter variable, and within this we have to pass some parameter. So here let's say separator is equal to, let's say, new line \n, and here we can mention chunk size. So for chunk size I'll say is equal to 1000, and overlap is 200. Okay, so this should be \n. So let's understand this. So we are creating the instance of character text splitter with separator of this new line thing. So what this will do is this will like look at this document and split the text with this like new line character. So wherever it sees this new line character, it will stop that and create a chunk there. And you can also specify what's the maximum size of the chunk. So here we are saying that the maximum chunk size should be 1000 characters, and the chunk overlap, so chunk overlap is 200. So this is basically when you have two let's say paragraphs or two chunks, we can't split it like with some art constraints. So there has to be some overlap. So let's say that you have a 10-line paragraph and you have to split it into two chunks. So you can't directly say that I'm going to chunk first 5 lines and the next 5 lines. So when you do that, right, so you miss the context in between. So in order to avoid this, we would be having this overlap. So let's say that in this 10 paragraph thing, the 6 lines can be in one chunk and another, the last 6 lines can be in one chunk. So there is like some overlap, so that the model LLM or even this vector similarity search that we do is kind of understanding the context in which a particular chunk starts and ends. So that's the purpose of choosing this chunk size and chunk overlap. You can play around with this number too, so check with different chunk sizes if it's applicable for your document and so on. And next I'll create a variable and call this as text chunks, and this text chunks is equal to text splitter dot split documents, and within that we are going to pass the documents, which is nothing but the text that we have extracted over here. So there is a different thing called as split text. So in that case, right, so instead of this will be as a document type. So if I check this type over here, so this will say it's like kind of a document type in this Langchain. So let me put this first thing within this list. So Langchain core documents based document. So in this case, we are using this split documents. So if this is like as a complete string text, in that case, you can use split text. So all these chunks that kind of chunked with this size and this overlap will be stored individually in this text chunks. So let's run this. Okay. So now I'll say embeddings is equal to Hugging Face embeddings, and here I can just mention this without any model. So this will load the default model, but you want a better model, a larger model, you can choose something like this. So you can find that in the sentence transformer documentation as well. So here I'll just go with the default embedding. So you can also go with OpenAI's embedding model, but that would again cost you some usage charges. In order to avoid that, I'm just going with Hugging Face embedding, so where you won't be you won't have to kind of pay anything. So that's the reason. Next, let's create a variable called as knowledge base, and this knowledge base is equal to FAIS that we have imported from documents, text chunks, and embeddings. So this part of the code is to take in the text chunks that we have and convert those into vector embeddings. So that later when a user asks a question, we can embed that question as well and find the comparison between those vector embeddings and the question and retrieve like whatever relevant information present in that particular document. So first we are loading this embedding model and converting this text chunks into vector embeddings by using this FAIS dot from documents and passing the text chunks as well as the embedding model. So this FAIS from documents expects these two parameters. One is the text chunks and the other one is the embedding model itself. So let's call this as loading the vector embedding model. And the next step is vector embedding for text chunks. So this is the step that we have done over here. So let's run this. So this will load the embeddings model. So this may take like a couple of minutes as it has to download the model and kind of it has to load it here, so you can see it. So if you are probably using GPU, right, so you would install the FAIS GPU version and the model will be loaded in the GPU. So now it's going to load in the CPU this RAM. So instead, if you have GPU environment, it will be loading getting loaded in the GPU. So here you can see the size of the model, which is about like 438 MB. So the next thing that we need to set up here is the chain that we are going to use. Chain for QA retrieval. So here let the model, okay, so as we can see the model is kind of loaded now. So here I'm going to say QA chain is equal to retrieval QA. So here we have different kind of chains as I said earlier. So we have this retrieval QA, which is solely for extracting like this question and answers. You have this graph question answer thing and conversation based chains and so on. So here we can use this simple retrieval.qa dot from chain type, and then we can say LLM. So we have to pass the LLM that we have loaded and say retriever is equal to knowledge base dot as retriever. So you can remove the chain type, so it's maybe not needed in this case. Okay, so knowledge base is the vector embeddings that we have over here. Let's run this. So this is our QA chain, and we will invoke this QA chain and ask the questions. Let's just go through what we have done so far. So first we are setting this API key in the environment variables and loading the GPT-4o model using Chat OpenAI that we have imported from Langchain. Then we are reading the PDF file and getting the text that's present in this PDF file and saving it in the variable called as documents. Then we are creating the chunks for this document. As let's say the document is like pretty large, we have to create the chunks. So here the chunk size is 1000 and the overlap size is 200. So once we have created the chunks, it's stored in this variable called as text chunks. Now we have to convert these text into vector embeddings. So we are loading this Hugging Face embedding model, and from documents we are converting this into vector embeddings using this model and storing it in this knowledge base. So this is similar to putting the data in a vector DB and querying it in the vector DB. So instead of setting up the DB, we're just doing it in the runtime here with this knowledge base thing, and then I'm setting up the chain as retrieval QA, which is used to retrieve this answers for the question with this FASS and the LLM. So here we are passing the LLM and the retriever as knowledge base dot retriever. So what this will do is when the user asks the question, this chain handles the part of converting this question into a vector embedding, putting that to the knowledge base, getting the relevant information. So once you get the answer, once you have the user's question and the documents part where the answer is probably present, it's going to take those two and pass it to the LLM and get a response. So this is how this RAG framework works. And now we can ask some questions. So here we currently have this attention is all you need paper, right? So here I'll maybe create a question and I'll say, what is this document about? Let's see if the model is able to answer this thing. And I'll say response is equal to QA underscore chain, the chain that we have created, dot invoke, and you have to pass this as a dictionary. So create a key called as query, and within that you have to put your question, and question is stored in the variable with same name question. Now we can print the response. So it will be coming as a dictionary. So you can say response of result. So it will be stored here. Let's run this. So the response will also be like pretty quick. It won't take like a long time in order to give you the response. So here you can say this document is a research paper titled Attention is All You Need, authored by this person, and so on. So you kind of see this response over here. So if you want to see this exact output, right, you can just say response and you will see that here. So you have the query that you have asked and the result actually contains the response that is coming from the model. So this is what we need. So you can just say something like, I can ask like specific questions from there. So I have curated like another question that I can ask. So here I'll say, what is the model architecture discussed in this paper? So it has to answer the question from here. And I'll say response, same thing. Response is equal to QA chain invoke query question print. So instead of print, in order to put all this thing here, I'll just say response of result. So I don't want to scroll through the answer. So let's see. So we get this model architecture discussed in the paper is transformer. It's a novel network architecture and so on. So we get this response. So we also we have to make sure that the response is coming from the paper. So what I'll do is open this paper that I have. So attention is all you need. So I'll open this PDF. I have this thing. So I've tested this out. So we have this applications of attention in our model, right? So let's run this particular question and make sure that the model is answering like whatever is present within this particular text. So I'll come back here, copy this first maybe, and here let me put this as question is equal to what are the applications of attention in our model. So let's ask this particular question and just copy this response thing. So we are getting it. We will try printing this output. So we have this encoder, decoder, attention, self-attention in the encoder, self-attention in the decoder. So in 3 layers, the queries come from the pre-S decode layer. So this is pretty much like what's present over here. So this is how we can pass a document to the LLM using this vector DB, vector embeddings and so on, and get a response from it. So I hope you understood everything present over here. I'll just give you a quick recap of whatever we have done. So the first step is installing all the required libraries that we have, such as transformers and sentence transformer, used to load the embedding model, Langchain and Langchain community, and Langchain OpenAI to load the model, as well as just to work with this change that's present in Langchain, as well as like all the unstructured FAIS. So all this we are importing from the Langchain's extensions, and then we have this FAIS CPU, which is also required, an unstructured and unstructured PDF in order to read the PDF file and extract the text from it. So here we are getting this API key from OpenAI and storing this in the environment variable. So the next part is loading the LLM GPT-4o model using this chat OpenAI from Langchain OpenAI, reading the file using this unstructured file loader. And once we done that, we are splitting this document using character text splitter. So you also have this another type of text splitter like called as recursive text splitter. You can try that as well. So then we are chunking the document's text into different text chunks, and then converting those chunks into vector embeddings using the embedding model that we got from this Hugging Face embedding. So it's getting downloaded over there, and then we are creating a chain, which is really important. So we in this case we are using a retrieval QA, and then we are passing the LLM and like how the retriever needs to be. So there, as I said, the different chains takes different parameters. So the conversational chain takes the chat history as another parameter, so that it knows like whatever the LLM has answered before. And finally, we can ask a question and get a response from it. So I hope everyone is clear until this point. So please practice this code. So this actually is like a very simple approach of doing this. And maybe in the next video, let's build a Streamlit user interface for this and work with the different models. So the user can select different models and get a response for a document. So yeah, I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. In this video, let's understand how we can get started with Ollama so that we can host and run LLMs locally. So here let's work with Gemma, but the process is pretty similar for Llama 2, Llama 3 and other models that are mentioned over here. So we will understand how we can download this Ollama software, how we can load the models from Ollama, and how you can access this. So we will be working with like 4 different techniques. One is how you can ask questions to the LLM from the terminal, and the other way is to access it with Ollama library in Python, and access it with API endpoint, and also how you can access the Ollama models that you have downloaded from Langchain. So these are all the aspects that we are going to discuss today. First, you can go to Ollama site. So go to Google and search Ollama. So here you will find this list of models that you can work with as well. So let's come back to this a bit later. So in order to first download Ollama, right? So go to the site and click this download button. If you are on Linux, you just have to paste this command on your terminal and run this. So this will install Ollama in your system, and you can access it from command prompt from your from your terminal in your Linux machine. If you are on Windows, you can download the installer, and the installation process is like pretty simple. So you can follow the steps and you can install it. So after installation, you can just open it once. So you can maybe search for Ollama in your search bar and open it. And once you have installed it, you will be able to access this from your command prompt or using your PowerShell. But I would suggest you to use it in Windows PowerShell. Mac OS also it's pretty similar. You have to download an installer, and then once you have installed it, you can access it from the terminal. So I have already installed Ollama in my system, so I can directly access it from my terminal. So I'm currently on my terminal, and you can maybe ask Ollama space help. So this only runs once you have like installed Ollama. So here you can see the different commands that we have. So we have this main commands are pull, which is used to pull a specific model, and then you have this Ollama run in order to run a model, Ollama list that lists all the models, and so on. So here you have copy, remove a model, etc. So I'll clear this and say Ollama list. So this will list all the models that I have already downloaded. So here you can see I've already downloaded Gemma 2 billion version, and the default quantization is 4-bit quantization. So you're seeing that the model size is pretty small, 1.7 GB. So you can use this model even if you have like a smaller GPU, or even you can load it in a CPU. Shouldn't be a problem as this model is smaller. And you can just like use pull command in order to pull this. So let's say that you want to pull Llama 3 instead of Gemma 2, right? So what you can do is, and also you can have multiple LLMs. It's not like you can have only one LLM at a time. So that's not the case. So here you have this models, right? Or the other way you can do this is come to Google and search Llama 3 Ollama. So you will see the command to run this. So here you can select different version, whether you want a 8 billion version, which is the default version, and you see this quantization over here, and also the size of the model is here. Let me close this one, and then you have this latest 70 billion version, and click this view more tags, and you have this instruct version, right? So the instruct version is also good for certain use cases. So we have 4-bit quantization, and the size of the model is 4.7 GB. So if you want to pull this model, copy this Llama 3 instruct. So first you have to pull this before you can run this. So here I can say Ollama pull, paste this Llama 3 instruct. So now this model will be pulled, and you can see the model is getting downloaded over here, which is about 4.7 GB. So if you want to work with Llama 3 instead of Gemma 2 billion, you can use that. But for me, Gemma 2 billion is sufficient for now. So I'm going to stop this process. And again, Ollama is very useful when you're like developing something, because if you're going with the Gemini or even with GPT-4 or GPT-4o, right? So you have to pay some amount for your API calls, and you have to give this payment methods and so on. So in development, it's better if you have this smaller models in your local machine. You can test that out. And even if you're deploying this on, let's say, a EC2 or a virtual machine, you can pull this model to those EC2. So all this Gemma and Llama 2 and Llama 3 are open source model. So you can pull and use that model as well. So that is like a good deployment technique as well. So I'll stop this for now because I don't need this Llama 3 for now. Again, I'll probably list the models. So this is the name that we are going to use in order to invoke this model. So now I can say, once I have pulled a model, I can say Ollama run Gemma colon 2 billion. So this will run the Gemma model, and I can access this from the terminal. As I said, you will try to access this model from the terminal, where you can directly send a message, or you can use Ollama library in Python, which we will discuss a bit later. And then you can also use request library to call the Ollama's API endpoint, or also you can use Langchain library in order to access Ollama. So here first I'll maybe ask, what is machine learning? So I can send this question. So when you call this Ollama run Gemma 2 billion, so it will go into this chat kind of interface where you can ask a question and it will stream you the answer. So it explains what is meant by machine learning and so on. So you can go ahead and ask like other questions as well. And if you want to come out of this, you can say /by. So this will come out of this, and you will see your terminal again. So this is how you can access it from your terminal. So this is the first step. So now let's see how we can access this pulled or downloaded LLM from Ollama in Python. So that will be the next step. So I'll open my PyCharm. You can maybe create a separate environment for this. So these are the three libraries that we are going to need. First is Ollama. So we will use this in order to directly access the Gemma 2 billion model that we have downloaded using Ollama library. And then we'll be using request in order to access it from a endpoint. So once you pull this, you can access this from your localhost endpoint URL as well. And then we will also see how you can do the same with Langchain community, the Langchain library. So here I have this folder called as SRC. Again, doesn't matter like what your folder structure is for this particular use case. So I'll create a Python file and I'll call this access Ollama. Okay, so make sure that you have installed all this library. You can say pip install Ollama this version, request this version, Langchain community this particular version. So these are all the latest library version by the time I'm recording this video. So you can the other way is you can put all this in the requirements.txt file and say pip install -r requirements.txt. So I'm in the project folder of Ollama getting started env, and within that it has this requirement.txt file. So I'm going to say pip install requirements.txt. So I've already installed this library, so it's not going to install again for me. So you can do this as the first step. So once you have downloaded this, so come back to your Python file and you can import Ollama. So for accessing this, we should have already pulled the model. So here I'll say Gemma should be pulled already. So this won't run if you haven't pulled a specific LLM. And here I can create a variable called as response, in which the response will be stored, and response is equal to ollama.chat. And within that, the first parameter that you're going to pass is model. So model is equal to Gemma 2, Gemma colon 2 billion version. The other one is I think 5 billion or 7 billion version. You can check that out. And then we are going to pass a set of messages. So Ollama chat. Okay, so response is equal to ollama.chat, and the other one is, sorry, so this shouldn't be a string. Model is equal to Gemma 2 billion and messages. So this is kind of like the payload that we have to send. So create a list, and within that we are going to assign few things. So we are going to create other dictionaries. So first you can create this role as system. So this is like giving the context to the LLM of what we expect it to do. So create the system. So this we have already seen when we have accessed GPT-4o from OpenAI library. So here you can create a variable called as content, and here you can say you are a helpful assistant. Okay, so this is the first dictionary within that list. And next what you can do is again create a role. So this role will be the user. So this is like we are first setting up the context for the LLM, and now let's say the user is asking a question of let's say what is machine learning. So this is kind of a chat completion use case. What is machine learning? Put a comma. And now let's say the assistant is answering something like, so here the role will be assistant. So we are defining the roles. And let's say the content, or let's assume that the response given by the model is machine learning is a subfield of artificial intelligence where a model learns from the data. So let's assume that this is the response that the model is giving. So now the user is asking another question of, so the role will be user. Let's say the user is asking what is deep learning. So this is just to give a template kind of a thing to the model. So it's like first we have to set up the context saying that the model should behave as a helpful assistant that's going to answer some question. So the first, the user is asking like what is machine learning, and the assistant is saying that machine learning is a subfield of artificial intelligence where a model learns from the data. And then there is another question from the user saying what is deep learning. So now we are going to send this to the model, and it's going to answer this question of what is deep learning. So here let's print this. So print response. So the final response will be stored in this message, and within that there will be a key called as content. So this is where this response will be stored. So this is, let's probably run this first. So this will invoke the Gemma 2 billion model that we have pulled, and it will answer your question. So let's say that you haven't pulled Llama 2 or Llama 3 and you are using Llama 2 or 3, it's going to show you an error. So here we are seeing this response of deep learning as a subfield of machine learning that uses artificial neural network with multiple layers to learn from the data, and so on. So this is the response that we are getting. Okay, so this is how you can use Ollama library in Python. So just do pip install Ollama with some version numbers and you can access this. But this is not that widely used. The other kind of approach is used to use this Ollama endpoint, the API endpoint. So this is useful when, let's say, you have a different front-end tool. So it can be like Angular, Node.js, or like some front-end tool. In that, if you want to access that, you can just call this API endpoint. So from that you can call this and pass a prompt and get a response. So that basically you don't have to work with Python in order to access this API endpoint. But if you're using this Ollama, then there is a limitation, right? So that's the reason we are having this another approach. So I'll create another file and I'll call this as Ollama as API. So for this we need the request library in Python, which is basically used to access APIs and send this get post request and so on. So here I'm going to first import a JSON library, leave a line space, and then import request library. So you should have already installed this request library as we ran this pip install requirements file. So the JSON we are kind of importing because before we send this payload or this body to the API, right? So we have to convert this to a JSON object. So here I'll create a variable and maybe I'll call this as Ollama endpoint. So by default, once you have pulled the model from, this is the URL from which you can access this. So I'll say http localhost and say 11434. So this is the default port in which you will find this Ollama models. Say API / predict. Sorry, it should be generate. Okay, so http :/localhost, and in the localhost it's going to run in 11434 port /API and generate. So even let's say you're using some other tools, you can access this Llama model, the Gemma 2 billion model, from this particular endpoint. So here we have this payload. So I'll create a variable called as payload and say json.dumps. So this json.dumps is used to convert a dictionary into a JSON object. So json.dump. So within this we have to pass a dictionary, and here you can say model will be Gemma 2 billion, Gemma : 2 billion, and the prompt for this will be, let's say, why is the sky blue? So let's ask this question, and then you can say stream is equal to false. Oh, so this should be a dictionary, so stream should be in quotes and then say false. Okay, so these are the three parameters that we are passing. So first is the model. What's the model that you're going to use? So it's going to be Gemma 2 billion. Prompt is why is the sky blue? This is the question that we are asking. Stream is equal to false. So if you enable stream, it's like it's going to send you character by character to give you a response that looks more like someone is typing you the answer. So something is like streaming. So we don't want this for this particular case. I'm turning off the stream, and now we can say response is equal to request.post, and within that paste the Ollama endpoint that we have loaded, and data. So we have to pass this payload. Okay, so now, oh, there is a typo, payload is there, and now I can say response is equal to, we are going to extract the response alone. So response dot JSON. So first we are converting it into a JSON, say response, and finally print response. Okay, so this is the method. So the model, you can access it from this particular port, localhost 11434, and model is Gemma 2 billion, prompt is why is the sky blue, and stream is equal to false. So we are creating a post request because we are going to send this JSON object, we are going to post it to this particular API endpoint, just passing this payload to this data parameter and getting the response, converting into a JSON and accessing the response alone where our text answer is stored. So when I run this, you will see the answer for the prompt, why is the sky blue. So I'll run this. So this is the result. So the sky appears blue due to relay scattering and so on. So here we are getting a response. So this is how you can access the Ollama model that you have pulled from a request library, or basically you can access it via a API endpoint, which is this one. So you can also configure this as well. And the other advantage of Ollama is that it's like highly customizable. You can customize your LLMs, and you can customize the parameters that you're going to pass and so on. So this is how you can do this. And the final step is we are going to access this model from Langchain, and this will be extremely useful when you are working on, let's say, building some RAG use cases, which is a retrieval augmented generation, where you pass some context to the model like a PDF file, and the model has to answer from the text present in that file. So those cases, this particular approach of accessing it from the Langchain will be really helpful. And also if you're building some AI agents and so on, accessing it via this method is like useful, as this is integrated with Langchain library. So I'll come back to this src folder, create another Python file and call this as Ollama Langchain access. And first I'll say from Langchain underscore community dot llm, so you can use the community version of Langchain. So from Langchain community dot llms import Ollama, so O should be uppercase letter, and create a variable called as llm. So llm is equal to Ollama, and within that you have to pass the parameters like model is equal to, so here we are going to use Gemma 2 billion as we have pulled that one. And then you can maybe mention other parameter as well. Let's say temperature again determines how random your response is going to be. So 1 second. Okay, so the value ranges between 0 and 1. If your temperature value is closer to 0, that means for a particular question the answer that you're going to get from the LLM is going to be similar. If the response is more, then you will get the proper correct answer, but it would be like random. You won't get those exact answers and exact words and so on. So that's for this temperature parameter. And you also have like other parameters that you can explore. So here I'll create a variable called as response, and response is equal to llm dot invoke. So we are going to invoke the LLM that we have loaded with Ollama. Again, all this will work only if you have pulled the model already. So that is like the first step. So here I'll say tell me a joke and just print the response. Okay, so let's run this. So what do you call a boomerang that won't come back? A stick. So this is the response that we get from the model when we ask it to tell a joke. So the main approach here is we are accessing Ollama from Langchain community library. So if you are building some RAG application where you would read the file from unstructured by PDF or some other file reading libraries, so you would chunk that, store that in a vector DB, and then you would pass the retrieved information to the LLM. So in that case, instead of using, let's say, a GPT-4 Gemini models, which is going to require a API key, you can just host your models in your local PC and you can access them and invoke this LLM. So that is all I wanted to cover in this video. So I hope this is useful to you. So please try this out. So it's like, as you know, this is like a very simple approach. So using this, we'll also try to build some application around this locally hosted LLMs, which will be useful for us. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. In this video, let's host a Llama 3 model on local using Ollama, and using this LLM, we are going to perform retrieval augmented generation, shortly known as RAG. So RAG is basically when you want your LLM to answer from a context window. So let's say that you have a document and you want the LLM to answer based on the content that's present in this document instead of the large corpus of data it has been trained on. So this is what RAG means, and in this video we are going to do all this locally by using Ollama, using which we will pull our Llama 3 model and we will host it in our local system. So this will be the agenda for today's video, and let's get started. So the first step is to pull the Llama 3 model. So for that, first you need to install Ollama. So I've already made a video on how to get started with this Ollama thing. You can go through that video if you want. I'll give the link of that video in this video description. You can check that out. So next, once you're done with that, go to Google and search Ollama Llama 3. So if you want to download, you can just download from this page as well. So the download process is pretty simple for Mac, Windows as well as Linux. So it's like not tough at all. So once we are done with the installation, now we can pull the model. So here you can find the different models that's present over here. So you can search the models like Gemma, Llama 3 and so on. So our model of interest is Llama 3, and even if you want to use a Gemma, let's say that you have a machine that doesn't have like that large of a GPU. So for example, my local machine only has like a 4 gigabytes GPU because it's a NVIDIA GTX 1650 Ti. So it only comes with 4 GB of GPU RAM. So here I'm currently using a EC2 instance with 16 GB GPU, which is a T4 Tensor Core Tesla GPU. So again, hence I'm using a Llama 3 model. So if not, you can just use a Gemma model as well. So that's the main thing. So let's say that we have searched Llama 3 in Ollama, and you have this different version. So you have 70 billion version. You can also see the size over here. It's 40 GB, and the 8 billion version is 4.7 GB, and you can also see it's Q4, which is 4-bit quantization. So the weight or the parameters of the model are reduced to a precision of 4 bits. So The purpose of doing this is your model's size decreases, but the performance or the efficiency doesn't like affect so much. So of course there will be a drop in the performance, but it's not like that much. So that's about quantization. So for RAG, we can use instruct version instead of the base version. So I'll click this instruct, and in order to pull this instruct version, you have to use this particular command. So this is Ollama run. So this is used when you have already pulled a model, and then let's say you want to run this model, so you would use that. So for the first step, you need to pull it. So I'll come to my terminal, and if you're in Windows, you probably would have installed this Ollama, and after that you can access this from the terminal from your Windows PowerShell. So Linux and Mac users also can access this from the terminal. You can say Ollama space help. So this will display like all the commands that you have over here. So serve, create, show, run, pull, and so on. So let's say that I can just type in Ollama list, and this will list all the models that I have pulled already. So here you can see that I have Gemma 7 billion model, Llama 3 instruct this particular model. So let's say that I want to pull just the base version 8 billion. So what I should do is I should come to the terminal and say Ollama pull. So look at the name over here, which is Llama 3 colon 8 billion. So Llama 3 colon 8 billion. So when I run this, so it's going to load the model. So it's going to pull the model from the repository. So that's the first step. But again, we are not going to work with 8 billion. So we are going to work with 8 billion instruct, right? So I'll clear all this and list this again. So now I have 8 billion instruct and Gemma 7b. So this is how you can pull the model. If you want, you can use again Gemma as well. So Gemma comes with 7 billion version and 2 billion version. So you can check that out as well. So that's the other thing. Okay. So now we can go into the coding aspects where we will load this model and how to do the retrieval augmented generation by passing a document and asking a question to the LLM. So that will be the next step. So for this, you need a bunch of libraries. So we are going to install Langchain and Langchain community. So the versions are given over here. So I'll share you this particular notebook. And then we have this FAISS, which stands for Facebook AI similarity search. So this was developed by Facebook's AI research team. So this is just to find like a similarity search of the vectors. So here we will convert all the content of the document into vector embeddings, and the query will also be converted into vector embeddings, and we do a similarity search. So for that we need this. And FAISS comes in two versions. One is CPU and the other one is GPU. And because of some CUDA version errors, so GPU is giving me some issues. So I'm going with CPU. And even if you are in Python 3.10, you probably shouldn't be facing any issues. But if you're in 3.12, so sometimes like it's causing issues with the CUDA errors and so on. So you can figure that out maybe. But if not, you can just use the CPU version for now. So we have this FAISS CPU, and then we have the unstructured. So this unstructured library is used to load the content of the PDF file. And then we have this PDF, related code for this unstructured. So that comes with this unstructured square bracket PDF. So that module will be downloaded. And then you have transformers. So we are downloading the transformers and the sentence transformer. So this is used to load the embedding model. So we have the sentence embedding models. So in order to load that, we are going to use the transformers and sentence transformer library. So these are all the dependencies that we need. So the next step is, once you have installed all this libraries, I've already installed, so I've commented it. So if not, if you haven't already installed it, you can uncomment this and work on it. So the next step will be importing the dependencies. So here I'll say importing the dependencies. So I'll say import OS. I'll tell you why we need all these things. Or the next thing is import Langchain underscore community dot LLMs import Ollama, and from Langchain dot document underscore loaders import unstructured file loader. From Langchain dot embeddings. I'll explain you the purpose of all these libraries and functions in a minute. Once I'm done with this, FAISS, so all should be uppercase. From Langchain dot text splitter, import character text splitter, and finally we need Langchain dot change, import retrieval QA. Okay, so these are the things. Let's understand this. So OS we need, one second, this should be from so OS is used in order to access some of the files that's present in our system. So for that we use this, and then we have this Ollama. Ollama is used in order to access the model that we have just now pulled, which is Llama 3 or Gemma model and so on. And then we have this unstructured file loader in order to load our PDF file, and then we have this Langchain dot embeddings. So from Langchain dot embeddings we are importing FAISS. So okay, so this should be not embeddings, but okay, let me try this again. From Langchain community dot vector stores, import FAISS. So from Langchain dot embeddings we have to load the Hugging Face embeddings. These are the things. Let's run this and see if this is working. Okay, so it's worked well. So we have Ollama in order to access the LLM that we have just now pulled, and we need this unstructured file loader in order to read the PDF file and get all the text content out of it. And then we have this FAISS for similarity search of vector embeddings. And then you have this Langchain dot embeddings. We are importing this Hugging Face embeddings, using which we will convert the text into vector embeddings. So the next step is character text splitter. So this is used in order to chunk the content that we have in the PDF file. So we cannot pass this entire text. So instead we would chunk this in a bit by bit fashion. So once all these chunks are present, we will encode those things into a vector embedding thing and store it in a vector DB, or just create a knowledge base out of it, and later we can use FAISS in order to do a similarity search. So for chunking it, we are using this character text splitter, and then we have retrieval QA. So there are like different chains. So there are like conversational chains, retrieval QA chains, and so on. So our focus here is just document question answering. So for that we can just stick with retrieval QA, where you can just pass this document thing and pass a question and get a response out of it. So this is how all the things work. So if you are also not very sure about the concept of retrieval augmented generation, I've already made a video about that. So it's like a conceptual video of all the things that's come together and the architecture of it. So I'll give that video link in the description as well, so you can check that out. So that's all about the import statement. Now let's load the LLM. So I'll say LLM is equal to Ollama, and within that I can say, so LLM is equal to Ollama, model is equal to, so we have to name this model. So the model name is Llama 3 colon instruct. So this is the 8 billion version. The other version is 70 billion. So Llama 3 instruct. And the other thing that I'm going to need is parameters like temperature. So you can also include other parameters as well. So temperature is kind of determines the randomness of the response of the model. So when I run this will load the Llama 3 instruct model. So this won't work if you haven't pulled your model already. So this will work only for the list of models that you have pulled and it's like available to you. So here also you can see the sizes of the model. So that's the next step. So we have loaded our Llama 3 instruct. Again, if you're working with Gemma, right, so you just have to replace this Llama 3 instruct with whatever Gemma version that you're working on. So 2 billion just comes with Gemma colon 2 billion. So you can check that out once and you can load that. So the next step is loading the document. So here I'll put a comment saying that sorry, it's loading the LLM, which is Llama 3 in this case. The next step is loading the document. So for this, I can create a variable called as loader, and loader is equal to unstructured file loader, which is the function that we have imported. And within that, we can pass the name of the file. So for this, we are going to work with the PDF file, and that PDF file is the paper that was released on Transformers. So I'll copy the name of this file and paste it over here. So both this notebook and this file are in the same directory. So I'm not giving any path to this. I'm just mentioning the name of this file. And I can say documents is equal to loader.load. So this will load the content of the PDF in a document data type, which is an unstructured data type. Let's run this. So this will load this constraint. So this may take some time depending upon the size of the PDF. So if you want to know how big of this PDF file is, right, maybe I can open it and show it to you. So in the downloads, oh sorry, this is the PDF file. So you can see the total number of pages is 11, and it has like some content about like the transformer architecture. So this is the paper that was released by Google first, basically on the transformer model. So we have this documents is equal to loader.load. So this will load the documents, and the next step is we are going to create chunks for this document. Create document chunks. So I'll say text splitter is equal to character text splitter, and we can mention like what kind of separator needs to be. So let's say that the separator is /n, which is a new line separator, and then we have this chunk size, and chunk size, let's say that it's 1000. You can play around with the different numbers, and overlap is equal to 200. Right, so here we are creating an instance of this character text splitter and giving the parameters for this. The separator can be new line, the chunk size can be 1000, and the overlap is equal to 200. So wherever it sees a new line character, it's going to separate those into different chunks. And again, the maximum number of characters that can be present in one chunk is 1000. So that's what we are mentioning over here, and the overlap is 200. So that means we won't chunk it just by the character sizes. So what happens is when you kind of chunk it like in a discrete way, the LLM or the vector embeddings may not have this proper context. So maybe I'll show this to you visually. So let's say that we have this a large paragraph about this transformer thing, or let's say we have this paragraph, right? And when we chunk it, let's say that let's take this example. So these lines are chunked to one chunk, and the line after that are chunked to a different chunk. So we don't do that. So instead we will first make this as the first chunks and do a overlap. So let's say that this has like, let's say 6-7 lines, and the second chunk will start from this line. So there will be a overlap, so that the context is not lost when we do this conversion from vector embeddings, text to vector embeddings. So that's the reason we are mentioning this overlap parameter of 200. Again, you can play around with this number. So this is the instance that we are getting. Okay, so this should be chunk overlap. So we are instantiating this character text splitter with all these parameters. Now we can pass our documents, which is basically the content that the unstructured file loader has loaded. So here I can say, you can print and show this to you. So you can see, so this is the entire text that has been derived from the PDF using this unstructured file loader thing, and it's in the type of document thing, page content, all this entire content. So I'll delete this for now. So here we can say text chunks is equal to text splitter dot split documents. So this is in documents format, so we can use split documents. Sometimes you can also chunk this as just as text string data types. So in those cases you will use split text. So here we are saying split documents, and within that we can pass the documents variable that we have created over here. So let's run this. So this step is done. So first we have loaded the document using unstructured file loader, and then we are splitting this document's content into different chunks. So the next step is loading the embedding model. So here I'll say loading the vector embedding model. So this is used to convert this text into vector embeddings. So let's create a variable called as embeddings is equal to Hugging Face embeddings. So within this Hugging Face embeddings, you can use specific models that's present in the Hugging Face library, the Hugging Face library or Hugging Face hub, but you can just go with the default one by just mentioning Hugging Face embeddings. So let's run this. So similar to loading the LLM, this will load the embedding model. There are some warnings, but you can ignore that for now. So it's about like resuming the download. So the next step is converting all this text content into vector embeddings using this embeddings model. So here I'll say knowledge base. So knowledge base is equal to FAISS dot from documents text chunks comma embeddings. So we are going to convert all these text chunks into vector embeddings, and later this will be used for similarity search from this FAISS, the similarity search library. So this will be the next step. So we are almost done with this. So only like there are few things left over here. So now I'll say retrieval QA chain. So let's say that QA chain is equal to retrieval QA, the chain that we have imported, dot from chain type, and here I'll say LLM comma retriever is equal to knowledge base dot as retriever. Okay, so we are creating a QA chain, a question answering chain. Okay, knowledge base must have made nearer. Okay, let's rename this and run this again. We are creating a variable called as QA chain and using this retrieval QA, which is used for this question answering task coupled with this, vector DB and LLMs. And from chain type, we are passing a LLM and the retriever. Retriever is basically your knowledge base as retriever. So what basically happens in this RAG thing is, right? So you have a document. So in this case, the attention is all you need. Paper is the document, right? This entire content will be read and this will be stored in a vector database. So if you want to use an actual database, you can go with ChromaDB, LanceDB and other vector DBs that are present. This FAISS just runs in the memory. So let's say that we are considering a vector database which stored these vector embeddings. So all these contents will be converted into vector embeddings and stored in the vector DB. And for each of this text, let's say that a particular sentence has been converted into a vector embedding. So it's nothing but some set of numbers that represent this text as vectors, and there will be this corresponding IDs as well to extract this corresponding text from those vectors. So now you have a vector DB that has the vector embeddings of this entire document, and now the user asks a question. So let's say that the user asks a question about this hardware and schedule. So now what happens is you would convert that query as well into a vector embedding, and now you search the vectors that's similar to this question to this entire vectors of this document. So let's say that in this case, right, so when the user asks something about, let's say, the machine translation thing, so the question is about machine translation, so it will convert that into a vector and search that vector with this entire documents vector embeddings, and let's say that it will extract this particular text. So now you have the question and the content in which the answer may be present. So now you send this question in text format as well as the answer in text format to the LLM, and the LLM will frame the answer. So this is all that's happening. It's not like the LLM kind of feeds from the vector embedding. So it doesn't kind of read the vector embeddings. So what happens is the vector embeddings is used in order to do the similarity search and find the similar vectors. Only the question and the relevant content that has been retrieved from the vector database is sent to the model. So it's basically like the question will be what is machine translation mentioned in this paper. So that question and this particular text will be sent to the model, and the model or the LLM in this case will the Llama 3 model will frame the answer for this question and it will send this to us. So this is what happens. It's not like the entire content is fed to the LLM. So that's not how this works. So this is about the architecture of this RAG, and this is what I've explained in my conceptual video as well. You can check that out if like you want to understand like this concept like more clearly. So this is about this QA chain. Next, let's ask a question. So let's say that this question is equal to, let's ask a simple question of what is this document about, and then you have to say response is equal to QA underscore chain, the retrieval QA chain that we have created, dot invoke. So you have to use this invoke, and within this you can pass this query as a dictionary. Query colon question. Now let's print this response. The final answer will be present within this response and within the key called as result. So you can check that. Okay, so let's run this. So here we are creating a QA chain and passing the LLM and the knowledge base, the vector embeddings that's stored, and then we are passing a question. So this question will be converted into a vector embedding, and we will retrieve the relevant information and then pass this to LLM. So this is what happens in a QA chain, and we are using this QA chain.invoke to invoke this chain which has this LLM and the knowledge base, put this query and get the relevant response from this. So this is how this RAG for this retrieval QA works. And let's see. So the LLM of choice in this case is, you know that it's Llama 3, but again, as I said, you can use Gemma, or if you want to use GPT-4o, right? Even you can use the Langchain version of this GPT-4o. So you can access GPT-4o API from Langchain itself. So that API thing you can pass to this LLM and then pass this in turn to this retrieval QA chain. So this answer says that this document appears to be a research paper or an article about the transformer, a sequence transaction model, and so on. So it was able to capture that information properly. Maybe let's ask another question of, again, a similar question of what is the architecture discussed in this model. Let's ask this. So the second turn kind of took about 4 or 5 seconds. It won't take like that much of a time. So the first time the model loads and all the other things happen, so it might take some time, but the later questions that you ask won't take that much of a time. Again, it also depends on the GPU that you are using. So the answer is the architecture discussed in the model is transformer and so on. Again, so we can't assure that all the questions that we ask kind of gives you accurate response, because this is fairly a smaller model. So Llama 3 8 billion version. So the larger version is 70 billion. Again, of course, we can't load it because of the GPU limitation. But if you are working in a company and they have that machine with them or the cloud instance with them, then you can use like the 70 billion version. But all this steps remains the same. So you can go to an EC2, instead of 8 billion you can kind of load the 70 billion version and so on. Again, if you're working on a local, if you have like let's say 8 GB GPU, you can load Llama 3 8 billion version itself. So it's only about 4.7 GB, but this is how this works. Let's just do a quick recap of what we have done. So the first step, we have imported all the dependencies that we need. So we have this Ollama in order to load the LLM, unstructured file loader to load the PDF file, FASS in order to do similarity search of the vectors, and then Hugging Face embeddings used in order to convert the text into vector embeddings. Character text splitter is used to chunk your PDF documents content into smaller chunks, and then retrieval QA where we'll pass the LLM as well as the knowledge base, which is the vector embeddings that we have stored. When we are loading the LLM from Ollama, the Llama 3 instruct model that we have pulled with some temperature parameter as 0, so that we don't want any larger randomness to the model. So, and then we are loading this using unstructured file loader, and then using text splitter, text chunks, and so on. And then we are loading the embedding model, and we are converting this text documents into vector embeddings and storing this in this FASS thing for similarity sets. And finally, we have this retrieval QA chain passing the LLM and the knowledge base to it. And then we can ask this question by using QA chain.invoke. So I hope everyone is clear about this, and please try and see how this code works. So that is all from my side, and I'll see you in the next chapter. Thanks for watching. Hello everyone, I'm Siddharthan. In this video, let's understand how we can build a Streamlit application in Python to perform retrieval augmented generation. So first, let's understand about retrieval augmented generation quickly. So this is known as RAG in short form, and this is nothing but, let's say that we have LLMs like GPT, Llama, Gemini, and so on, right? And all these large language models are trained with vast amount of data. When you want the LLM to answer from a custom data set, let's say that you have a legal document about a company and you want the LLM to answer a question from this document, this is what we call as RAG. So we give this context window, which is nothing but this custom data that we are going to provide it, and the LLM is going to answer from that particular context instead of answering it from the vast amount of, or the corpus of data it has been trained on. So that's what RAG means. And the other important thing here is we are going to perform this locally. That means we are going to host the model, which is Llama 3 in this case, locally using Ollama. So using Ollama, you can host different models like Gemma, Llama, and other open source models as well. And again, if you don't have a large GPU, that's fine. You can even use a shorter version of Gemma, which is only like about 2 gigabytes in size. But if you have a slightly larger GPU, let's say 6 GB or 8 GB of GPU, in that case, you can definitely host like Llama 3 models as well. So this is what we are going to see. So we are going to build a RAG application with a Streamlit user interface where the Llama 3 model is hosted in local. So I hope everyone is clear with the purpose of this video, and let's get started. So my laptop is 4GB GPU machine, so it has this NVIDIA 1650 Ti, which is like a pretty old GPU. So I've kind of like provisioned this EC2 where I can use a larger GPU. So this EC2 has 16GB GPU, which is a T4 Tensor Core GPU. So RTX, GTX, so all these kind of GPUs from NVIDIA's are kind of optimized for gaming. This T4 and A100s and so on. So these lines of GPUs are like optimized for deep learning and other ML deep learning related stuff. So this particular EC2 is kind of using that GPU configuration. So I'll explain you how you can get started with this Streamlit application now. So the first thing that you need to do is install Ollama. So I've already made a video on my channel. I'll give the video description of that, the link of that video in this video description. You can check how you can get started with this. So the installation is pretty simple in like Linux, Windows, Mac, and so on. So once you have installed this Ollama, right, so you can access this from the terminal. So I'll open my terminal. And here, once you have installed it, you can run Ollama with this Ollama command. So I'll say Ollama help. So this will list like all the commands that we have, and here I can say Ollama list, and this will list all the models that I have. So here I have Llama 3 instruct model, which is 4.7 gigabytes, and Gemma 7 billion model 5 gigabytes. So Gemma comes with another 2 billion version, and the size of that is 2 GB. Again, as I said, if you have a smaller GPU, you can go with that. If not, you can go with Llama 3 if you have like enough GPU. So the first part is you have to pull this model. So once you have installed Ollama, you have to pull this model. For that, you can go to this models list, and here you will see this Llama 353 and so on. There are like different models, Gemma and so on. So let's say that you want to install Gemma, or you want to pull Gemma, so you can go to this and search for Gemma model name. So here you can search the version that you want, whether you want 2 billion version, 7 billion version, or the latest update and so on, or the instruct version. So let's say that you want the 2 billion version, and this is the command. So we have Ollama run Gemma 2 billion, right? So instead you have to say Ollama pull Gemma 2 billion. So run is only after you have pulled it, you can run this so that you can run this model in your terminal itself. So I'll show you this one. So let's say that I'm going to this terminal. So I already have this Ollama 7B. So let's say that you are opening this for the first time. Just type in Ollama pull Gemma 2 billion. Maybe I'll pull this and show this to you. So this won't take much time in this EC2. So let's see. Ollama pull Gemma 2 billion. So you can see the size of the model is like 1.7 gigabytes. So this will pull the model and then you can access this model using Ollama run Gemma 2 billion. So now I'll copy this particular command. And I'll come back to my terminal. So it's pulling the model. Okay, so now this part is done. I'll clear this and say Ollama list. So now you will see that I also have a Gemma 2 billion version. Now I'll paste this command of Ollama run Gemma 2 billion. So this will start an interface where I can send a message asking, like, let's say, what is a LLM? So this will answer a question. So now we have this model in the local. So we are going to access this model that we can access in this Ollama from the terminal. Instead, we are going to use it with Langchain and so on. So in order to come out of this, you can just say /by and this will come out of this Ollama thing. So this is how you can pull a model. So if you want to pull, let's say, Llama 3, Llama 2 and so on, you can do that as well. So let's say that you have pulled the model and you have this model ready. So now we can get into the coding aspects. So I'll open my PyCharm. So it's better to work with PyCharm so that you can access this terminal and have like proper virtual environment for your projects. So here the code structure is that I have a folder called as SRC, which is like more of a standard way to put your Python codes, which has all your source code. And then I have this requirements.txt. So both source folder and the requirements.txt are in the same folder. This is my project directory. So I have these things, and in the requirements.txt I have few libraries. So I have Streamlit. So all these are latest version by the time I'm recording this video. So I have Streamlit, Langchain community, Langchain, FASS, CPU, unstructured PDF transformers, and sentence transformer. So first you need to install all these libraries. So for that you can come to this terminal and you can see this is the project directory env and -rec June 21, and that directory contains this requirements.txt. So I'll directly say pip install -r requirements.txt. So this will install all the libraries and the versions mentioned here. So I've already installed all the libraries. So it says like requirements already satisfied. So for you, this would probably like install all these libraries. I'll quickly explain you the purpose of this library. So Streamlit, we know it's used to build the user interface. Langchain community is used and Langchain. So both these libraries are used in order to access the different chains that we have, and the LLM we are going to use is from Ollama, right? So you can access this Ollama models from Langchain as well. And the FAISS CPU is used to do a similarity search of the vector embeddings, which we will create. And then we have this unstructured and unstructured PDF. So this is to extract the data from the PDF, which is the context that we are going to send to the model. And then we have transformers, which is nothing but the Hugging Face library, and then sentence transformer. So we are installing these libraries in order to load the embedding model. So how this works is, we have this PDF. Let's say that there is this PDF. So I can show this to you. So this is the PDF I'm going to use, which is nothing but a paper on transformers. Yeah, this is the paper. So this is the research paper that was released by Google for the first time about transformer. So we are going to pass it. So how this RAG works is, we first extract all this text from this PDF, chunk it into different pieces with proper overlaps so that the context is not missing. So now you have like different chunks of this particular document. Now you convert these text chunks into vector embeddings and store it in a vector database. So here we won't be using an actual database, but it will kind of be built on the fly with this FASS CPU. So we will build a knowledge base which has this vector embeddings of this text. And when a user asks a question, right, we do a similarity search. So we would convert this user's question into a vector. So now you have this large vector embeddings of all the text present in this document, and you have a vector which is nothing but the question that has been converted to a vector. So let's say that the user asks like, what is this document about? And now that question is, let's say, converted into a vector, and we do a similarity search, and let's say that abstract is the answer for that particular question. So we do the similarity search with this FASS library, and then we extract this information. So you have like two vectors now. One is the question vector and the answer vector. and using that you would extract the actual text, human readable text from the DB itself. And now we send this human readable text and the human readable question to the LLM, which is Llama 3 in this case, get a response and display that to the user. So this is how RAG works. So I hope this part is clear. So if you want a detailed explanation, again, I've made a video on the concept of RAG in my channel recently, so you can check that out. But this is the overall flow. Okay, so I hope everyone is clear about this. So yeah, that is about all these libraries. And FAS's CPU uses CPU, but there is another version for GPU. You can install it, but for Python 3.12, it's kind of creating some issues due to the CUDA versions and so on. So I'm just using CPU, but you can try installing GPU. So that would kind of fasten the process of getting the response. So that's something you can try, but for now, I'll just stick to this one. Okay, and within this src I have two files. One is my main.py file where I'm going to put all my Streamlit code, and then I have this doc chat utility which is I'm using as a modular code. So this code will contain the part where we would send a document name from this Streamlit app once the user has uploaded that file. So that document will be passed on to this particular code, and here we will do all those steps of converting into a vector embeddings, getting a response, and so on. So that's about the code structure. So you have a source code folder which contains these two files, and we have this requirements.txt file. So now let's start with building the user interface with the Streamlit app. So I'll import the required libraries. So first is import OS, and then I'll import Streamlit as CST, and then in this doc chat, let's create a placeholder function which we are going to fill in later. So here we can maybe say import OS, or we can come back to this part later. Okay, so we have import OS and import Streamlit as ST, and here I'm going to say working directory is equal to os.path dot directory name, and within that I'm going to pass os.path dot absolute path of file. So this is a very important piece of code. So let's understand what this line of code does. So I want to extract the entire path of this file. So when I say file, it's going to find the path of main.py. So if I go here and copy the path, right? So I'll give this, copy the absolute path and paste it over here. So this is what it's going to do. It's going to find the entire path of this file, which is main.py. The reason we are doing this is the file that the user is going to upload, the PDF file we are going to upload, we have to save in this working directory of, let's say, src. And when you run your Streamlit app, this won't be the working directory. So this env rec won't be your working directory, but the working directory will be the place where your Python is installed. So we have to give the complete path of the file to say that this is where your file is kind of saved. Okay, so that's the purpose of this. There is other way to do this. I can hard code this path. So I can hard code this working directory, but the issue with that is, right, so if I share this code with you, and you have to change this based on the directory that you have in your PC. So we don't want that. We have to find this working directory dynamically when we run this code. So that's why we are doing this. So the purpose of this working directory is mainly to find the path of this main.py file. Okay, so that's the first step. Now I'll say st.set page config. So here we can set the configuration of the pages, such as the page title, page icons, and how you want the layout to be. So all these things can be done here. So let's say that the title of the page is chat with doc, and let's give a icon to this as well. So page icon is equal to, I'll just copy a document symbol, document emoji. So I can do this from emoji PDF. So I'll copy this. You can, again, you don't have to do this, but this would just give this icon and name to this, which looks good. So you can also choose like a different icon as well, so no limitations on that. And then I can give the layout as layout is equal to center. Okay, these are all the three things. and then I'll say st.title. Let's call this document question answering, document Q&A, Llama 3 using Ollama. So you can give any name. Let's say that we are giving this particular name. So we can maybe try running this app. So come to your terminal and say Streamlit run src slash main.py, because the main.py file is present within this src folder. So your Streamlit app won't start if you just run this file. So you have to start this from the terminal using Streamlit run command. So I'll run this, and here you will see the URL. So localhost 8501 is the default port it runs, and here you can see this document emoji that we have copied, and the name is chat with doc, and we have a center layout and the title. So this is what we have done so far. So we have set up the page configuration, and then we have given the title for this Streamlit application. Okay. So the next step is we are going to create a file uploader widget to this application, so that the user can click that particular widget and upload a PDF document of their choice. So here I'll say uploaded file is equal to st dot, which is Streamlit, the Streamlit library that we have imported. So st dot file underscore uploader, and within that I can say label is equal to upload your file, and then we have another parameter called as type. So here we can say like what kind of files the user can upload. So let's say that first we are building this only for PDF files, but this can be scaled to other documents as well, Word files, TXT files, and so on. So that can be done. And we have this now let's create another variable called as user query, and this variable is going to store the question asked by the user, for which we have to give the answer from the PDF. So I'll create this user query variable and say st.text input. So this text input is a widget that's going to get the input from the user, so input text from the user, and within this within this parenthesis you can say ask your question. Okay, so when the user asks something, so this question or the text that they are typing in will be stored in this variable called as user query. So maybe first let's run this. So I'll open my terminal and again say streamlit run src slash main.py. So now you're seeing this upload your file, and there is a upload file widget, and I'll come back to the code. So this st.file uploader is what we are seeing, and the label is upload your file, and the type is PDF, and here in the browser it would show this file type as PDF, and you can browse your files. And now we have this text input widget, and it says kind of as this label called as ask your question, and then we have the text widget where we can like type in some question. Okay, so that's about creating these two widgets. So one is file uploader widget, and the second one is a text input widget. So next we can create a button called as, let's say, run or something, and when a user clicks in that button, we are going to process the document that they have passed and taken this question and respond with some proper answer from the LLM. So I'll say if st.button, let's call this a run. So if this button is clicked, right, so this if condition will be satisfied, and we have to do few things. So here I'll say bytes data is equal to uploaded file dot read, and we have to extract the file name. So for that I'll say file underscore name is equal to uploaded file dot name. So I'll explain you why we are doing this. So the purpose of this is to save the uploaded file to the working directory. Okay, so once the user has uploaded the file, so we are going to save that in this src directory. So that is the purpose of this particular piece of code. So let's do that. Okay, so let's create this entire file path, and this file path is equal to os.path.join working directory, comma file name. So basically we are joining this working directory, which is this src and the file name. So bytes data is nothing but, so we are reading this file uploaded by the user in bytes and storing this with the same file name. So when you call this uploaded file.name, so it will return you the name of the file that the user has kind of uploaded, and then we are storing it to this particular path. So here we have defined the path by joining this working directory and the file name. So now we can save this. So with open file path, so this will create a file in this particular file path, and wb, that means like we are going to write this files in bytes as f, and here I'll say f dot write bytes data. Okay, so this will save this file. So the next step is we have to get the answer. So we have to process this document that we have saved in this particular file path and get a response. So that part of the code will be handled by this doc chat utility. Okay, so that will be the next step. So now let's see how we can do this by using Langchain, and using that we can load the Llama 3 model that we have in Ollama, and we can do that. So let's go into that part. So first I'll import OS. So here also we have to define the working directory. So for that reason I'm importing this OS, and then from Langchain community dot llms import Ollama. So this is to load the model, and from Langchain document loaders. Okay, so it should be Langchain dot document loaders. Let's import unstructured file loader. So this is the unstructured library that we have installed. So I'll call this unstructured file loader. This is the one. Okay, so this will be using in order to read the PDF file and extract its contents. Now Langchain underscore community dot vector store. Import FAISS. This is to do the similarity search on the PDF embedding, vector embeddings, and the question that's asked by the user. So FAISS, which stands for Facebook AI similarity search. Now from Langchain dot embeddings import Hugging Face embeddings. This is the embedding model that's going to convert the text into vector embeddings, and then we need Langchain dot text splitters. Import character text splitter. So this is used in order to, one second. So used in order to split the text into smaller chunks, and then this will be converted into vector embedding. So we can't do this on the entire document, so the data will be pretty huge, so we can't pass this entire data to the LLM, so we are chunking it. So I'll say character text splitter, and finally we have to import the chain. So from Langchain dot chains import retrieval QA. So here we are working on a simple document question answering, so I'm using a retrieval QA. So if you are working more of a conversational kind of chain, you can use like conversational QA chain and so on. So here we have this retrieval QA. Okay, that is all. Let me run this once to make sure that all the input statements are right. Langchain Hugging Face embeddings, new import of, so okay, these are just warnings, so that's fine. So we don't see any errors here. Okay, right, so this is okay then. So the next step will be specifying the working directory. So for this we can copy this same working directory that we have in this Streamlit code. So I'll copy this because we have to read the file that has been saved, right? So in the previous step we have saved the file, so we need to locate that file. So for that we are specifying this working directory, and now we can load our LLM. So in order to load our LLM, you can use this Ollama, and within that you can pass the model. So I'll say this model is equal to llama 3 colon instruct. So this is the model that I'm going to use. So again, if you are using a different model, you can kind of use that as well. And again, you can pull any model of your choice that's present in Ollama, and in order to list that, you can use Ollama list as we have discussed already. So here I have Gemma 2 billion, llama 3 instruct, and Gemma 7 billion. So I'm going to use llama 3 instruct. So I have to use the same name here. So if you want to use Gemma 7 billion, you have to specify that name. So I'll close this terminal for now. So this won't work if you haven't pulled your model already. So you have to do that in the first step. So here I'll say temperature is equal to 0. So this reduces the randomness of your output. So if the temperature value ranges between 0 and 1. If the value is smaller, it's going to give you less random answer for a specific question. If the value is more, it's going to get creative and give you like different response every time. So here we are loading the LLM, and next let's load our embedding model. So here I'll say embeddings is equal to Hugging Face embeddings, which is the module that we have imported. This will load the specific like default embedding model, but you can also like specify some other models that's present in the sentence transformer library as well. So that will work. If you think that you want to use a better embedding model that is like, let's say, pretty large, you can choose a different model as well. So that's the thing. And now let's create a function that's going to take in the file name and the query, and it's going to process this. So we have this uploaded file and the query, right? So it's going to take these details, process this, and give an answer for that particular user's question. So here I'll say define get answer. So the input parameters will be file name and query, and the file path would be, it's same. You can do a os.path.join, or you can just use a simple string with f, which is basically used to substitute some string values. So I'll say working directory slash, again in curly brackets I can say file name. So this is nothing but it will give in the working directory details. So it's like this particular directory slash the name of the file that we get from the function. So this particular function we will call from here, from this Streamlit code, and then this function will process the file and give a response to the user. So now we have to load the document. So here we have to instantiate the unstructured file loader. So I'll say unstructured file loader, and within this you can pass the file path, the path of the PDF file that has been uploaded. And in the next line you can load it by documents is equal to loader.load. So this two steps, right? The purpose of this is to read the PDF file and extract all the text contents from it. So that's the step. So maybe here I'll put a comment saying that loading the document, and the next part is create text chunks. So we can't put this entire text into convert these into vector embeddings and store this, because in that case you will send this entire text into the LLM. So that's not what we want. So we are going to chunk it, store it in the vector database kind of a thing, right? So vector, we are going to convert these text chunks into vector embeddings, and when we match a particular text chunk with the user's question, so we pass that chunk alone and the user question to the LLM, and the LLM will answer. So please understand this part where we are not sending the vector embeddings to the model, but the text is kind of sent. The vector embeddings part is done just to do this similarity search thing. So once we find this text chunk that is relevant to the user's question, we retrieve the corresponding text and send the corresponding natural language or human readable text and this user question to the LLM, and the LLM will frame an answer for that. So that's how this would work. So here I'll create a variable called as text splitter, where we can load this character text splitter. So character text splitter, here we have to pass in few parameters. So first one is the separator. So what's the separator is going to be? So let's say that we have this new line separator, and then we have this chunk size, and chunk size, again you can play around with these numbers. So here I'll use 1000 as my chunk size, and chunk overlap is equal to 200. So here we are splitting this document into different chunks, right? So the overlap is required so that the context is not missed. So we shouldn't make a hard stop for these chunks. So it should always have some overlap so that all chunks are kind of connected and there is some overlap between them. So this is our text splitter, and then I'll say text chunks is equal to text splitter dot split documents, and within that I'm going to pass the documents that we have loaded. So here we are specifying how we want the character text splitter to be, the parameters for it, and then we are passing the documents which we have read using unstructured file loader. So this will split the document into different chunks, and this will be stored in this text chunks. So later these text chunks can be converted into vector embeddings. So here I'll say vector embeddings from text chunks. So knowledge base is equal to FAISS dot from documents, and within that first we have to pass the text chunks that we have created, and then the embedding model that we have loaded, which is Hugging Face embeddings in this case. So embeddings, right? So this will create this vector embeddings and store it in the variable called as knowledge base. So this FASS kind of works in memory. So if you want a proper vector DB, you can go with options like ChromaDB and other vector DB that's present. So ChromaDB is like a open source one, so you can try that without any charges. So that's about this. And then now we can build a chain for our QA thing, so that we pass this LLM and this knowledge base, and the LLM will be able to answer for a user's question. So I'll create a variable called as QA chain, and this QA chain is equal to retrieval QA, which is the chain that we have imported from Langchain. And I can say from chain type, so we have to pass the parameters such as LLM, and the retriever is knowledge base okay, so it's knowledge dot as retriever, and put a parenthesis here. Yeah, it's already there. Now we can say response is equal to QA chain dot invoke query, and this query will be the same thing, query. And finally I can return response result. So this final result is stored within this result variable, and now we add this one. There shouldn't be a curly braces here. Let's quickly understand what we have done. Okay, so we have imported all the libraries and we are specifying the working directory so that we can access the file by specifying this working directory. And then we are loading this LLM from Ollama, which we have pulled, which is Llama 3 instruct in this case, and we have specified the temperature parameter. And then we are importing the embeddings model from Hugging Face, and then we are creating a variable called as get answer. And this get answer function will take in two parameters. The first one is the name of the file the user has uploaded, so that we can locate it in this working directory, and then the query, the user's question itself. So here we are creating the file path by combining the working directory and the file name to get the entire path of the file, and later this is passed on to the unstructured file loader function, and this will load the PDF file and store all the text contents in this variable called as documents. So next part is creating a text splitter, where we are using a character text splitter. So there is another text splitter called as a recursive text splitter. You can try that as well. So yes, we are specifying the separator, the new line separator, chunk size, and what's the overlap is going to be. Again, you can play around with different numbers. And here we are creating this text chunks by using text splitter split documents, and we are passing these documents that we have loaded, and we finally be getting this text chunks in this variable called as text underscore chunks. And then using this FASS from documents, we are creating vector embeddings for these individual text chunks. So let's say that there are 20 text chunks that we get from this PDF file. So we would kind of convert all these things into vector embeddings and store in this knowledge base. And then we have this QA chain, and we say this retrieval QA dot from chain type retriever is equal to knowledge base. So here we are creating a chain and saying that the LLM that you're going to use is this one, which is Llama 3 instructor in this case, and this is the knowledge base. That means you have to look for the answer in this particular knowledge base. So how this would work is when this QA chain is invoked, which is in this case it's invoked with a particular query, which is nothing but the user query, right? So let's say that the user is asking a particular question that's present in the document. So this QA chain, the process it works is it would convert this query, the user's question. So let's say that they are asking what is this document about. So this question is converted into a vector embedding as well, and it is matched with those 20 text chunks, but these text chunks are not in the form of text but as vector embeddings. So we do a vector similarity search, and let's say that chunk 18 as the answer for this particular query. So we retrieve the corresponding natural language text, the exact text that's present in the PDF, and the query that the user has sent. So only this part is sent to the LLM in the next step in this QA chain, and the LLM will frame a proper answer for this particular question, and it would kind of give you the response. So that's what happens in the retrieval QA. And within this function, in the Langchain, there are like pre-built prompts that are like already present over here. So again, so that's how like it's able to give this output here. So yeah, that's how this works. Okay, so I hope this part is clear. So first we split the text documents, convert it into vector embeddings, and then you have this user query, get the relevant information, pass to the LLM, and get a response. So this is how it's going to work. Now let's put this, or maybe let's call this function from our Streamlit code, and let's see how this is giving us a response. So this file name is docchat utility, which is in the same directory as my main.py, which has the Streamlit code, and I'm going to use this get answer function. So I'll come back to my Streamlit code, and here we can say answer is equal to, or first we can import the function. So from docchat utility import get answer. So that is the reason I'm importing the libraries in this way. So in the first steps we import all this pre-built libraries in Python, and in the next step we can install like the other libraries that we have installed, the third-party libraries, and then in the next step we have this custom Python functions and modules, right? So that can be imported in the next step, and you can leave a line space between like each of these things. So this is like a page standards that you can follow so that your code is like more structured. So now I'll say answer is equal to get answer, which is the function that we have imported, and within this I'm going to pass my file name and the user query, and this will give me a response. And finally I can say st.success, which would create this green text bar, and inside that we can display the answer for the user. So this is the entire steps. So when we run this for the first time, it's going to take a few seconds because it has to load this Hugging Face embeddings model, which is like about 400 MB or something. So the first time you run this, it may take some time, so you can maybe keep that in mind. Now I'll probably clear this Streamlit running in the background and start it again, and let's see. So I'm going to upload this paper on attention is all you need, and ask a maybe simple question of like what is this document about, and maybe a few others. So here I'll browse the files, and it's present in my downloads. So I'll say what is this document about and run. So you can see the process is running in the background. So this will, if you open this PyCharm right now, you can see like all the warnings and other things that's being going on in this particular code. So here this Hugging Face model will be pulled, and all those things will be done. And finally we will see a response. So let's wait for it to complete. So when you run this the second time, this won't take because we have already initiated the embedding model, the LLM and so on. So this won't take a lot of time from the second run. So you can ignore these warnings, so it's like not a big deal. So it says that this document appears to be a research paper on article about the transformer sequence transduction and so on. So this is how you can you know, paste in a question and get a response from this. So I hope everyone is clear until this point. Please try this code. Maybe I'll just give you a quick recap of what we have done in the Streamlit. So we have just like built a simple user interface with page configuration and so on. And the two key factors are your file uploaded widget and the user's question. And then we have this button thing, st dot button, where once the user has clicked that button, we are going to process that file, get a response from the LLM using this doc chat utility code, and finally we are going to display that answer using this st.success. So this is how you can build a Streamlit interface for your local RAG application, where we have used Llama 3 as our model hosted in our local system using Ollama. So please try this code and let me know in the comments if you have some doubts or facing some issues. That's it from my side, and I'll see you in the next upload. Thanks for watching.